Hey everyone, today we will be finally implementing the EnCodec architecture, which is essentially a neural audio codec. I already had a previous video talking about speech tokenizers, which are essentially just audio codecs, so go ahead and take a look at that if you want some more prerequisites or background of why these architectures are really cool. But we're going to be implementing EnCodec because it's essentially one of the most foundational architectures, and a lot of the modern research are just iterative methods improving on top of this architecture specifically. Now, as you can see in EnCodec, there is a ton of stuff going on. So we're going to mostly be focusing on everything except for these transformer blocks here. This transformer that you see here is a secondary stage of training of EnCodec, where we essentially train it on the codes from the vector quantizer to additionally reduce our bit rate. We're not going to care about that, so ignore this, but everything else here we're going to be implementing. The other difference between our implementation and what the original EnCodec implementation is that we will be not implementing a streaming mode. So we're going to assume that we get all the audio up front and we essentially compress, decompress, and we're good to go. The original EnCodec architecture also supports streaming, where we can essentially just pass in audio in real time, and as we're passing it in, we can quantize it and do all that sort of stuff, but that's really just details that we're not going to focus on. So to go ahead and get started, the bit rate of audio is typically, if we have 24,000 samples per second, and each sample having 16 bits, we get 384 kilobits per second. And that was the entire purpose of codecs. Standard codecs like MP3s or WAV files or whatever, these are essentially going to take the raw bit depth, right, the bit rate of our audio and reduce it down. That's the entire goal. But neural audio codecs seem to be able to compress to even lower rates than other methods. Where these numbers come from, we already covered in the previous video, but I'll come back to this again later. Now, our main goal of audio codecs is not really its compressive ability, although that is important for a lot of applications. For us, it's more that we want to treat these codes. Basically, this audio gets passed through multiple codebooks and a residual vector quantizer. And from each residual vector quantizer, we get some code index, right? Like it's 2890 across time. So we get code indexes across time. And of course, we're going to get a sequence of these code indexes from every single codebook that we quantize with. We can potentially pass these into large language models for generative tasks, because if I know that I have a encoder that can compress to these codes and a decoder that can take these codes and decompress back to the original audio, then the generation of my audio really just depends on the generation of these tokens. And if these are just standard discrete tokens, then why not use an LLM? That's the speech LLM stuff that we'll focus on another day. The encoder-decoder portion of the architecture is simply the SeaNet architecture. So you can read that paper. This paper is proposed for essentially cleaning of noise to basically denoise speech and things like that. So the standard SeaNet architecture, the implementation is not very challenging. Just a couple of little details and padding things that we'll have to deal with, but it's fine. We'll see it when we get there. The quantization is the more interesting part. Of course, there is residual vector quantization, but we'll be looking for now, just let's look at one of those quantizations, because residual vector quantization just does a lot of quantization in sequence. And so in quantization, basically our encoder produces an embedding vector. We'll have one embedding vector per time step, across time per time step of audio, but whatever it may be, we have some vector here. This vector then looks at this code book, and then we select argmin the closest code, right? Which code here in my code book is closest to this embedding vector right here. And then we take that codebook and we pass it forward. The problem with quantization, of course, is this argmin operation is non-differentiable. So to solve this, in our VQVAE tutorial that we had a while back, I'll link it down below, we looked at the codebook and commitment loss. This is the formulation from the original VQVAE paper, where essentially we use something called stop gradients. And it kind of looks like this. The commitment loss says that we want our encoder to produce embeddings that are close to the embeddings, the code vectors in our codebook. But because I can't actually compute the derivative between the codebook and the embedding vector here, let's go ahead and add stop gradients. Basically treat EK, which is one of our codes, as a constant. And then because this is being treated as a constant, essentially the optimizer sees that we're trying to minimize the distance between the output of the encoder and some constant, which is no problem. That doesn't cause any issues. In the same way, we have our codebook loss, where codebook loss is just the reverse. You can see it's exactly the opposite, but now what we want to do is have the code vectors update in a direction that's close to our output of the embedding. And so you can see that we're essentially just swapping the stop gradient. Now, the key idea is that in the commitment loss, this is essentially saying that the encoder should produce embeddings that are close to here. So this computes gradients for the encoder. The codebook loss, the more important part, is that we want our code vectors to be close to this, where this is essentially treated as some kind of a constant. And if that's the case, that's no problem. When we try to minimize this, that's what the optimizer sees, is just a constant, and then it produces gradients here. And these gradients are essentially just going to, be used to update these code vectors. And this is how we did it in the VQVAE tutorial. Of course, we're not going to implement it that way because that's not how the EnCodec architecture implements it. Other, maybe more modern, but maybe more current or other speech tokenizers have used codebook and commitment loss and have found great results with it. So there's no reason you couldn't do it the other way. It's just we're going to stick to the EnCodec implementation as much as possible. So in EnCodec, they use essentially we still keep the same commitment loss, so that's no problem. But instead of computing the gradients of the code vectors here with some kind of approximate, try to get this to be close to here, we're going to update them with exponential moving averages. The way to think about this is our quantization. This entire quantization process is basically just k-means, right? K-means. We're going to have some, let's say we have some clusters of points here, and the code vectors are essentially the cluster centroids. And so the process will be kind of like this. We need to be able to iteratively update our code vectors without using gradient descent. And this formulation looks kind of scary, but it's really not. So let's kind of think about it. Our k-means, so when we pass our model, our first batch of data, we're going to get all these embedding vectors, right? We're going to have a bunch of them. And so we can go ahead and initialize the code vectors with k-means. So, just run standard k-means clustering on these code vectors. No problem at all. Once we do that, then we can compute some statistics. One of them being, for every single code vector, how many points was it assigned to? That's n. And what is the sum of all the assigned code vectors? So for example, in this cluster right here, we can see there's 9 points. So there's 9. And m would be the sum of these embedding vectors. Just sum, nothing fancy. We just add them all together. The reason we do this is because the code vector is the mean, right? It's the mean of that cluster. So if I take m, which is the sum of all the values, divided by n, the number of values, well, it's just the average, right? That's equivalent to taking the average. But we don't just store the average like this because we're going to be doing something interesting here. We'll see that in just a second. But that's the main idea. Go ahead, initialize, and we can create some values like this here about the number of assigned clusters or the number of assigned points to every cluster, and then the sum of those assigned points. So of course, the reason we need to be able to compute this iteratively is because in standard k-means, when we run k-means clustering like we do here, normally you just have all your data and there you go. You're good to go. You compute k-means and you're done. But there's two problems with this formulation. Number one, when we look at this, as we're training our model, the distribution, right? The embedding space will continue to change as this changes. So that's one problem. And two, we typically train on batches of data. Our model doesn't see everything, it just sees a small subset of the data. And so that's what I meant by on the very first batch, go ahead and initialize it like this. But of course, then a new batch comes in and we have new data points. Well, if we have new data points, let's go ahead and just check. We have the original cluster centers, those are the red. The greens are, we can see they've moved over a little bit. So we need to essentially update the reds to be in the new cluster center. So for every single one of these centroids, go ahead, find the nearest, nearest points essentially to every single one of them, count up and just, compute your statistics again. How many have we assigned to this specific point? 13 of them, 5 of them, 11 of them, and then the sum of those assigned points. And so once we do that, well, we go ahead and update, right? Go ahead, just compute the mean. We get the average of, we can compute the average, just m over n for all these clusters, and we're done, right? No, wrong. This update method would be far too noisy because every time a new batch comes in, we're essentially just computing a completely new cluster center. And the problem is, especially when the model doesn't know anything and the distribution of this embedding space is highly variable right at the start of training, this will lead to divergence, right? Basically, it's just going to update to Yeah, it's just going to update too quickly. And we need to be able to have a better way of shifting these around. So updates are too noisy. That's the problem. The way we solve this is by smoothing it using exponential decay. So instead of just saying that our cluster centers are just based on the current n and the current m, let's go ahead and do an exponential moving average where my n for this time step, right, this iteration, this batch, so t is the batch index, which batch are we on, is going to be the, some gamma, 0.99 is the default, I believe, 0.99 times the previous value plus 1 minus 0.99 times the current statistic for the current batch. And then we do the same thing for the mean. For this specific mean, for this specific batch, we do the exponential decay of the previous batch plus 1 minus that decay value plus times my current one. And by doing this, essentially we're just going to keep a running estimate of my number of samples per k, right? So for every cluster center, we're going to have number of samples assigned to it, and per k, the sum of those embedding vectors. And by smoothing it this way, we get a better representation, a smoother representation. So instead of just every single batch, our cluster center just hopping around all over the place, well, if we set a constraint that our cluster center has to be, if this is my original cluster center from the previous iteration, and this is the new cluster center that would have been computed from this iteration, well, it would be somewhere in between, right? Because we do 0.99 times the statistics for this one, plus 1 minus 0.99 times the statistics for this one, the new statistics. And by doing it this way, we essentially just incorporate some smoothing into those updates. There is a engineering problem though, and that's in distributed training. Of course, we want to be able to train on multiple GPUs, not just one. And this means that every single GPU, of course, is going to get a different batch, and every batch is going to be slightly different. And our number of samples assigned to each cluster, of course, the cluster centers themselves are synchronized, or those are going to be identical across GPUs. But the data coming in and the statistics that we compute about the running sum and the enumeration, right, the number of samples assigned, that'll be different per GPU. And so when we do our update, we need to make sure we actually gather this information across GPUs. We want the global statistics across all GPUs, not just the current statistic per GPU. And so when we write the quantizer, we're going to be focusing a lot on how to get this to run in distributed training specifically. Of course, that's like extra. Most people don't really care about details like that, but it is important if you actually want to train models like this. Of course, we're not going to be doing just standard quantization. We'll be doing residual vector quantization, but that doesn't really change anything, right? We still have, essentially, instead of having one quantization notebook or codebook, we're going to have, however many, 8 of them, 10 of them, however many you want, doesn't matter. And here's the other part that's challenging. We have a ton of loss values. So of course we have the quantization stuff, and that has its own thing, but we're also going to have our bunch of losses. We're going to have a codebook loss that comes out of basically the commitment loss, things like that. We have a discriminator, which means we're going to have a discriminator and a generator loss. We're going to have a MEL spectrogram loss. We're going to compare MEL spectrograms to each other. We're going to have a time loss where we compare the actual waveforms to each other because we want to make sure that the input looks like the output as much as possible. Because we have so many different loss values, we need to find a way to balance it. And so essentially it looks like this. With this audio, we produce all these different losses. And so the total loss is just the sum of them. And then when we do backpropagation, then each of these losses contribute to the the gradient at the layer that produced this audio. And then our overall gradient is the gradient contribution from each of these losses. But of course, if all of our losses have different ranges, like if loss 1 is small numbers, loss 2 is large numbers, and loss 3 is kind of between here, then just by default, loss 2 will have more gradient contribution. It'll have more of an effect on the model than the other losses, just because the magnitude is larger. And of course, that's not really what we want. Like maybe loss 1 is extra important to us, and we want to make sure the model's really trying to minimize this one. But that wouldn't happen because the scale is different. This is why we typically multiply by some constants, right? We can multiply loss 1 by a. So if we want loss 1 to have a similar magnitude to loss 3, we can multiply this by like 10. And if you want loss 2 to have similar magnitude to like 3, we can like divide by 50 or 75 or something like that. And so balancing these is kind of important. Since we multiply them by some constants, so the gradients are essentially all multiplied by a constant, and if all the gradients are multiplied by a constant, then we can go ahead and balance it out. The problem with this is it's not very interpretable, right? It would be easier if the loss was balanced according to the proportion of the overall weights. Ideally, we would have, if we had the ratio of our losses, A to B to C, our loss weights, and these are set by us, A to B to C. So if I say I want a 1 to 2 to 1 ratio, then my gradients should also be 1 to 2 to 1, right? Just based on intuition, it'd be easy to have it that way. And so in the EnCodec, the other novelty is the automatic weight balancing, where we essentially just compute those gradients and then we re-weight them so they follow exactly that proportion. We'll implement that later. Again, there's another engineering challenge here where these gradients are not based on the gradients of one GPU, but across all GPUs, right? So we need to do that gather again. And that's basically it. So you can see there's a lot of really small details going on. And so let's just go ahead and start with implementing the model, and we'll reference back to this as we are going. So just to start off, we need to implement a base conv model, nothing very fancy. And this convolution model essentially has a couple of different options, and we're not going to care about all of them right now, but we'll just implement it just to make it look similar. This is based on, there's a EnCodec trainer Git repo. I'll link some Git repos down below that essentially a lot of this code is inspired from, but just to make it simple, I can find this right here. So yeah, there's a couple references, so I just want to make sure I show you them. These are results. Where did my references? Here we go. So of course the original EnCodec implementation from Meta, right? So of course take a look at that. But more important than that, EnCodec, their implementation didn't release any kind of training script or anything like that. And so there's been some awesome extension packages like the EnCodec trainer that this is based on. So you can take a look at this. And then of course the EnCodec PyTorch implementation. These are a little bit different because none of them use Accelerate, and I like using Accelerate, Hugging Face Accelerate, for distributed training. And this has some extra stuff that I didn't really implement, so we'll see exactly how we implement it. So I think mine is just like a simplified version of this because I don't have as many features. Okay, good. So let's go ahead and get started. So what we need to first implement is a convolution with layer normalization. Nothing very fancy. And there's a couple of different types of normalization that we can do, but layer norm is, let's go ahead and just implement a layer norm specifically for convolutions. So it's going to be class conv layer norm and then dot layer norm. So it's just going to be a wrapper on the existing layer norm. And layer norm just takes a normalized shape, and it can take other kwargs if we pass them in, whatever it may be. So it's just standard layer norm. The only reason we have to do this is because layer norm expects the shape of batch by L by E. That's, standard layer norm works on that. And the normalized shape in our case would just be E, because that's the dimension that we want to compute the layer norm over. But when we do convolutions, our data is going to be batch by channels by L, essentially. And so we need to just transpose these two dimensions, perform the layer norm, and then transpose them back. That's essentially all this is going to do. So it's going to be super dot init, and we're going to initialize it with the standard layer norm, so normalize shape and all the other kwargs that we want to pass in. Nothing else here, and so def forward self x, and we're going to do x is inops dot rearrange, and we're just using inops to make this simple. So b, they're going to be a bunch of dimensions in the middle, and then t, because we said it was batch by channels by sequence length. And we're going to just make this batch by t by everything else. So we're just bringing that to the beginning. And this everything else is normalized shape, and normalized shape in our case is just that one dimension. So there's really nothing going on. X is then going to be super, and we're going to actually pass it through the forward method of our layer normalization, and then we're just going to do x is again inops dot rearrange. Just put it back how we found it. So batch by t, and we're going to just put it back to batch by blank 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 t. Simple as that. So first helper method done. We have two kinds of normalizations. One is weight normalization. So we kind of briefly took a look at these in our HiFiGAN implementation, but essentially weight norm and spectral weight norm, for example, instead of just training the weights of the model directly, the weights of some layer, let's say a convolution layer directly, we instead decompose the weights into two things, the magnitude of the weights and the direction of the weights. And by decomposing it this way and training it with kind of these separate parameters, essentially, research has essentially found better stability in GAN training. So weight norm and spectral norm have been proven to have better stability when training GAN based models, and that's why we have it here. We also have these normalizations here, which is your standard like layer normalizations and stuff like that. So this is fine. So we're going to do def apply parameterization norm. So if you want to do this, then to a module, we're going to add some kind of normalization method. We're going to make sure assert the norm method we pick is inside the conv, all those options from above. And then very simply, if norm is weight norm, then we're going to do return weight norm module. If norm is spectral norm, and similarly, we'll return spectral norm module. Otherwise, there's nothing to do. Else, just return module. In the same way, we're going to be able to, we also want to add an option to just add layer norm. So we're going to do def get norm module, norm kwargs, and we're going to assert norm in, again, conv normalizations, and we're going to do if norm is layer norm, then we're going to do return conv layer norm module dot out channels norm kwargs, because remember our data is going to be in the shape of batch by channels by L. That's the typical shape, and this convolution is going to apply something to here, and it's going to output some output number of channels, module.out channels, and then to that out channel, we're going to apply our conv layer norm, which is going to transpose the dimensions, do the layer norm, and then transpose them back. And so that's all it is. Or we could also do group norm. So if norm is time group norm, we can do return nn.group norm one module dot out channels norm kwargs. Now, anyone who can see this immediately sees that what's the difference between doing a layer normalization versus a group normalization with only one group? Technically, a group normalization with one group is identical, or supposed to be identical. It looks identical to a layer norm because a group norm essentially just does the layer norm, but in chunks. The main difference is in layer norm and group norm, we don't have just the normalization parameters. We also have a gamma and beta, right? Basically a scale and bias, trainable scale and bias term. And in the layer norm, these all happen at the pixel level. So basically for every single pixel or time step or whatever, we have one of those. But in the group norm, there's kind of a global one for each chunk that happens. So there's a, you can look in if you find this code in my Git repo, I have a link to PyTorch discussions about kind of the nuances of this stuff, but I don't want to go into details about this because it's not really that interesting. And I think we just use layer norm, so it doesn't really matter. Identity. There we go. Okay, so there we go. If we don't have anything, then we don't have anything. So now we're going to implement, I'm going to write the first one and then just copy in the last couple because they're all the same. Norm conv 1d nn.module. Well, this is going to be very simply def init. We're going to have self. We have standard arguments. What norm do we want? None by default. Normalization keywords if we have them, and then any other kwargs if we have them. So it's very generic input, and super.init. And we're going to do self.conv is going to be apply parameterization norm, and we're going to apply it to an nn.conv 1d that has some args and kwargs, so we can just use standard inputs and then some norm, whatever norm that we want to apply to it. And if it's nothing, then we'll just return the module. So it just depends. By default, it's none. Else, or not else, but the second thing is our norm itself. So if, we can have a parameterization norm, or we can have standard layer norm, group norm, whatever it may be. So that's why we have the get norm module self.conv norm, and then norm kwards, just like that. And so in the forward method, very simple, self x, we're going to return self.norm, self.conv x. And that's what it's going to look like for a 1D convolution. Of course, we need to also do it for a 2D conv, and then we need to do it for a transpose 1D conv and a transpose 2D conv, and all of this code is just repetition, so I'm just going to paste it in. So you can see we had that 1D conv from earlier, then 2D is exactly the same thing, but it's conv 2D instead of conv 1D, and then we have our transpose conv 1D, and then we have our transpose conv 2D, but other than that, the code is identical, so we don't have to worry about it other than that. Okay, now for the first kind of annoying part. So I'm going to just start, we're going to come back, we're going to have to write a couple chunks of code, but the main things we're going to have to write is these two methods, def get extra padding for conv 1D. This can take x, kernel size, stride, and something called padding total, which we haven't seen yet. We're going to have to write this. We're going to have to also write def pad 1D x padding mode is 0 and value is 0 pass, and we're going to also have to write def unpad 1D x paddings pass. So we'll fill these in just a second. So what we're going to do is write the base convolutions. This is the actual convolution that the SeaNet is going to be using. So class sconv 1D nn.module. Now here is the problem. So let's go ahead and just kind of do a test case. Let's say rand is torch.randn 2 by, let's say we have 3 input channels and 1000 and I don't know, 2 is my sequence length, right? And our conv is going to be nn.conv 1D, and we're going to have essentially 2. Not 2. It's going to be an input channel 3. We'll keep an output channel 3. Let's say we have a kernel size of 5 and a stride of 2. So we're going to do print conv. We're going to apply it to rand and then print out the shape. Now what I want, let's first look at the Python m modules dot, what was it called? Conv. Okay. What I want is if I say I have a stride of 2, regardless of the kernel size, if I say I have a stride of 2, I want my audio, the length of the audio, to downsample by exactly the stride. So I would expect this to be 501. But you can see we got 499. And so of course we need to just mess with the padding. So we can do padding equals like 1 maybe. Let's test that. So that puts us at 500. Maybe padding equals 2 maybe. There you go, 501. So in this case, padding equals 2 is the correct answer. But of course, every audio is going to be slightly different. Like this could be 3, and we're still, it's 502 now. So it's always going to be a little different. And so ideally, we have a way to handle this automatically. And all of this padding computation here is kind of like what PyTorch does internally. If I set like padding equals same, but padding equals same, we'll just pad it so the input size doesn't change. PyTorch does not have an option to say like, padding to like some specific factor, right? Like make sure downsamples by a specific factor. So that's what we're going to have to be doing right here. This logic is not very hard. It's just a little bit involved. So I'm going to copy actually all of the stuff that is repetition from before. So this is a convolution with in-channel, out-channel, kernel size, stride, dilation, groups, bias, So all of this stuff is your standard convolution up to groups and then and up to bias. And then this is the extra stuff that we're adding in. And here's all of our standard stuff. And here's that norm conv 1D from earlier. Nothing fancy. And so the first thing we need to do is in our forward function, so def forward self x. And we know our data coming in is going to be batched by channels by sequence length is x dot shape. Now, here is the first key thing to keep in mind. So let's look up dilated convolutions. So dilated convolutions or Atrius convolutions, there's a couple terms for them. They look like this, right? Where our convolution kernels are not consecutive. They look, they have, they're separated out in this way. And so technically this is a 3x3 filter, right? Because there's, 3 values. It's a 3x3 kernel, but even if it's a 3x3 kernel, we can see it looks like a 5x5 because they're spread out. And so there is the actual kernel size, which is 3x3, but the effective kernel size, just because the amount of space this kernel is taking up, is technically 5x5. And so we need to be able to first compute that. What is the effective kernel size that we have? That's pretty easy. Our kernel size is going to be equal to self.kernel size minus 1 times self.dilation, it's just a formula, plus 1. And just to make an example, if our true kernel size is 3, but our dilation is 2, like we had in that picture, then 3 minus 1 times 2 plus 1. So that's going to be 2 times 2, 4, plus 1 is 5. And 5 is exactly what we have here, right there. There's a total length of 5 on each side. And so this is just standard formula to get the effective kernel size. So this is the effective kernel size. There we go. Now, what we need to do is make sure that we have enough padding such that the output, we want to make sure there's enough padding, padding such that the output is equal to the input divided by stride. So the length of the output should be the length of the input divided by the stride. And I'm going to paste a little bit of quick math here. So we'll kind of go through this math. This is just algebraic manipulation to make this happen. So this is the standard formula for our convolution. Okay, so the output of the convolution, you can find this directly from PyTorch. In PyTorch, they have 2 times padding, but we're doing padding total. So padding total for us is the total padding on both sides. If we add padding, we add it to both sides of the audio or the image or whatever. And so that's the padding total. For simplicity right now, let's assume this floor function just disappears. Okay, disappears. We're gonna handle that condition a little bit later, that exception. For now, let's assume it just disappears. And so let's just say the output length is really just the input length plus padding, standard formula from earlier, just without the floor function. And what we're gonna do is we're going to set some variable called padding total as the kernel size minus stride. Now, why would we do that? Well, let's just go through the math. So I'll just paste the math in here. Output length is equal to the input length plus padding total minus kernel size. If I'm saying padding total is kernel size minus stride, then the output length is the input length plus the kernel size minus stride, so kernel size minus stride, minus the kernel size. And this kernel size and this kernel size, it's plus, minus, so they'll disappear. They'll cancel each other out. So we're left with input length minus stride divided by stride plus 1. And so you have A minus B over C, so it's going to be A over C minus B over C. So input length over stride minus stride over stride. Stride over stride is just 1, so it's minus 1 plus 1. And we're left with output length is equal to input length divided by stride. So this means if I have a padding total is equal to kernel size minus self.stride, assuming that it's divisible, so that floor function no longer exists, then we're good, right? That's what we need. Now, of course, we can't just assume that it's divisible, so we have one other extra condition. And so I'm going to paste that example right here. So we had this assumption that things divide evenly, and this only works if every convolution window is full. So for example, our original data, let's say is 1, 2, 3, 4, and we have a stride of 2, kernel size of 4, and we say total padding is 4. So if total padding is 4, that means we have 2 on one side and 2 on the other side, right? Because we've split the padding on each side. And if we have a kernel size of 4 with a stride of 2, let's go and do it. So kernel size of 4, starting here, we go forward 4, and that goes with this 1 position. Then we move over by 2, go over by 4, that goes in this 2 position. Move over by 2, go over by 4, that goes in this 3rd position. But notice this last 0, this last one right here, is untouched. It's never used. And this is a problem because essentially not everything is being utilized. And if not everything's being utilized, then we're not having complete windows, right? So that's why this floor function exists. So how can I make it such that that doesn't happen? So I always have full usage of all windows. Well, we can compute some extra padding. Let's say we add another. So we had 2 zeros and 2 zeros as padding. Let's do 2 zeros and 2 zeros, but add an extra 0 right here. Now we have 1, 2, 3, 4. No problem. Let's move over by 2, 1, 2, 3, 4. Move over by 2, 1, 2, 3, 4. Move over by 2, 1, 2, 3, 4. And so now we have all 4 outputs that are all using complete windows on this. And that's exactly what we want to be able to accomplish. Basically, just make sure that we're using everything. So every convolution kind of exhausts the entire window size, that we're not just, clipping off and missing a value or something like that. So to do this, we need to compute this extra padding. The formula for this is relatively straightforward. So what we're going to do is just write down write it down like this. So we're going to I'm going to copy this example right here. There we go. So let's say x has some length of 10, with a kernel size of 3, start of 2, padding total is 2. And so we know from our standard formula for convolutions, ignoring that floor function, that this would mean the output length would be 10 minus 3 plus 2 divided by 2, the stride, plus 1, which is 5.5. And 5.5 means that we are missing a portion, right? Basically, that last window never actually happens because only half of it's available. And so this is what we want to solve. Ideally, so basically the question we need to ask ourselves is, if I don't want it to be 5.5, I want it to be 6. I want a complete window at the end. So what does x, so x is originally 10, but let's just set it to a variable. What does the length of this have to be to give me 6 here instead of 5.5? I know if it's 10, it's 5.5, but if it's something else, what gives me 6? And so we just solve. And so again, this is just standard algebraic manipulation. It's just going to be 6 minus 1 times 2, right? Just moving things over to the other side, plus 3 minus 2, and that's going to be x, and that's going to be 11. So if x is 11, then I know that I'll get full even windows and I'll have a output of 6 at the end. I won't have some like decimal essentially. So let's go ahead and compute that. So length is equal to x.shape minus 1. And we're going to do n frames is equal to length minus kernel size plus padding total divided by stride plus 1, so standard formula. And what we're going to do is our ideal length, what it should be to make sure we always have full windows, it'll be math.ceil n frames. So n frames was 5.5. We're rounding it up to 6 minus 1 times stride plus kernel size minus padding total. And so we're going to return the ideal length minus the length, because the ideal length is 11. The original length was 10. And so if I just added one more padding to the 10 to become 11, I will have everything be solved out for me and we're good to go. And remember, this kernel size is again dependent on the effective kernel size, not really the actual kernel size that we set, but the effective kernel size if we have dilated convolutions. And that's it, right? Nothing too crazy. So that is our extra padding. And this is going to be our get extra padding for conv1d, x kernel size, self.stride, padding total, and I think that's it. Okay. Now we actually need to add so we've computed some padding. We have the padding total, and padding total is just going to get split. Remember, it's the total padding on both sides of our signal. So our padding right is going to be equal to the padding total divided by 2, and padding left is going to be our padding total minus the padding right, just in case, it's an odd number for the padding instead of even. So there we go. And now we need to actually apply this padding here. And we could just use f.pad, and that would be fine. But there is a small exception we need to handle. And so this is what the pad1d is. This exception really doesn't matter, but I want to keep the code as similar as possible to the source. So we're going to keep it that way. The reason it doesn't matter is as long as your audio is long enough, then this doesn't really apply. So the problem is this. There are different kinds of padding. Like if we have 1, 2, 1, 2, 3, 4, we can do 0 padding. So we could add 0, 0, and 0, 0, and that's 0 padding. If we have total padding of 4, just say, add 2 to the left, 2 to the right, there we go, 0 padding. There's also a thing called reflect padding where we do 1, 2. Basically, we just take the signal and just reflect it back in this way. So basically, if we have 2 here, then look 2 forward and then copy them reflected back. If we want 2 here, look 2 backward, copy them reflected back. But what if our signal was this, 1, 2, 3, and we want 5 padding, let's say. We want 5 padding on the right side and the left side, whatever it may be. Let's say the right side for now. We want 5 padding, but we only have 3 values here, so I can't really reflect this, right? I mean, it'll go 3, 2, 1, but then what do I put here? And that's basically the problem. And so the way we handle this is we essentially just add some zeros. We're going to pad it to 0 so it is long enough. And then we can reflect back whatever we need afterwards. So that's the only exception that we need to handle for reflect padding. In the case that our signal is not long enough, we need to add in some extra 0 padding before that reflection. So we're going to do length is that, and we're going to do padding left and the padding right. Right is equal to padding. So padding will be passed in as a tuple as left, right. If mode is equal to reflect, only then do we really have to handle this condition. Otherwise, we can just return f.pad x paddings mode value. Paddings. Okay, so yeah, if we're not doing reflect, then there's nothing to really do. If we are doing reflect, then we just have to do this quick check. So max pad is going to be max padding left, padding right. So what's the maximum that we're going to be padding? Extra pad by default is just 0. We don't have to do anything. But if the length of the signal is less than or equal to the max pad, that means we actually can't do reflect padding. So we have to do extra pad is going to be max pad minus length plus 1. So basically, how many samples do we need to add on so we can actually do the reflection? And then we're going to just go ahead and do x is f.pad x, and we're just going to add some extra pad onto the end of the signal of 0. Just add on a couple zeros and go from there. And then our padded is going to be f.pad x paddings mode value. Yes. Okay. Yeah. Okay, good. So we go ahead and we do that, and we go ahead and then actually apply the padding, the reflect padding. Now, because we added some extra time steps into our thing, our reflection will end up being longer than we intended it to be, and so we need to go ahead and clip it. So our end is going to be the padded.shape minus 1 minus the extra pad, the extra stuff we added on, and then we can do return padded ... up to the end, and that's it. So it's just a quick trick. Just go ahead and just if we don't have enough, 0 pad it, do the reflection, and then clip off the extra stuff, and we're done. This, again, as long as our signals are sufficiently long enough, this is not really a condition we care about, but it's there. In the same way, unpad 1D is just going to take a signal that has a padding left, padding right. It's going to be equal to paddings. And then our final end is going to be x.shape minus 1 minus the padding on the right. And then we can return x, ignore all the other dimensions. And we're going to go from padding left to end. So essentially, given some paddings that we had initially, we want to go ahead and just clip those off based on that. And that's it. So that's unpadding, nothing crazy. So now that we have our padding left and padding right, we can go ahead and do x is going to be that pad 1D method that we just wrote, x padding left, padding right, plus extra padding, of course, right? Just in case we had those. And our mode is equal to self.pad mode. And we're going to return self.conv x. And that's it, right? That is a standard convolution. We just added this extra padding logic just to make sure everything's nice and evenly divisible. But that's essentially it. Our transpose conv is identical. So nothing really new happening. So let's go ahead and put it right here, conv transpose. And we have the padding total. And here is the key idea. So we're going to add the conv transpose in like that. And then we're going to do this using that unpadding here. Now, here's the key idea. In the forward pass, we added 2 kinds of padding. The first one is deterministic. The padding total is dependent only on the configuration of the convolution. On the other hand, this extra padding here is dependent on the length of the input. So when I do the convolution, the forward pass of the convolution, I'll end up with an output. Basically, the input got padded to something and then went through the convolution. That means when I do the transpose convolution to undo that, I need to go ahead and remove that padding, right? Just to essentially just go in the opposite direction. The problem becomes essentially this. because my padding total, I know exactly what the padding total is based on my configuration. And so based on that, there's really no issues, and I can do that. On the other hand, the extra padding I added is just based on the kernel size. So I could either A, go ahead and just return the extra padding here, track them, and then make sure in every corresponding transpose that we have that we go ahead and remove them, and that just sounds like a lot of work. So for simplicity, what we're going to do is we're going to remove the padding that we know in the backward pass. That's what this is. In the transpose method. That's what this is. Go ahead and just compute the padding total based on the configuration that we set, and basically every conv1d will have its corresponding reverse transpose conv1d. Go ahead and remove the padding we do know, the deterministic one. This little bit of extra padding that we may have added doesn't really affect anything. It just makes sure that we complete the window. And so whether or not we remove that or not remove that now doesn't matter. So what we're going to do is at the very end of the model, we'll verify the input length and output length and remove it then. So for now, let's not worry about this. We are essentially just removing this. So again, in the convolution, we added some padding and then did the convolution. That means in the transpose convolution, we're going to transpose it, putting us back at the original shape. And then we're going to go ahead and remove that padding, at least the deterministic padding. To test this out real quick, let's go ahead and run a quick test here. So what we're going to do is I'm going to pass in a signal of length 100 with some 16 channels. And I would expect that if I apply a convolution to it with the stride of 2, this should go down to 50. But then if I apply a transpose convolution to it again with the stride of 2, it should be upsampled back to 100 because the stride controls the length, right? With what ratio the lengths of these things are changed. So let's go ahead and run that. And we see exactly that. We go from 16 channels to 32 channels and then 32 channels back to 16 channels. So there we go. And then we go from 100 to 50 and then 50 back to 100. And that's it. That is our convolutions. So now that we've got this first part done, let's go ahead and revisit the architecture real quick just to make sure we are on track on terms of details. So we've implemented the convolutions, not the conv blocks. We'll do that in a second. And we've implemented these transpose convolutions, not the blocks. We'll do that in a second. What we haven't done is this little part right here. These are LSTMs. It's a standard LSTM. In the original EnCodec architecture, these are going to be your standard these are going to be your standard single direction LSTM, so essentially causal LSTMs. But in our case, we're going to be doing a bidirectional one as an option because more modern architectures like the speech tokenizer use bidirectional ones. Of course, if it's bidirectional, we can no longer make this a streaming model, but that's okay. We weren't planning on doing that anyway, so this doesn't really change anything. So we're going to implement that right here. This is a very simple layer. Import torch.nn as nn, it's class slstm nn.module def init self dimension of the thing num layers is 2, bidirectional is true by default, and skip. Do we want to skip connection here? Also, true or false. Super.init. So what we're going to do is self.lstm is standard nn.lstm. It's going to go from dimension to dimension. The hidden size will be just the same thing. Our num layers is going to be the num layers. Our bidirectional is going to be bidirectional. And by default, I'm going to say the batch first is false. And that just changes how we do the shapes. So we're going to do if bidirectional. Remember, if we do bidirectional, the output of an LSTM is going to be 2 times the hidden dimension. And so we just want to make sure everything is, if it's single dimension, if we do non-bidirectional, so causal, then the output is just dimension. If it's bidirectional, it'll be 2 times dimension. So if it is bidirectional, we just need to project it back. So self.proj is going to be nn.linear dimension times 2 to dimension. Else self.proj, there's nothing to do. We can do nn.identity just to make sure dimensions don't change. And self.skip is skip def forward self x, and this is going to be x is going to be x.permute 2 0 1, because remember our data is going to come in the shape of batch by channels by length, and I want I want length by batch by channels. And the reason I have length first rather than batch first is because batch first is false here. If I had batch first is true, then I'd want it to be batch by length by channels. So there we go. I've permuted it so it's 2, 0, 1, right? So we have the dimensions correct. Then y, and then of course we are going to get our hidden and self states that we don't care about. It's going to be self.lstm, x, pass it through. Y is going to be equal to self.proj, x, just in case we need to do that to get the dimensionality to stay the same. If self.skip, if we want to skip connection, then y equals y plus x, standard skip connection. And y is equal to y.permute, 1, 2, 0. Just put it back how we found it and return y. Very simple. Very simple LSTM, just a little wrapper to make LSTMs work well with the typical convolution shape that we're going to be working with for our model. So now we've got all of that, we can go ahead and import all of this stuff that we've written. And it's time to write the actual block. So class SeaNet ResNet block. And actually, let's just go ahead and copy the stuff that's don't want to type. There we go. So it's going to be a ResNet block. There's going to be some input dimension. This block is controlled by, so if I have like 3, 3, 3, 1, and then 1, 1, 2, 1, that means this block is going to have 4 convolutions. The first one having a kernel size of 3 with dilation 1, then kernel size 3, dilation of 1, kernel size 3, dilation 2, kernel size 1, right? You get the idea. So the list here, the length of the list is the number of internal convolutions. The activation function used by the EnCodec is elu. More modern activation functions are probably better. Like snake activation gives an implicit bias to the periodic nature of audio. So that's what the speech tokenizer and like some of the like VQGAN or whatever it was called is using. So there's some other stuff. elu has the alpha parameter that controls basically the the exponential term in elu. And then we have what kind of normalization do we want, its parameters if we have that, what kind of padding do we want. We have compress. The compress is in the hidden dimension. So whatever dimensionality it is, the ResNet is going to take the dimensionality. The very first convolution is going to compress dim to dim divided by whatever compresses, in our case 2. All the other residual convolutions will happen there, and then we project back to dim at the end. So the output of a ResNet block, just to keep in mind, is it never changes the dimensionality. The input dim and the output dim are the same, and it never changes the sequence length either. So that's what we'll be handling now. So our hidden is going to be dim divided by compress, should be divisible, but that's fine. And our activation function is going to be getAttr, nn activation. That's it, right? So from nn, is it nn.elu or glu or relu or any other one that you want. And block is an empty list for I, kernel sizes, dilations, oh, wait, no. Kernel size, dilation, in zip, enumerate. There we go. Kernel sizes, dilations. There we go. So our initial channel, the in channels, is going to be equal to dim if I is 0, because that's what's coming in. But every other convolution afterwards, the in channel will be equal to hidden, right? So else hidden. And for the same reason, out channels is equal to dim if I is equal to len kernel sizes -1. So the final output channel, so if I is len kernel, so basically on the last I, the final output channel should be dim. We want our input has to be dim and the output has to be dim, but everything else internally should be hidden. So essentially it's going to go from dim to hidden, and then if you have more stuff, hidden to hidden, and then again we'll go from hidden back to dim. And so we just need to make sure that initially in channels is dim for the very first one, and out channels is dim for the very last one, and everything else is hidden. So that's how we're grabbing those. After that, we need to actually do our block, which I'm not going to type all this out, so I'm going to just paste it. So our block is going to be that. I don't have this extra stuff for the snake activation, so I'm going to delete it for now. Put a comma. There you go. So it's going to be the activation function plus one of our convolutions with the this pad mode should be equal to pad mode. There we go. So a block with that. So for every single one of these, we're going to do a block. Once we've done all the blocks, then self.block is going to be nn.sequential. Just unpack the list into there so it's easy forward pass. If true skip, so here's a key idea, self.shortcut is equal to nn.identity. So a true skip connection is going to be like x or y is equal to x times some function of x, right? That's, or not x times, sorry, x plus some function of x. That's a standard skip connection. But we can also potentially add a g of x plus f of x, where g of x is a meaningfully simpler function being applied to x, where an f of x is some complex function, like a bunch of residuals or something like that. So if true skip, we're just going to directly add the input to the output, and there's nothing to do. Otherwise, we're just going to add the projection. So self.shortcut is equal to sconv1d from dim to dim. Kernel size is 1. Norm is norm kwargs is going to be norm params, and pad mode is pad mode. So just very simple, just add an extra convolution if we want. And so then our forward method, def forward self x, we're going to return self.shortcut x plus self.block x. And that's essentially it, right? That's a standard residual block. So now that we have that, let's go ahead and write the SeaNet encoder, and then we can essentially just copy paste the decoder because it's going to be the same thing, just backwards. So to do this, I'm going to paste or copy in the initial part. So type all this. So the encoder, again, in channels, we have essentially our model initially is going to go from in channels to n filters, basically that very first convolution. After that, it's going to go through a bunch of convolutions. Each convolution block will have however many residual layers we want. So we'll set that up. So basically how many of these ResNet blocks we wrote up here in each of those. And each of them is going to have some ratio. So what the encoder is going to do is it's going to take audio, downsample by a factor of 2, then 4, then 5, then 8. So we're going to have to reverse this list. And the backward pass, or not the backward pass, in the decoder, it'll be in the correct order. So we'll see that in a second. So that's essentially it. If we're downsampling by a factor of 2, then 4, but then 5, then 8, then we have a total downsampling factor, an effective downsampling factor of 320. And so what we're doing is we're going from 24,000 hertz audio, and we're going to downsample by a factor of 320. This gives us 75. And this is why right here at the beginning, right here, where was it? Right here. The bit rate has 75 samples per second. So initially it was 24,000 samples per second, but we downsample it to a 75 samples per second. Good. So now that we have all that, again, everything else is just the same. Standard ELU, all the stuff from earlier. We have our kernel size that we can set as a parameter, the last kernel size, the residual blocks kernel sizes, the dilation base. We'll see that in a second. And then we have pad mode, true skip. We have an LSTM layer and bidirectional. So we'll have to add all that in. So to do this, very simple. We've saved all of this. Like I mentioned, our ratio, we need to reverse this list because we want to do 2, 4, 5, 8. In the decoder, we're going to have to upsample by 8, then upsample by 5, then upsample by 4, and then upsample by 2. So in the decoder, this doesn't matter, but in the encoder, we just need to switch that list around. And the hop length is exactly that, the overall, the effective downsample. Our activation function is going to be get adder nn activation. We're going to start our multiplication factor off as 1, and our model is going to start off as and I'm going to copy these in because I don't want to type all this. It's going to start off like this. It's going to be a convolution that's going to go from the input channels to n filters times that mult. And mult is right now 1, and we're going to make that, not 1 later. We're going to iterate it. And so then what we're going to do is for I ratio and enumerate self.ratios. So for every single one of them, and for every single one of these ratios, right? So imagine these are essentially, if we have 4 of them here, that means we have 4 blocks of stuff happening. And at the end of every block, we're going to downsample. But before we do the downsample, we can have however many residual layers we want. In this case, n residual layers is 1, but it can be more you have, deeper the model. For j in range, n residual layers, our model, as I'm going to again copy this in, however many of them we want, we're going to have these ResNet blocks over and over again. Each of them is going to have, each of these residual blocks are going to have two convolutions in it. The first one's going to be the residual kernel size with the dilation base to the power j. J is 0 for initially, so it's basically something to the power 0 is just 1. But if we have n residual layers be like 3, then this is going to go up to 4, right? Because in the first iteration, it's going to be 2 to the power 0, then it's going to be 2 to the power 1, then it's going to be 2 to the power 2. So we're going to iteratively increase the dilation for deeper residual layers, essentially giving it a larger context window, right? The effective receptive field just increases faster with dilation increasing. And the last one is just going to have a kernel size of 1 and a dilation of 1. So there's two convolutions, just like we had, right? In this case, it was 3, 1, 1, 1. But here it's set up like this. These are just copying from the implementation. So there's, I'm sure they did some kind of hyperparameter tuning to find out this works out pretty well. That's our model. Of course, after that's done, I'm just going to keep pasting, so I don't have to keep typing these big blocks. After that, after all of these residual layers, we're going to go ahead and add on a activation function. We don't need any of you. And we will have our final convolution. Now, this is going to go from mult to n filters, mult by n filters, mult times n filters, sorry, to mult times n filters times 2. Basically, we're going to double the size of our number of channels, but we're going to downsample by some ratio. And they decided to use a kernel size of ratio times 2. I'm not exactly sure why, but we could technically pick anything we wanted here. So essentially with deeper layers, our basically the more we want to downsample, our kernel size will also increase by that amount. So I guess they just wanted them to be balanced. So the kernel size increases as we increase the downsample ratio, but that's fine. And then we have a stride of ratio. This will ensure that we again downsample by the factor that we specify. And then of course we went from mult by n filters, mult times n filters to mult times n filters times 2. So we need to now update mult to be times equals 2, right? Just update it for the next iteration. And we just repeat that, right? Do that for every single I. Now that we've completed that, so again, for every single one of these, we're going to have a block of residual channels, but residual blocks, followed by a activation and a downsample block. And once all that's done, we can do if LSTM, then we're going to do model plus equals our S LSTM. It's going to take in mult times n filters. That would be the final output. Num layers is LSTM, and bidirectional is going to be LSTM bidirectional. And that's essentially it. Right, so we've added on that LSTM layer. In the original figure, we can see that after, let's go back to that figure, after the LSTM, there's one more convolution, and this convolution is going to project to the dimensionality of the embeddings that we want. So the final embeddings that pass out at every time step, what's the dimensionality we want? That's also a hyperparameter, of course, and we set that up here, right? The dimension that we want of the final output embeddings. In our case, it's 128. And so that's, again, so I don't have to type all these blocks out. It's going to be the activation. It's going to be an activation followed by another convolution that's going to output to dimension with the last kernel size, whatever it's set to. And so our self.model is going to be nn.sequential pass in model. And then our forward method is going to be self x return self.model x. And that's it. That is our SeaNet encoder. The decoder is identical. Absolutely nothing changes. It's just the same thing in backwards mode. So I'm just going to paste it in because I don't need to type all that again, and I'll just walk you through it. So the decoder has all of the same configurations because we want them to be essentially, reflections of each other, right? And with all of that, we're going to have not this. We don't care about that. And we have everything the same. Again, we don't need to reverse the ratios anymore because in the encoder, we downsample by a factor of 2, 4, then 5, and 8. That means in the decoder, we want to upsample by first a factor of 8, then 5, then 4, then 2. In the encoder, the last thing we did, so we had a convolution, we had an LSTM followed by a convolution. That was the last couple things that we did. So in the decoder, we're going to have a convolution, then the LSTM right at the beginning. And we see that right here as well. We can see the decoder does a convolution followed by the LSTM, just to keep that mirror image, essentially. And then and I can delete you, don't have that. for every single one of them, these blocks are identical. It's just we're doing transpose convolutions instead. So first we do the activation and the convolution, transpose convolution, followed by a bunch of those residual blocks. And then instead of multiplying by 2, we divide by 2. And then we go ahead and apply a final convolution right here back to the number of output channels. So in our case, channels is 1. So whatever it is, that's what it is. And then optionally, we can add a final activation like 10H. And, you can try this out. I didn't, and it didn't seem to affect anything. So essentially, our audio, for example, the waveforms, the generated waveforms should be between -1 and 1, right? That's the range of audio in the way that we're going to set it up. So technically, we could add a 10H function here because we want the output of the model to be between -1 and 1. So why not do that? So you can test it out. In the original paper, they don't do that because the model ends up learning that distribution. It ends up learning that everything should be between -1 and 1, and we can just clip any value that's minorly above or below that. So it shouldn't be any issues. And then we pass it through the model. Again, we pass in Z here because we're passing in the latent vectors, right? And so with all of this, we have everything we need to just run a quick test here, right? So basically with this encoder decoder, I have 24,000. This 24,000 should be downsampled to a factor of 75 and then upsampled back to 24,000. As long as that's true, we are good to go. Not the conv, we're going to do SeaNet. Okay, looks like I have a bug. List object cannot be interpreted as a integer. So let's see here. This method right here, kernel sizes, where are we looking? Oh, I think it was up here. Here we go. So in kernel size dilation, in kernel sizes and dilation, so what's the issue? It's saying that a list object cannot be interpreted as a integer. Oh, my bad. This should be enumerate zip. There you go. Got it flipped. My bad. Now let's check. Okay. Looks like we have another bug. Now it's going to be in the model itself, in the forward call. What are we looking at? By 1024 by 512. So this could be an issue in module.py. No, that's not me. In SeaNet self.model. Why? Okay, in the projection. So let's go double check right here. LSTM. Print. Here, let's do it right here. So it's right here's the issue. So print x.shape and self.proj. Double check. So x.shape is 75 by 1 by 512, but it's expecting 1024 to 512. So what happened? I have bidirectional as true here, and our dimension, let's see, we have 512 as a dimension, so 1024 is indeed correct. Okay. Oh, that should be y. My bad, right? So we produced a y, we have a y. There we go. My bad. All right, so we go from 24,000 down to 128 channels by 75, and we go from 1 back to 24,000, and there we go. So that's everything we wanted, right? That is literally everything we needed this to do, and we are now done with the encoder, the decoder, basically the entire SeaNet model. And we now have to do the middle part, right? The quantizer, right? So that's what we will be working on next. So now that we've completed the encoder and decoder portions of our EnCodec, basically the SeaNet architecture, we need to go ahead and write the residual vector quantization. But before we get to RVQ, we actually need to write a single quantizer, and then RVQ essentially just applies them to deeper and deeper layers. And we'll see all of those details when we get there. To do quantization, again, remember the difference between what we had seen in the VQ VAE tutorial I have, where we use the commitment and codebook loss, we now will be using standard EMA, exponential moving averages, and this is kind of the setup for it. We'll see this formulation as we get closer and closer to that point. But let's go ahead and just set this up of how we do this step by step. Of course, when we do k-means, we need to initialize the code vectors with something reasonable. And there's all sorts of, whenever you do quantization, we need to initialize these code vectors in some reasonable way. And there's all sorts of ways we can do that. And k-means is essentially one of the methods that we can do. So on the very first batch of data that the model gets, we can go ahead and initialize our code vectors with the standard k-means algorithm. So let's go ahead and actually implement k-means, and then we'll see how this all starts to come together piece by piece. So let's go ahead here to do k-means, and I will move this right here. There we go. All right. So to do k-means, we need to actually write the k-means algorithm. K-means, you should be already comfortable with it. It's a very simple iterative algorithm where you just keep trying different points and you iteratively find cluster centers and just kind of move the centers in those directions. To do this, we're going to need a couple of things. So I'm going to paste all of my imports right here. We'll see all of those being used later. And for now, we need to write standard k-means. So we're going to do k-means. And basically, given some samples and however many clusters, which is our k essentially, and some number of iterations, let's go ahead and do k-means algorithms. The k-means algorithms is relatively straightforward. Let's create a test case here. Test k-means. And to do this, we're going to import matplotlib.pyplot as plt. And we will create some true centers. So I just want to create a synthetic data set to do our k-means clustering on. So I'm just going to paste this stuff because it's not that interesting. There we go. So basically, I pick some cluster centers. I say how many samples I want per cluster center. The dimensionality, I'm doing 2, so I can actually plot them. And then I have my, for every single center, go ahead and just add, some noise to it, essentially. Create those points, combine those clusters together. And if we look at our figure, right, so what it looks like, we can do plt.scatter, very simple. And then we can do plt.show. So let's just take a look at that. So we need to actually run test k-means Python conda activate torch Python m modules dot quantizer. It should make a very simple plot matplotlib. Oh, did I misspell? Matplotlib dot pyplot. Oops. There we go. So what I've done is I have my kind of, data here. And what I want to find are the cluster centers for this data. So let's go ahead and get started to see how we can do that. Don't close that. I just need to close you. Okay, so this k-means algorithm is going to essentially do that. So we're going to apply our k-means algorithm to this specific data set. Now, I already know ahead of time that this, of course, has 3 clusters because that's how I constructed it. So let's go ahead and try this. I'm going to not print this out for now. We will comment you out just so we don't have to print it over and over again. And we will have our means, which will be the cluster center, and the bins, which will be the number of points assigned per cluster. We'll see that later, is equal to k-means. And we're going to apply it on the samples. I have k of 3, number of clusters is 3. I'm going to say num iters is 20. So for 20 iterations, go ahead and apply k-means, because again, it's an iterative algorithm. So let's go ahead and now write our k-means algorithm. This is relatively straightforward. So as we can tell, our samples comes in the shape of n by dimensionality, right? That's all it is. Our num clusters is just 3, or just some integer, and num iters is just how many iterations of this k-means do we want to apply. And so our dim is going to be equal to samples.shape minus 1. Our dtype is equal to samples.dtype, just so we can keep all that the same. And we need to just start somewhere for our k-means. Like, we need to start with some cluster centers and go from there. And it's kind of up to us how we want to do it. In k-means, you have standard just random sample something, or there's k-means plus plus, so you can do it that way. In the implementation, they end up picking just, essentially, if we have 100 samples, let's say n is 100, if we have 100 samples and I want 3 clusters, then just go ahead and pick 3 samples randomly from here and just treat those as our initial starting point for the cluster. So of course, there's plenty of right ways to do this. It doesn't really matter. So we're going to have to write a new method called sample vectors. We pass it in some samples, which is n by dim, and the number of things we want to random sample from. And this is pretty simple. So num samples is going to be samples.shape 0. So that's our n essentially. And then we have our device is going to be samples.device. And we're going to do if num samples greater than num. So here's our two cases, else pass. If we have 1,000 samples, let's say 1,000, and we only want to sample 3 things from it, we're kind of fine. Just random sample 3 things from the 1,000 and we're done. And we can do indices, just basically between 0 and 999 for 1,000 things, indices. Just go ahead and do torch.rand perm. It'll basically random sort all the values from 0 to 999, in our case, up to num samples. Make sure it's on the right device is device. And then just select the first however many indexes we want. And we can then return samples indices. No problem there. Now, for the other case, if our number of samples is less, let's say we only have 5 samples, but we wanted 10 clusters, then when we random sample, we need to repeat some of them, right? Because we don't have enough to get to 10, so this is just a case that we need to handle. So indices is equal to torch.rand int 0 to num samples, num device equals device. So this is going to random sample numbers from 0 to 10, but let's say 15 times. And so of course some of those indexes will be repeated in that case. This is totally fine. This really isn't a case that should be running for us because as long as our batch size is sufficiently large enough, then we should have enough samples for the number of cluster centers that we need. So again, this shouldn't really be an issue, but it's there just in case. Now we have our means. And so the means will simply be our sample vectors from samples and num clusters, right? So go ahead and just select num clusters, in our case 3, of our original data to act as our starting point for the center. So we haven't done any kind of update rule yet, but this is fine. And so now what we're going to do is let's go ahead and just print out the means real quick. And we should see that basically these 3 samples were randomly selected to be our thing. And I'm going to return means and none. So I'm going to, just none for now, just so it doesn't keep throwing that error. And there we go. And so of course, if we try to, this is just a random guess, right? So let me add in the other line to plot our cluster centers, just so that's also there. There we go. If we try to run this right now, we'll essentially get our starting point, right? So this is how we initialized our cluster centers. And we're hoping with enough iterations that we'll actually, get true cluster centers. This is just our start. Good. So I'll comment this back out again. Don't need you. Okay. So let's do the standard K-means algorithm. There's nothing fancy. So the K-means algorithm, as a quick recap, is essentially for every single cluster center, find all the points in the data that are closest to it, and then take the average of those closest points to compute our new cluster center. And it's as simple as that. So we're going to do for blank in range num iters, right? So however many iterations we want to do this for. We need to basically find the pairwise distance between every sample and every cluster. So right now, we need to create samples, which is currently n by dim. We're going to make it n by 1 by dim. Just add in an extra dimension. In the same way, our means, our current cluster centers, are, I'm going to call this k for num clusters by dim. And we need to make it 1 by k by dim. So add in those extra dimensions. So let's do that. So samples means is equal to samples dot unsqueeze 1, and then means dot unsqueeze 0. That goes ahead and just adds those extra dimensions in. And now what we're going to do is compute something called diffs. And this is going to be samples minus means. And so what we've done here is essentially samples will be n by 1 by dim minus a 1 by k by dim, and this will give us a n by k by dim. Basically the pairwise difference. We have the difference for every single n and every single k, because this n will broadcast along this dimension and this k will broadcast along this dimension. So we get the pairwise differences. Now, if we just do one of them, let's say that it was a, b, c minus d, e, f. Let's say this is one of the vectors in n and this is one of the vectors in k. Well, this will give us a minus b, or a minus d, b minus e, and then c minus f. But this is just the difference, right? This is just the difference. But this is not how we compute something like the Euclidean distance. The Euclidean distance would square, right? Square each of these terms. So I'll just add them in. Square. And one more. Square. That's the Euclidean distance. And then we just sum them together because that's exactly how the Euclidean distance works. So this samples minus means is just a minus d, b minus e, c minus f. So we need to actually compute the distances now. So our dists is going to be the diffs squared. So that's going to do element-wise squaring of everything. Dot sum dim equals minus 1. So this is going to be now in the shape of n by k. So let's go ahead and check that out. Print dists. Take a look. We can see we have basically let's throw a break in here so we don't do it for every iteration. So that's our data. So we have essentially for every single sample, we have its distance away from cluster 0, cluster 1, cluster 2. Distance away from cluster 0, cluster 1, cluster 2, cluster 0, cluster 1, cluster 2, ... And we just do that for all of them. Good. And of course, what we need now, let's put that back, is not the distance away, but rather this specific sample is closest to which of the clusters? Well, this is closest to cluster 0. This sample is, this sample is closest to cluster 2 because this is the smallest one. This sample is closest to cluster 2, so on and so forth. This sample right here is closest to cluster 1 because we can see it's the smallest one there. And so that's how we're going to do it. Basically, what is the closest one to it? Now, we could just do min and that would be fine, argmin essentially. But in the implementation, just to stick true to it, they don't use min, they actually use max. So instead of finding the smallest distance, we find the largest negative distance, which is the same thing, right? Finding the smallest of something is the same as finding the biggest negative something. It doesn't really change anything. I just want to stick to their implementation. So we now create something called buckets. And this is going to be dists.max along the last dimension dot indices. And if we print out buckets, we'll see that we have basically which cluster center, there's 3 of them, so 0, 1, 2, which cluster center was each of these samples assigned to, and those are my buckets. Now that we have the buckets, we also need to know is this part here. So I know that this specific cluster center was assigned to these samples, and this specific cluster center was these samples, this one was assigned to these samples, but what I really want to know is the n. How many samples were they assigned to? Like, what's the number of them, essentially? So we can quickly compute that using bin count. So we can do bins is equal to torch.bin count buckets, and we pass in the min length is going to be num clusters, right? Because that's the max that it can be. So print bins, and we'll get something like this now. So each of these were assigned to 300. Our random sampling is pretty easy, but we can run at different times, and you can see that cluster 0 was assigned 394 things, cluster 1 was assigned this many things, cluster 2 was assigned that many things, so on and so forth. And so that's our n. That's exactly what these are. How many were they assigned to? Now that we have that, we have our bins. We could have a condition. So later on, when we actually want to compute the cluster center, what we do is we add up the embeddings of the corresponding cluster. So basically this cluster is assigned to these embeddings. So let's add them all together and then divide by n. So it's basically this. So the m is the sum of all the assigned cluster embeddings divided by the number of cluster embeddings that it was assigned to. So simple average. Of course, when we try to do that, if for some reason a cluster center has 0 here, then we'd have a divide by 0 error. So we need to just handle that exception really quick. So we're going to do a 0 mask is going to be bins is 0, and then bins min clamped is going to be bins.masked fill 0 mask, and just fill it with 1, because we'll just divide by 1 so we don't have that divide by 0 error. And now it's time to go ahead and update our means. Our mean, the new means, is going to be essentially what is the average of the assigned cluster, the assigned embeddings to every single cluster. So to every cluster center. So if these are all selected for this one, then go ahead and take the average, and that's how we're going to update it, right? Standard update rule. So to do this, we're going to create a new tensor called new means. It's going to be buckets dot new zeros num clusters dim dtype equals dtype. And then all we need to do is just loop through. So there's actually 2 ways we can do this. So this is basically an accumulator. And what it is for every single cluster, we have some dimensionality of dim. And so what we're going to do is for every single cluster, we're going to loop through all of the samples, find which cluster was each of the samples assigned to, and then take that embedding and then add it into the corresponding index of our accumulator. So what this will look like is essentially this. For I in range n, and so n in this case, let's just do it, n is equal to, let's see, it will be len of samples, right? So however many samples we have. For I in range n, we're going to do our cluster is equal to buckets I. So basically, in this specific sample was assigned, the buckets tell me which cluster center this sample is assigned to. Whichever one it was assigned to is my cluster. So that's the cluster that I want. And then what I'm going to do is inside my new means, at the index of that cluster, I'm going to add in that sample, that specific sample. And this will go ahead and compute my new means. It should be pretty straightforward. So there we go. We just accumulated all of them up. And then after that, we need to just go ahead and divide each one of these, right? Divide each one of these cluster centers by our the number. So that's our bins, right? So we just divide by bins and we'll be done. This is a completely valid way of doing it, and we could have left it this way. But in the implementation, they do it slightly differently. So I'm just going to talk about it that way just to make sure it's exactly the same as much as possible. So we're going to do new means, or actually what we're going to do is we're going to do repeated buckets. So let's print out buckets again, just so we can compare them, and then print, and then our repeated buckets is going to be our buckets dot unsqueeze -1 dot repeat 1 dim repeated buckets. And I'm going to comment you out. So all we've done is we took this and just copied it twice and made 2 columns. So now it's a n by 2 thing. So it's basically number of samples by a dimensionality of 2, because that's the embedding dim, and that's it. And by doing it this way, we can now use scatter operations. So we can do basically sparse operations like new means dot scatter add dim equals 0, index is repeated buckets, and source equals samples. So samples is a n by 2 tensor. That's what it is. And it's basically saying along these indexes here, 1, 2, 0, whatever they may be, they refer to the 0th dimension of new means, which is num clusters, because num clusters goes from 0 to 2. So these indexes go from 0 to 2. And all I want to do is just add them together in this way. So this is saying this first sample is 1, 1. So just go ahead and grab this specific sample at these indexes and add it to the 1, 1 index in my new means. This is just a simple scatter operation. There's nothing, so you can read about scatter and gather and stuff like that. This is exactly the same thing as that for loop that we had from earlier. It doesn't really matter. This is just slightly more efficient, I guess, so that's fine. New means is then going to be new means divided by bins min clamped, right? Could divide by bins. And we have to add that extra dimension in, just so, remember, this is basically just a vector. So we need to add that extra because this is a n by dim. So we need this to be basically we need to have that extra one dimension at the end. Otherwise, we don't have enough dimensions. It'll throw an error, so we just add the dimension in. And now we have our new means. And there we go. So these are my newly computed cluster centers. And of course, we do need to kind of adjust for something. When we had our empty clusters, we need to just make sure that empty clusters aren't actually updated. So if a cluster is divided by, it had nothing assigned to it, we technically is divided by 1, and this is technically incorrect. So what we're going to do is our means is going to be torch.where 0 mass dot, again, just add that extra dimension in just so we have 2 dimensions for n and dim, means, new means. So just go ahead, wherever our 0 mask is true, go ahead and use the means, or sorry, wherever it's false, then go ahead and keep the means for the samples where, keep the means. Yeah, so all we're doing is for empty clusters, right, where it was 0, where the mask is true, just go ahead and use the old mean, and for the non-empty clusters, actually update them, and that's it. And we can now print means. There we go. Those are updated. In this case, we didn't really have anything, so it's fine. So, and we're going to return both the means and the bins. There we go. So let's plot out our K-means algorithm, right? So see where the cluster centers kind of end up, and there we go. We have 3 nice cluster centers for our data. And we're done, right? So that's standard K-means. And again, the K-means algorithm is only used once for the initialization of our code vectors. You can do this however you want. There's all sorts of initialization methods. They just use K-means because it already gets the code vectors like nicely centralized on different clusters and things like that. And these don't really matter because, of course, on the very first batch, the model doesn't know anything. So these embeddings just don't really mean anything. But it's a good initialization point, essentially, and we're good to go. And this step right here, just to make it clear, this new means divided by bins mean clamped was exactly what we have right here, right? Basically the sum of everything divided by the number, which was in our bins. Okay, so now that we have done our K-means, let's go ahead and write a couple of other helper methods. So we need EMA, I'm going to call it they call it in place, so we're going to do the same thing, moving average, our new, and decay. Remember that EMA updates, we are going to be using exponential moving. Now that our code vectors are essentially initialized, every subsequent batch, we're going to compute new m and n, and then we want to use EMA updates to go ahead and actually update the code vectors. And so to do this, we're going to use this update rule, essentially. It looks scary, but it's basically the old n times gamma plus 1 minus gamma times the new n, and the old sum times gamma plus 1 minus gamma times the new sum, and it's as simple as that. And so to do this, we need to be able to actually, perform this operation of gamma times n plus 1 minus gamma times the new thing. And so that's what it is. The moving average is my existing value, so that's like this one right here. And then gamma is my decay, and then plus 1 minus gamma, and then nk in this case, or this term right here, those are the new values. And so that's moving average, new, decay. And all we're going to do is moving average dot data dot mul. Then we're doing this in place for efficiency, so decay. So multiplied by decay, and then add to it our new value multiplied by, and we can use alpha here, 1 minus decay. And so this is the equivalent of just doing our moving average is equal to moving average times gamma plus 1 minus gamma times new. And so this alpha term basically says before we do the add, multiply by 1 minus gamma or 1 minus decay, and then do the add. And because it's an in-place operation, there's really nothing to return, right? Because it's going to update moving average directly. There's nothing to do there. We also need to do something called Laplace smoothing. So Laplace smoothing. This is, if you haven't ever heard of Laplace smoothing, it's also typically called additive smoothing. So I'll show you categories and categories 1e minus 5. I'll pull up a quick visual on that. So Laplace smoothing is pretty straightforward. So it's called additive smoothing or Laplace smoothing or Lidstone. I've never heard of that before. Or heard it called that before. But it's a technique to smooth count data, eliminating issues caused by certain values to have 0 occurrences. And so basically, if you have some number of observations from some d-dimensional whatever, all we're going to do is take some x, add some small epsilon term to it. But this means we're adding to every single, if there's n possibilities, then we've added essentially some alpha to all n of them. And so we need to make sure we also divide by that as well. And so what we're going to do, that basically just makes sure that the scaling stays the same, right? So we don't change it out. So this is basically a smoothed count. And the smooth count alpha greater than 0 is a smoothing parameter. With alpha equals 0, there's no smoothing at all. So this is a typical trick, and we'll see why this is necessary later. It basically saves us from a divide by 0 error when we're actually updating our model and stuff like that. So we'll see that. But very simply, it's just going to be return. We take x, we add some EPS, but this is going to basically, there's n possible categories, right? Or n classes in our case, or k essentially is what we call it, in the k code vectors. There's n possibilities, and so we're adding EPS, a small, tiny little EPS for all of those categories. So to make sure our scaling and stuff stays the same, we're going to do x.sum in the denominator plus n categories times EPS. So this is basically very simple. If this is 0, if EPS is 0, then really we just added 0 and then divided by just the sum. And so nothing really would change, right? So there we go. It's just a small smoothing term. This just makes sure that if there's any zeros in x, we add some tiny little 1e minus 5 to it. So it's no longer 0. And that's it. Okay. So now that we have that, we also need a quick helper method, uniform init. So given some shape, all we need to do is just return. So t is going to be some torch.empty shape, and then nn.init.KMeans uniform t, just initialize it and then return t. So it just gives us quick uniform initialization, and I believe that's it in terms of that. Okay, good. So we have our initialization, we have our k-means. Now we go on to actually write the code book, and this is where it starts to get a little bit more challenging, but we will work through it just fine. So new class, Euclidean. Oh my god, I spelled that wrong. Okay, 1 second. EuclideanCodebook. I'm missing an I. Yeah. Okay. There we go. nn dot module. Definite. And so this code book, this is going to be one of the code books in our residual factor quantizer, but for now we have this code book. It's going to have, let's just do the standard self. It's going to have some dimensionality. The codebook size, how many codes are in them. We'll have k-means init, true or false, whatever you want. K-means, if we're doing k-means initialization, then we need how many iters we need. K-means iters, we'll set it to 50. We have our decay factor, 0.99. This will be for the EMA decay, so we'll see that. We have our epsilon is going to be 1e minus 5. We have our threshold, EMA, dead code. So this is extremely important. We'll talk about it in just a second. And then accelerator is none. So the accelerator, remember, whenever you write accelerate code, we're going to do like accelerator is equal to accelerator later on when we write our training loop. This accelerator contains all of the information about the distributed system that we're training on, right? How many GPUs we have, the ability to like gather stuff, all that information. And so we're going to pass this in to here so we can access the distributed variable stuff, the distributed systems information inside this class, because we're going to need to do that. And we'll kind of see those details in just a bit. And yeah, we'll talk about the dead code in just a second. That's fine. So all we're going to do is store all of this right here. There you go. K-means iter. And, oh, I spelled it wrong in my actual code. Okay, that's fine. I'll fix that later. Spelling doesn't matter. Okay, so first off, we need to initialize. So our init function is going to be the uniform init, if not k-means init, else torch.zeros. And so our embedding is going to be equal to init function codebook size, and dim. So this will go ahead and actually initialize our embeddings for us, either using uniform init or just as zeros for now, and then we'll actually, populate them when we do the forward pass, the very first batch. So we'll see that in play. So if we're doing uniform, initialize uniformly. If we're not doing uniform and doing k-means, just initialize as zeros, and we're going to populate those later. So we'll see that. And now what we're going to do is save all of this stuff. And this is where it becomes really important. These parameters, like the codebook of this model, are not trainable parameters in the sense that there's gradients. There are no gradients. We're going to be updating them with EMA updates. So no gradient necessary, which means we don't need to do nn.parameter. I mean, we could, but there's no need to. So instead, we're going to save them as buffers just to keep it the same as, so register buffer. Basically, it'll be treated as something important to the model, and that should be fine. So register buffer, we're going to do initted. It's going to be torch.tensor, not k-means init. So this is going to be a flag, basically a single tensor with a single true-false value in it saying, has this thing been initialized or not? If we initialize with uniform, then yeah, it's been initialized and we're done. If it's been initialized with k-means, we actually haven't initialized with k-means yet. We've just set it to zeros. And so that's why it's just that, not k. And then we're going to do self.register buffer. We need to store some additional metadata, so cluster size, torch.zeros, codebook size. Just go ahead and save that. So this is going to say how many samples are assigned to each cluster, question mark. Well, in this case, we haven't done anything yet, so we're just going to initialize them as zeros, right? So for every single one of the codes, how many samples are assigned to this cluster, we don't know yet because we haven't done it yet. So we just initialize to zeros, then we're going to do self.register buffer. We have our embeds, the actual embeddings. We're just going to store the embed in there. And then self.register buffer. We have our embed average. This is the moving average thing that we're going to be updating. For now, it's going to be embed. And we're just going to clone it, and we're good to go. And so yeah, since they're storing as parameters, we're going to store them as buffers because they're not really trainable. So there's no need to, I mean, we could store them as parameters and then do like set them to no grad, like torch.no grad by default, but this is kind of equivalent to doing that. So it doesn't matter. You can do it how you want. I'm going to create a quick, so this is where it starts to differentiate from the original implementation a little bit because I need to handle all the distributed stuff with accelerate. So this is going to be a quick flag to check, is something distributed? And we're going to return self.accelerator is not none, so it has to be none, and self.accelerator.num processes greater than 1. So accelerator, if we don't pass in an accelerator, then it's not distributed. And if we do pass in an accelerator, then the number of processes has to be more than 1, where num processes is the number of GPUs we're using. And here is the other thing. Remember that when I do stuff on the GPU, on multiple GPUs, all of this stuff is going to be created per GPU. Like every GPU will have their own. But of course, we don't really want that. We need to, if we have multiple GPUs here, we need to synchronize stuff across GPUs. And what that really means is we need to do something called broadcasting. Broadcasting is essentially just go ahead and take variable values from one GPU and just copy them into all the other GPUs. So like if N01 is set as 12 here, and I copy it over to GP1, then N01 here should also be 12. And so that's just our copy. It's just a copy method. This is very simple. Accelerate makes this very simple. So does Torch. We could have also done this in Torch, but broadcast buffers. So basically all these buffers are the stuff we care about. So let's go ahead and make sure we have the method to copy them over. So we're going to do if not self.isDistributed. So if we're not distributed, then we just return. There's nothing to do. And otherwise, you do for buffer in self.buffers. So these are the 4 things stored as buffers. Go ahead and just copy them over. We're going to do buffer.data, the actual, underlying data, is going to be accelerate.utils.broadcast. And we're going to do buffer.data from process equals 0. We're always going to copy from the main GPU. In our case, it's GPU 0. And that's it. It's as simple as that. Basically, this is the copy method. Basically, .data accesses the actual data attribute of this specific tensor. And all we're doing is taking any GPU's buffer.data, so basically this specific variable on all GPUs, are replaced by the value of buffer.data on the 0th, our main GPU. Oh, on our main GPU. There we go. All right. So now that we have all of that set up, let's go ahead and write the first method, def init embed. Oh, def init embed self data. So we need to be able to initialize our embeddings. They add an extra, this doesn't really matter, but technically we don't need this to be compiled, so we can do torch.jit.ignore. So if you do like torch compile or torch script or anything, this doesn't compile because it doesn't matter. This initialization only occurs once. Remember, the KMeans initialization that we have here only will occur one time. So if basically we have to look in here and check the initted method. If initted is true, that means there's two possibilities. Either we use uniform init and there's nothing to do here, or if we're doing KMeans init, then we've already done KMeans init and this thing will be toggled to true at that point. But right now it's false. So that means right now at the very beginning, if we run if self.initted, this should be false and we can just return. So initially this will be false. We're going to set this to true in just a second at the very end. And what we're going to do now is if self.is distributed. So if we're in distributed, what we need to do is, remember, when we do this stuff, like what we want to do essentially is find the cluster centers for the data across the batch. But unfortunately for us, when we have multiple GPUs, our batch of stuff is kind of across all the GPUs. So what we need to do is copy all the data from all the GPUs onto the main one, do the computation there, and then copy those computed cluster centers back to all the GPUs. And so this is relatively straightforward. What we're going to do is all data is going to be self.accelerator.gather data. So this is going to go ahead and essentially just grab all the data that's sharded across GPUs and put it in one GPU, our main GPU essentially. And gather is actually an all-to-all operation. So basically you can imagine that if we have two GPUs here, if we do gather, all the data from GPU 1 is copied to GPU 0, and all the data from GPU 0 is also copied to GPU 1. So basically all the GPUs have all the data, and they're just concatenated together. So this all data was the original data from both GPUs concatenated together. Very simple. But then technically we only need to do this KMeans initialization on one GPU because that's all we need. So we're going to do self if self.accelerator.is main process. So on the main GPU, we're going to do embed, and cluster size is equal to KMeans all data self.codebook size self.KMeans iters, right? So go ahead and do that. So remember, KMeans is going to take all of that data. How many codes do we want in this thing? So if it's 1024, then it'll do the KMeans algorithm on that. And then we're going to do how many iterations you want, and that's going to return the embeds. These are the actual initialized codebook vectors that we want to start out with. And of course, our cluster size, which is how many samples are assigned to each one of these codebooks, right? That's exactly what we implemented up here, the means and the bins. And so now that we have that, we just need to store all that information. So self.embed.data.copy in place. We can do embed self.embed average.data.copy embed.clone to store a copy of that. And then, because initially the embed and embed average are the same thing, they start out in the same place. And self.cluster size.data.copy cluster size. And there we go. So that's going to go ahead and save these things in those buffers. And what we're going to do is do self.accelerator.wait for everyone. Because remember, when we run this, this is only running on the main GPU. We want all the GPUs to kind of just hang around until the main GPU is done doing this operation. And then we're going to do self.broadcast buffers. This broadcast buffers will then take this information that's been computed on the main GPU and just copy it over to all the other GPUs. So everything is starting from the same embedding, same cluster size, same everything. Otherwise, if we're not distributed, there's really nothing to do. So the code is identical, so we can just paste this in. just go ahead and do exactly the same thing and just copy them. But there's no need to do the accelerator or broadcast or anything because we're only running on one GPU now. Now that our embeds have been properly initialized, we can now do self.initted.data.copy, and we're going to do torch.tensor true, right? We have officially initialized things, so we're good to go. And we need to make sure this is also synchronized across all the GPUs. So we're going to do self if self.is distribute. Technically, this should already be synchronized because it's going to run on every GPU individually, but it's fine. It's just self.initted.data is equal to accelerate.utils.broadcast self.initted.data from process is 0. And that's it. Very simple. So it's just essentially that's our flag. Nothing too crazy has happened. I think this is fine. So that's our initialization. Now that we've initialized, we need to do some other stuff. And so let's kind of talk briefly about the threshold EMA dead code. The idea is this: if there's a code vector that is being unused a lot, and it's basically never being utilized, then it's kind of a waste to have a code vector in our embeddings that are being unused. And so us being able to dynamically replace code vectors that are being unused is an important thing. And we can kind of tell that, right? Because we can look at our cluster size. The cluster size tells us how many samples are assigned to each code vector. If the number of samples assigned to each code vector is like none over and over again, then that essentially means that that code vector is not being used. And so what we're going to do is essentially an EMA update on the cluster size. Just keep track over time. What is the cluster size? And if our cluster size, falls under 2, the kind of the exponential decay or exponential average of the cluster size over time, if it falls under 2, that means this code is barely being used, and we should probably replace it with a new one that's more likely to be used. And so to do this, there's 2 things that we're going to need to do. First, we're going to do def. We're going to write a method to replace things. So self, samples, and mask. And so what we're going to do is our modified codebook is going to be equal to torch.where. And it'll be mask dot, just add in that extra dimension. So just like before, just for that dimension, it's 2 dimensions. So we need to have 2 dimensions in the mask because the mask is just going to be 1 dimension. And we're going to do sample vectors. Just go ahead and resample from samples, self.codebook size, and then self.embed. And that's it, right? So all we're going to do is basically, we want to look at our embeddings, and then for everything that's masked out, so these are the ones selected to be replaced, we're going to go ahead and sample some new vectors from our batch of samples to replace them. And so this is kind of like before, but only instead of kind of initializing everything, we're only going to initialize whatever the mask says true. So for the non-true positions, just go ahead and just stick to a normal embeddings because we don't want to change those. And so then we can do self.embed.data.copy modified codebook. And that's it. So that's our replace method. And so now we can do def expire codes self batch samples. Okay, so what we're going to do is this expire codes method needs to happen again across GPUs and stuff like that. So we're going to implement all of that. So let's first do if self.threshold EMA dead code is 0. If we set this to 0, well, our number of samples assigned to each code can never be less than 0. So there's really nothing to do. So if you set this to 0 here, that disables our codebook's ability to dynamically replace code. So that's why we have it to 2 here. And so there we go. What we're going to do now is expired codes is equal to self.cluster size less than self.threshold EMA dead code. So cluster size, remember, is going to be how many samples are assigned to every single cluster. If we have 3 clusters, let's say we have 14 to the first thing, 25 to the second thing, and 64 to the third thing. And then that's for the first batch. And in the second batch, we could have 22, and then 54, and then 61, ... But instead of just tracking, instead of the cluster size just being like something like this, we're going to do an EMA, essentially, just like before. So it'll be 14 times some gamma plus 1 minus gamma times 22, 25 times some gamma plus 54 times 1 minus gamma, so on and so forth. This way, our self-def cluster size isn't going to be exactly the cluster size for this specific batch, but rather a running average across all the batches, which just gives us a smoother estimate. This means if our model, our cluster sizes are consistently less than 2. So they're being consistently unused, or whatever you say this, whatever this is here, whatever you set this to. If it's consistently less than 2, only then will one of these thresholds drop under 2, like the exponential average. And if it drops under 2, then it falls under an expired code. This is a code that needs to be replaced by something new. And so what we're going to do is first, if not, torch.any expired code. If there's nothing to replace, not self dot, just expired codes. If there's nothing to replace, then we just return there's nothing to do here. But if there is something to replace, now we need to do some work. So we're going to do batch samples. It's going to be exactly the same thing. So remember that our data, we're going to handle this later as well. Our data is going to be batch by length by E, right? This is the typical output of like, how we want it. Batch by sequence length by embed dim. That really means we have batch by L vectors, each of the vectors being of length E. And each of these batch by L will get quantized with some other embedding of length E, right? That's the entire point of this. And so what we need to do is essentially just go from batch by L by E to batch times L by E. And this is essentially the N by dim that we've been looking at earlier, where N is just batch times L, because there's multiple dimensions here. So batch by samples, and so it's going to be inops.rearrange batch samples, and we're going to basically take all the dimensions except for D, and we're going to just group together all dimensions and still have D at the end there. And we're going to do if not self dot is distributed, or self.accelerator.is main process. So if it's not distributed or we're on the main GPU, then we're going to do self.replace, replace batch samples, mask is equal to expired codes. So basically, go ahead and replace, right? Let's recap here. In our codebook, replace the things that are selected to be expired with some new vectors from my batch of samples, from my data. And there we go. That's all. If self.is is distributed, so if we are in distributed mode, then we need to make sure we do self.accelerator.wait for everyone. So of course, when we're doing this, this all is going to happen on the main GPU. And then once this is done, we need to make sure we do, again, if self.is is distributed, just go ahead and do self.embed.data is equal to accelerate.utils.broadcast self.embed.data from process is 0. Go ahead and copy the embeddings over because we updated on the main GPU. We want to make sure it's updated on all the GPUs so they're synchronized, so we don't have things changing between things. We're going to have a quick method here, def process self-x. So this is the exact same thing that I mentioned before. We just want to make sure that we flatten all those extra dimensions. So this is, we could have actually used that right here. That would have been fine. That's fine. Okay, so that's just same reason as before. Now let's go ahead and write our actual quantization method, right? So def quantize. To quantize something, we're going to take self and x, and we're going to do two things. First, we're going to do embed is equal to self.embed.t. So we're going to go from n by e to e by n. That's the transformation we're doing here. And what we need is to compute the distance, between each x and embeddings. So basically, each one of these and each one of our code vectors, we want the pairwise distance. And basically, we know the formula, it's x minus e squared. Well, isn't that really just x squared minus 2xe plus e squared? Right, standard. That's our standard formula. So let's do exactly that. Dist is equal to, it's going to be x.pow 2 x squared, and then we need to sum them up, right? Because we have, we want the Euclidean distance, and this is two-dimensional, so keep dim as true, minus 2 times x at embed, right? So that's how this is going to be set up. So we're basically doing a, x is going to be some like batch times n, whatever it may be, by e, and we're map modeling it with an e by n. So we're doing basically the number of samples in x by number of samples in n. That's what this is going to end up being. And then plus, same thing for the other one, embed.pow 2.sum along the 0th dimension, keep dims is true. So this is just the vectorized form of doing the pairwise distance between every single x and every single embedding. So we could have also done a for loop, but this kind of, with broadcasting, this handles exactly the same thing. And just like we did before, instead of finding the min distance like we do here, we're going to find the max. So we're going to do minus 1 times this, and then just do max again. So embed ind is going to be dist.max dim equals minus 1. What is the largest negative distance, basically the closest distance? Which index is closest? And again, we'll have the dot indices right here to get the indexes. So this is going to tell me for every single sample in x, which is the close, what's the index of the closest code in our set of codebooks. And it's simple as that. And we can then return embed index. Good. So now we can do a little bit of effort here. So, or work. So def post process embedding EMB. This is going to be a quick method that's just going to reshape back to the original input shape. So this is going to take self, embed index and shape, and we're going to return embed index dot reshape, and we just want to have all the shapes from everything except for the last one, right? So this is going to go ahead and just reshape back to the original input shape except for the embedding dimension. There we go. So we'll see that in practice a little bit later, but if our embedding index is essentially, we had to do in this pre-process, we had to do this flattening operation where we kind of took these dimensions and grouped them all together. In this one, we do exactly the same thing, but we essentially ungroup them, right? We ungroup them. So we have all those dimensions separate again. So if we went from, here we had batch by L by E, and this batch by L became batch times L by E. Our embedding indexes here is going to be batch times L, right? Batch times L, because essentially the embedding index is an index for every single sample in batch times L, right? Flattened dimension. What is the closest code vector, code index that goes with it? And we want to go from batch times L back to batch by L. And of course, there's no longer that E dimension from earlier. It's just batch by L. So that's why it's minus 1. We ignore that last dimension, and we just grab all those shapes and we just unpack it, and we're done. And that is our post process. We also need the ability to dequantize self.embed index. So basically, given some indexes, the code indexes, actually grab the corresponding embeddings in our code vector. So we can do return f.embedding, just use the functional form. In the embed, with these embed indexes, grab from self.embed. So it's very simple. Just index the just standard embedding matrix. Because this is an embedding matrix, so given these indexes, grab those embeddings, and we're done. Okay, now we need to def encode self x. And remember, all of this stuff that we're about to do here has no actually, we can write the encode and decode in just a second. So let's do def encode, def decode. These are what we're going to use for inference time. So embed index. We'll write those in just a second. Let's write the actual forward method first. Self x. So given some data, we're going to store shape dtype is equal to x.shape x.dtype. And this forward method will only be used for training purposes, because once we're done with training, then this will update the embedding. We don't want to update anymore. So this is only for training purposes. During inference time, these are the methods we're going to use, and we'll write those in just a second. So first we're going to do x is equal to self.preprocess x. This will go ahead and just prep the data from, again, batch by L by E to batch times L by e to flatten it, because we need essentially two-dimensional stuff to do all the code that we wrote earlier. So we're saying that there's batch times L number of vectors, and each vector has an embedding dimension of e. And now we're going to do self.init embed x. So basically on this data, we're going to initialize. Of course, this will only run for the first forward pass, because in our init embed, we verify. We have this check for if we're already initialized, then don't do anything. If we are not initialized, then go ahead and do the initialization process. So this will only run on the first forward pass, and then after that, it never runs again. Embed ind is going to be self.quantize x. Go ahead and actually quantize the data. So this is going to give us the indexes of each of these batch times L vectors were assigned to these specific embeddings in our basically indexes of our code vectors. But this will be in the shape of batch times L. We would want them to be in the shape of batch by L. So we'll do that in a second. We're going to do our embed one hot. So instead of having this be like 0 to 1 dot dot dot, we're going to have it be 1 1 0 0 0 0 1 0 1 0, right? So we're essentially, instead of storing indexes directly, we're going to store a one hot encoded matrix of the same information. And we can use f dot one hot to get that information. We do embed index self.codebook size. We just have to tell it how many classes there are. And then dot type is going to be the d type of the original data. So there we go. That's our one hot. So if this is of size n, and this essentially stores indexes of, for every single n, which code vector was assigned to, this is going to be of size n by k. Where it's going to be the same thing, but it's going to be 1 in the kth dimension for the k that is its code vector, and then 0 for all the other ones, right? Because one hot encoded. We now need to go ahead and actually get the quantized values. Remember, these are basically what are the indexes that were selected, but we don't actually have the embeddings themselves, so we can grab those. So this is going to be our quantized. Quantized is going to be self.dequantize embed index. So that'll go ahead and actually grab the corresponding embeddings. And now here's the difference. If we're in training mode, now we actually have to do stuff. So if we're not in training, then this quantize is technically all we need. But if we are training, then we have some work. So if self.training, right, the internal flag that all PyTorch modules have, if we're in training mode, we need to do a couple things. We need to first gather the batch samples from all GPUs for our code expiration computation, because what we have essentially is how many times was each of these code vectors used on each GPU. But of course, the number will be different per GPU. We need to gather that information all together and see overall across all the GPUs, how many times was each of these code vectors used, because our batch is split. So we're going to do if self.is distributed batch samples is going to be self.accelerator.gather x. Else batch samples is just x, right? So if we are in distributed mode, then of course we need to grab all of them across all GPUs. If we're not in distributed mode, then it's just x and there's nothing to do, right? And now we're going to do self.expire codes, the method we wrote earlier, on batch samples. So this is going to go ahead and run our expire codes. It's going to check the cluster sizes, and if there are any cluster sizes that are less than 2 in our case, then it's going to go ahead and replace samples in our code vectors, in our codebooks, our embeds, with new vectors from our our batch samples right here. So very simple. So that's going to go ahead and do that. And now what we need to do is compute the local statistics on this GPU. So what we're going to do is our local cluster count is going to be embed one hot dot sum 0. Remember, this is n by k, where it's along the k dimension. So if it's going to be like 0 1 0 0 0 1 0 0 1, let's say something like that, then what we really want is how many. So we have n by k. We just need to compute the sum along this dimension. How many times? So in this case, this first one was used 0 times. Second was used 1 time. Third one was used 2 times, right? Basically, my local statistics. And this operation will happen per GPU because this embed one hot variable right now is on each GPU separately. We haven't kind of combined all that information together yet. So essentially, it's just that. So just add up the number of times each one of these things were used per GPU. So that's going to be .sum0. And then what we're going to do is compute the embed sum, which computes the sum of all the vectors assigned to a cluster. So our local embed sum is going to be x.transpose at embed one hot. So what this is doing is we have a dim by n, because remember x is n by dim, so we transposed it, and we map mul it with dim, by n by k, and this will give us a dim by k. So if we have, let's say 0, 1, 0, let's see, 0, 0, 1, 0, 1, 0, something like that. And what we're doing is we have that, and then we had some other, let's say dim is 2. So A, B, C, D, E, F, and we actually flipped it, so let's do it this way. Here, I want to make this clear. So we have A, B, okay, C, D, E, F. There we go. All right. So basically, we have 3 vectors because we transposed it, right? So it's this direction. So there's 3 of them, and each of them is, so the first vector is AB, second one's CD, third one's EF, right? Those are my vectors. And I'm doing the map mul between this 2 by 3, dim by n, by 3 by 3, which is going to be n by k in our case. And so here, let's make this a little bit clearer. So EF, just make the dimensions different, G and H. And then let's add another one right here. Let's say it's 0, 0, 1. And so what would this map mul look like? Well, it's going to be this row times this column plus, and then this row times this column, and then this row times this column. Well, what does that actually give us? In the very first one, it's going to be A times 0 plus C times 0 plus E times 0 plus G times 0. So that's just 0, right? There's nothing really happening there. And then in the next one, it's going to be A times 1 plus C times 0 plus E times 1, so plus E, plus G times 0, so there's nothing else there. And then the last one will be A times 0 plus C times 1 plus E times 0 plus G times 1 plus G. There you go. And let's do the next one. So it'll be kind of the same thing exactly. So it'll be 0. And then we'll have essentially indexing out B and F. So B plus F. Oh, B plus F. And then so B plus F. And then we'll have D plus H. Well, what does this look like? This looks like all I've done is I've added together. So if we look at this one here, it's A plus E, B plus F. That's A plus E, B plus F. So all I did is I added this vector here with this vector here. And then C plus G, D plus H. That's adding this vector here with this vector here. And that's exactly what I want because I know that let's see. So this first index, right? So this is index 0, index 1. Index 1 it selected, so the closest codes, the closest, basically closest embeddings to this is going to be this one and this one. So sample number 0 and sample number 2 were selected to be assigned to code number 1. And so that's sample number 0, A, B, and sample number 2, E and F, and then we add them together, A plus E, B plus F. In the same way, I have this sample here and this sample here, so sample number 1 and sample number 3 were assigned to code index number 2. That means code index number 2 is going to be the sum of sample number 3 and sample number 2 and code index number 2 is assigned to sample number 1 and sample number 3. So what's sample number 1? That's C and D. Sample number 3 is G and H, so C plus G, D plus H. And so this is just the sum. So if we kind of go back to here, that's exactly what this is, right? All I've done is I found, let's go here, for this specific code vector, what are all the corresponding closest ones? These code vectors have a 1 in the index that tells us what's the closest one, and then 0 on all the other ones. And all I'm doing is adding all these code vectors together. So because this code vector and this code vector, or sorry, this vector and this vector were both assigned to the same code vector, 1 and 1, we have to add them together. So that means A and B and E and F were assigned to both this code vector, and so we're going to do A plus E, B plus F. In the same way, this one and this one were assigned to code vectors, basically this last code vector, and so that means we're going to do G plus C plus G, D plus H, right? This one and this one. And so this is just an easy way of basically doing that accumulation. That's it. Nothing too crazy. You can draw that out for yourself as well if you're still not convinced, but that's it. So if self.is distributed, here's the key part. Of course, this is the local per GPU. And so now we need to do global cluster count is going to be count. Self.accelerator. What I want is the total sum across all GPUs. So we can use reduce. We're going to reduce the local cluster count. And our reduction type, reduction, is going to be sum. So basically take that vector that we produce from every single thing and just add them all together. And we're going to do that both for the cluster count, and we're going to do it for our embeddings, right? The local embed sum. And then I know that the division of this and this is essentially what we have, right? What we've done is we've computed M. M is this sum. I have N right here. N is my count. And so M divided by N will give me my average. Of course, we can do exactly the same thing if we have a single GPU. It's much easier. We just store them like that, and that's it. And so now we need to do our EMA updates. So we're going to do EMA in place. We're going to do self.cluster size. Remember, the cluster size is not actually the cluster size of the current batch, but rather the running average of the cluster size over many batches. Our global cluster count. Spelled that wrong. There we go. Global cluster count. And with some decay, which is a hyperparameter. And then again, EMA in place. Self.embed average. It's going to be the global embed sum. We need to go ahead and transpose it because when we did all this, this thing is all transposed. It's dim by k. We're going to make sure it's k by dim, so we're going to transpose it back around just so it matches the shape, the original shape, how we saved it. And then, again, this is going to be self.decay. So we have our running average of that embed average right here, right? That's our running average. And so what we've done is we've now updated the cluster size, the running average of the cluster size. We've updated the running statistics of our embeddings. And so now it's time to actually update the embedding. So our cluster size is going to be equal to, and this is the important part, we're going to make sure we don't have a divide by 0 error. So we can do Laplace smoothing, which will add a little bit of, value to our zeros, just so they're not 0. And we can do then self.cluster size, self.codebook size, and then self.epsilon. So that goes ahead and does the Laplace smoothing times our self.cluster size dot sum. So this goes ahead and just updates our cluster size to have this additional Laplace smoothing term applied to it, just so we don't, divide by 0. And we're good to go, right? So our cluster size, all we now need to do is embed normalized is going to be self.embed average, which is just a sum up till now, right? It's the sum, basically the running sum of what we've had. We just need to divide by the cluster size dot unsqueeze -1 just to add that extra dimension in. And then we can do self.embed.data.copy embed normalized .copy embed normalized. And that's basically it, right? After that, very simply, we just need to do our quick updates. So go ahead and synchronize is distributed. If it's distributed, go ahead and broadcast all the buffers again, wait for everyone, and then return quantize and those embedding indexes. And that's essentially it, right? Nothing too different. So yeah, there's a lot going on. So as a recap, right, all we've done is we take some data x, reshape it so we flatten the first 2 dimensions, so it basically becomes an n by e, where n is batch times L. Go ahead and initialize the embeddings, which only runs on the first forward pass. After that, it doesn't do anything. It's a no-op. After that, we have our embedding indexes, which cluster was each of the samples in b times L assigned to. And then we get the one hot encoded version of the same information. And then we go ahead and grab the actual quantized embeddings. And if we're not training, that's all we need. We just need the quantized and the embedded. But if we are training, then go ahead and gather all the samples across all the GPUs, because we need that information to do global statistics rather than just on a single GPU. Once we're done, we go ahead and expire any codes that have fall under the threshold. And the threshold is based on our cluster size. We then get a local cluster count on every single GPU, how many samples were assigned to each of the things, each of the cluster centers. Go ahead and do our mapmul here. This is essentially, again, going to go ahead and compute our M's for every single cluster center, add together all the values from X that correspond to each of those cluster centers, giving us a final dim by K or K by dim. So for every single cluster center, we have an embedding size of dim, and these dims will be populated with the sum of the x's that were assigned to that specific k. And that's a simple one hot encoded. After that, if we're distributed, we need to do the reduction across all GPUs to get global statistics. Otherwise, we're done. There's nothing to do. We then do EMA updates on the cluster size, so we get a running average of what the cluster size, the assignment to each cluster is. And then we also get the embed average. Basically, just go ahead and this is our running track of that sum from earlier across all the GPUs, of course. And then go ahead and store that. And then our actual cluster size, just in case some cluster had no assignment, we'd have a divide by 0 error. So you multiply by the Laplace smoothing term to ensure that we no longer have that same issue. So this just adds a little term, so we don't divide by 0 anymore. And then we go ahead and actually divide the embed average by our cluster size. So we get, m over n gives us the actual cluster centers, and these give us our new embeddings. And then once we've computed them, copy them into embed, and then broadcast them again across all GPUs. Technically, all this stuff should be the same, because this reduction and this gather, these are all-to-all operations. So all GPUs will basically share data with all the other GPUs, but in case of some tiny little numerical inconsistencies between GPUs, go ahead and just make sure the main GPU copies its copy specifically to all the other ones. Wait for everyone, and we are done. With this now, we can write our vector quantizer. So I'm going to copy the class definition right here. A lot of this will be relatively straightforward now. So yeah, hard part's done. We've finished the hardest part of this implementation. So in the vector quantization, we have the dim, and we also have the codebook dim. And the dim is basically what's coming into the model, into this quantizer. And the codebook dim is the dimensionality of the codebook itself. Like every single vector in our codebook has what dimensionality. And this is for the most part fine, but if dim is different from codebook dim, then we need to project it. We need a linear layer, right, to project between the two. And so what we're going to first do is our codebook dim is equal to codebook dim if codebook dim is not none, else dim. So if our codebook dim is set to none, then we assume that dim is we're just going to use dim for everything. And then requires projection is going to be codebook dim does not equal to dim if there's a difference there. So self.proj in is going to be nn.linear from dim to codebook dim if requires projection, else nn.identity. And then self.proj out is the same thing. It's going to be a linear layer, but it's going to go from codebook dim back to dim if requires projection, else nn.identity, right? Just some setup. And then we essentially have our, oh, actually, we forgot to do one thing. We wrote the forward method here, which is fine. We technically haven't wrote the encode and decode. Let's quickly do it. These are easy. So to encode something, these are computed. There is no gradients anyway, but torch.no grad, we'll just throw that on there. To encode something, we're going to do our shape is equal to x.shape. This should be batch by L by E. X is in self.preprocess X. Our embed index is going to be self.quantize X, and then embed index is going to be self.postprocess embed ind and shape return embed ind. So this will just give me my code vector, right? This is it. It's just to do that. And then the other one is exactly the same thing. So I'll just paste them in. So that's just to give my code vectors batch by L by E, N by E, where N is B times L, grab the embed index N, but I don't want it as N. I want it back as B by L, essentially. So I need to do that post process that takes N and splits those dimensions back apart. And then we have that. And to decode, we just essentially take the embeddings and then pass them through the dequantization. So it's just a subset of what we had down here. Okay, so continuing on, just my bad, forgot about that. We just need those. And then, of course, we have our codebook. So we can just paste that in here. It's what we wrote earlier, just pass in all of our methods. And that's it. And of course, we can pass in the accelerator as well if we need it. And so now what we're going to do is our encode. We'll start with the forward method again. So forward self x device is equal to device is equal to x.device. We're going to do x is again ein ups. X is going to come in the shape of batch by D by N, and we're going to make it batch by N by D. So it's just a transpose. And then X is going to be self.proj in X in case we need to project it, right? Einups.rearrange. In case we need to project it to the code vector, right? So if our code, whatever the codebook dim is, if we need to project it, we have to project it. So we're going to proj in here. After that, we need to do our quantize, and our embed int is going to be self.codebook x, right? That's us actually doing the quantization with all the codebook stuff that we did. We, of course, need to do our stop gradient, right? So this is the same as before. We did all this stuff, and our codebook will be trained via EMA, but we still need to copy gradients from later to the past. So if you remember again from our VQVAE, that's pretty straightforward. All we do is if self.training, we're going to do quantize is equal to x plus quantize minus x.detach. So this technically looks like we're doing quantize equals quantize because x and minus x will cancel. So this keeps the same value, but this essentially tells PyTorch that this essentially all PyTorch is seeing is quantize is equal to x, which isn't true. Quantize is equal to quantize. That's why we have this stuff here. But by saying quantize is equal to x, then when we do the derivative, essentially we're going to copy the derivative from x into quantize, which is essentially going to skip over the entire quantization process here because there is no way to compute gradients through this. And we've already handled that. So this is our stop gradient, right? Standard method for this stuff. Now what we need is our loss. We have the EMA method to update the codebooks. We also need to update our, the rest of it, basically the actual encoder portion of the model. And this was the commitment loss. So remember back here, we have a commitment loss, which essentially is make sure this is close to the embeddings here, and that's our gradients here. And then we have our codebook loss, which is to update this. The codebook loss has now been replaced with our EMA updates. So we don't have that, but we still have the commitment loss. So we're going to do that here. And so by default, we're going to say loss is equal to torch.tensor 0. Just a placeholder. Device is equal to device, requires grad is self.training. If we're training, then yes, we need grad. If self.training, if self.commitment weight greater than, where is it? Greater than 0. So we set this up here, right? The commitment weight, whatever you want. If it's greater than 0, then our commitment loss is going to be f.mse loss, that means squared error loss, between the quantize.detach and x, which is exactly what we had here, right? We're going to go ahead and take the quantized terms, detach them, and we want our embeddings, which is x in our case, the raw embeddings that are going to get quantized, we want to make sure that this is close to the values of this. And so we need to just do the mean squared error between the two, and that's exactly what you see here, quantize detach and x. And our loss is equal to loss plus commit loss times self dot commitment weight. Okay, I think yeah, okay, good. That's it for training. And then we're going to do quantize is equal to self.proj out quantize. Of course, if we change the dimensionality in the forward pass, we also need to put it back how we found it in the, as we continue at post quantization. And so now we have that, we can do quantize is equal to inops.rearrange, just put it back how we found it. So it's going to be batch by n by d back to batch by d by n. And again, the reason we did this is because in convolutions, our data comes in as batch by channels by sequence length. But we want it to be batch by sequence length by channels, right? Because the d, the channel dimension, is what we're essentially the dimensionality that we're quantizing over. So there we go. Okay, and now we can return the quantize embeddings, the actual embedding indexes, and the loss. And there we go. Just as two quick helper methods, just kind of wrapping everything we did. The forward method is what we'll use again for training, but for the actual, let's see here, this needs to go back. I need to tab U back once. There. So yeah, to encode and decode, it's exactly the same thing, but oh, I missed some of that. There we go. Yeah, so to encode and decode, we'll use the forward method for training purposes, but once we are done training and we are just inferencing, then we'll use this encode and decode method. And it just does exactly what we've done earlier, or it does exactly what we did here. But that's it. Okay, good. So that is our vector quantizer, right? Nothing too crazy. A lot of the hard work is kind of handled for us through basically the codebook. The Euclidean codebook does all the heavy lifting for us, but we already wrote that. And now, of course, we don't have one quantizer, we have many of them. So we're going to do class residual vector quantization and then module. We're going to do def init self num quantizers. So how many do we want? And then other kwargs, right? Kwargs being all of the information we care about for each of the quantizers, right? And now that we have that, let's just go ahead. All we need to do is define a bunch of these quantizers in stack. So it's going to be super.init. It's going to be self.layers. It's going to be nn.module list vector quantization with those kwargs, whatever we want, for blank in range num quantizers. Just go ahead, just create a bunch of them, however many we want, and then everything else is going to be kind of the same. So let's just write with the forward method. So def forward self x. And now instead of quantizing x once, we're going to quantize it many times. And so how we do this is essentially this. We're going to create a variable called quantizer out. It's going to be 0.0 initially. And our residual is going to be x initially. And we're going to do all losses is an empty list. All indices is going to be an empty list. And what we're going to do is, and we're going to actually pass in one more thing here. NQ is none. So let's say we define this with 8 quantizers. That means by default, we can go through 8. But if I set this to 3, then I'm only going to use the first 3 quantizers of the 8. And so this is just a limit. So we'll see that be used later. It's used for basically multi-bit training. We'll see that later. So what we're going to do is NQ is equal to NQ or len self.layers. So if we set NQ in here, then use that. If we don't set NQ, then we're going to go ahead and just use all of them. So the length. For layer in self.layers up to NQ. Okay, actually, yeah, let me make sure I keep the underscores everywhere so it's all the same. There we go. For every single one of the layers, we're going to do quantized, indices, and losses is going to be the layer residual, right? Basically into one of these vector quantizers that we had from earlier, we're just doing the standard forward pass, which is going to return the quantized, the embeddings, and the loss, right? Our commitment loss. So there we go. And what we're going to do is this. Our residual is equal to the residual, which at the very first iteration is just x. So all we did is really just pass an x, and we're going to subtract quantized dot detach. Okay, so what we're doing here is the residual is my initial input, and I get my quantized representation, estimation of the residual. So the difference, the new residual is my old residual minus what I estimated, because there's going to be some estimation error between what I quantized it to and what the true values were. And we're doing dot detach here because of course we can't compute gradients between these, because we can't actually, this is the entire quantization process, right? So there is no derivative between these, so we do dot detach. And so this is just treated as a constant essentially. And then our quantized out is going to be equal to quantized out plus quantized. Basically, our quantized out here is going to be the original one plus the quantized. And every time we do it, our quantized is first a representation of x, and then the next one's going to be a representation of the error, and the next one's going to be a representation of a second level of error. So kind of going back to here, right? This quantized embedding selected right here is a representation of this, my best guess, but there's going to be some error, some quantization error between the two. So that's going to go onto here, that quantization error. That quantization error gets quantized again for this embedding here. My best guess at that residual, take the difference. And then we keep going. This is my second stage of residual. Go ahead and quantize it again and repeat that over and over again. That means this, my best guess at the original, plus this, my best guess at the first level of error, plus this, my best guess at the second level of error. If I add all three of these together, that should be a closer estimate of my original input than this would have been. And that's the entire point of RVQs, right? So basically what we're doing is as we get each of these quantized, each quantized is a better and better estimate of a deeper residual. And so adding all of those quantized together should give me my final representation. Now that we have that, we don't need you. We're also going to store some information, the all indices.append indices and all losses.append losses. And then our out losses, once we're done at the very end, losses is going to be torch.stack all losses. And then our out indices is going to be torch.stack all indices. And then we can return back our quantized out, which was our accumulated final quantization, right? Basically from all the blocks, added it all together. And then we have our out indices, and out losses, and we're done. Our encode and decode kind of look the same, but I'll actually type these out. So def encode self x nq by default is none. We'll use the enq for something called variable bitrate training. So when we actually write the training loop, we'll see why this matters more. So no grad. Okay. And we'll do our residual is again x. All indices is an empty list. NQ is equal to NQ or len self.layers. We're going to do for layer in self.layers NQ. And this will actually I don't really need to type this. It's exactly the same code as before, so that's fine. Just to save us some time. So basically all we do is just loop through, grab them, do that. And remember, we don't need to do the detach or anything anymore because there's no gradients anyway. Stack them, return the indices. And basically the indices will look like this. From every single code book, we'll get the sequence of indexes for the sequence of time across time, right? So there we go. And in this case, we'll get 75 of them for every second of time we have in our audio because we have the downsample factor of 320. To decode, exactly the same. We start with zeros and we iteratively grab our indexes and then add them all to get the final quantized output. And that's it, right? Nothing of too much concern. So I believe that's it. So I wrote a quick test case here. So yeah, let's run that real quick. So yeah, so what we have here is basically our number of processes. So let's do accelerate launch So it's inserting. Okay, so if we do Python, that's actually a good point. If we run with Python, Python will just run this with a single GPU. Num processes is 1, current process is 0, and we just go ahead and do everything, and nothing really happens. There's no synchronization needed for single GPU. Let's actually do right here. If I run with accelerate launch, this will run it with 2 GPUs. And so we can see there's some extra stuff happening, but it checks at the end what's the difference between GPUs and the difference between cluster sizes. Everything is the same because everything gets copied over, right? So it basically test just runs a couple of iterations. And then after a couple of iterations, we just synchronize across GPUs and then verify that the values across GPUs are all the same. And we do see that is true. So we are good to go. Okay, so that is our quantization. There's a lot of stuff going on, but that's okay. Let's see here. So we wrote that. Let's go back to our EnCodec architecture. As of now, we have essentially completed the encoder, decoder, and all of the quantization stuff, and everything now works on our multi-GPU setup. All that's left is this discriminator, and then of course the training loop. Discriminator is actually relatively simple, so let's go ahead and write it out. Okay, so now it's time to go ahead and implement our discriminator, right? So as we know, here we've implemented all of this stuff. Now we have to implement the discriminator, and it's relatively straightforward. So let's just go ahead and get started. I'm going to paste in a bunch of the extra stuff, so we can paste that right here. There we go. Okay, so these are just standard imports, and then we have our normconv2d that we implemented much earlier, and then this is the configuration of our discriminator, okay? And in this discriminator, what we essentially have is how many input channels and output channels. They should be the same. The number of filters and max filters and filter scale. So number of filters is the very first convolution is going to project from 1 to 32. And then for every subsequent convolution, how much do you want to scale the filter scale by? So if it's 2, then it'll go like 32, 64, 128. By default, they use 1, so the number of filters will not change. And then we have the max filter, so we don't exceed that. So if we set this to 4, it'd go 32 to 32 times 4, 35, so on and so forth. We just don't want to exceed some max threshold, but none of these really apply to us as max filters set to 1 and we set filters to 32. We will have multiscale discriminators, right? So this discriminator, there's going to be multiple of them, and each of them, and this is the key idea behind the multiscale discriminator. We can see it says multiple scales right here. What this is going to look at are the spectrograms. So this discriminator looks at the spectrogram of the generated audio and the spectrogram of the input audio. And the discriminator has to analyze, which one is real, which one is fake, just like every other discriminator. And so because we're looking at the spectrograms, we need to run them through 2D convolutions, because spectrograms look like this, right? They're basically just images, right? And spectrograms have their time frequency relationship. If you have a spectrogram with a high window size, like the window size is large or your FFT window is large, that means you have good frequency resolution, but you have poor time resolution. On the other hand, if your window sizes are small, then you get good time resolution, but poor frequency resolution. So there's always a trade-off between the two. And that's why they say instead of just doing one STFT discriminator, let's do a bunch of them with the different window sizes. And we can see all those window sizes set here. Okay. So to implement this, it's relatively straightforward. We have, let's create some data. So let's do class discriminator STFT add-in.module. And actually, I'm going to paste all of this stuff in just so I don't have to type it all. There we go. So it's just all the stuff about this specific. So this is one of many discriminators, right? So we have one of many. And of course, we also need the ability to take audio and convert it to a spectrogram, right? So we can do that right here. So we use Torch Audio to do that. So Torch Audio has a spectrogram method that runs on the GPU, so we'll use this. And these are standard spectrograms. So for this specific FFT, let's go ahead and do that. So let's do rand is equal to torch.randn. Batch size of 2, sequence length, or let's say we have one input channel and a sequence length of 25,000. Or let's do 24,000, right? That's 1 second of audio. So let's do times 3 for 3 seconds of audio. And our discriminator, one of them is going to be the discriminator STFT. So let's print out the discriminator real quick. So we can do Python modules discriminator. Called it. There we go. So it has an activation and that's spec transform. So let's write a forward method real quick. Def forward self x. And we'll kind of write the forward method and the actual methods themselves at the same time. So we'll see. So we're going to do feature maps. We'll see what that is in just a second. Z is equal to self.spec transform x. And let's print out x.shape or z.shape. So z, there we go, z.shape. What you'll see is it looks like this. Oh, I have to actually pass it in. So disc rand. You'll see it looks like this. You have 2 by 1 by 513 by 278. So basically, we have 2. The reason there's a 2 here is our batch dimension. And then we have the 1 channel. And then we have basically a height, 513, and the width, 278. The height is the frequency dimension, right? So we picked a window size. The default is set to 1024. So we have essentially 2 of them. It's split because we have the real part and the imaginary part. So we have 513. And that's essentially it, right? That's our setup. And our sequence length of 2400 got compressed down to 278 because it depends on the window size and the stride and things like that. So that's a standard spectrogram. Nothing. We have our frequency dimension and the time dimension. Now this z, if we just print out z alone, you'll see that there's actually something here. We have this part, we have like numbers, but then we also have these imaginary numbers. Because of course a Fourier transform, like a spectrogram using Fourier transforms, have the real and the imaginary parts. So what we do here is there's actually 2 possibilities. We can print out abs, torch.abs, z. If we do this, this will give us the magnitude spectrogram, the amount of energy at different frequencies at different times. We could also do torch., I think it's just angle. Torch.angle gives us the angle in radians, but the phase information. Remember, a Fourier transform gives you 2 things. You can get because they're imaginary numbers, for each imaginary number, we can get the magnitude and the phase, the angle information. And both of those are just as important, right? The phase is kind of the alignment of the different frequencies, and the magnitude is the amount of energy of the different frequencies. And so what you see in the EnCodec papers, they say, well, we have the real and the imaginary part. Let's just concatenate them together and have our convolution process both of them. So what we're going to do is just very simply, z is equal to torch.cat z.real and z.mag on dim equals 1. Concatenate them on the channel dimension. So now if we look at the shape, we have 2 batch size of 2. We have 2 channels, each of them being 513 by 278, where the first channel is the real portion and the second channel is the imaginary portion, because I know the combination of the 2 gives me both the phase and the magnitude information, and that's what the convolution is going to be processing. And then what we're going to do is z is equal to inops dot rearrange z, and we're going to go from batch by channel by width by time to batch by channel by time by width. So we're just going to do a quick transpose essentially. And that's it. So that's the first part. Now what we're going to do is pass it through a sequence of convolutions that's going to analyze this batch by channel by time by width, where the time dimension is that, and the width is technically, so instead of width, this is batch by channel by time by frequency, right? The frequency, basically our frequency dimension. So these are all the different frequencies, and these are all the different times. And so how we're going to do this is a couple ways. There's different views that we can take. So the way they set it up is, let's do a stack of dilated convolutions. And these dilated convolutions give essentially different views into it. So for every single convolution, we're going to go ahead and do a dilation. So we're going to do for I. We set this up here actually. So dilations, 1, 2, 4. So that's saying we want a convolution with a dilation of 1, then another one with a dilation of 2, and then another convolution with a dilation of 4. And the number of convolutions we do is set by the number of dilations. If you do 1, 2, 4, 4, 4, that means we would have 5 different convolutions that we do here. So we do for I, dilation, enumerate dilations, dilation. There we go. Couple things. Actually, before we do the dilations, we haven't even done the initial. Sorry, I missed one. We forgot something. Our data is coming in with 2 channels, as we see right here. 2 channels. We need to first do the projection. So we need to go from these 2 channels to the initial 32 channels right here. So let's add that convolution in first. So we're going to do our spectrogram channels. Spec channels is really going to be 2 times self.in channels. And then self.cons.append, which I haven't even created. So self.cons is going to be nn.module list. Each of these convolutions is going to be a norm conv 2D with the spectrogram channels as the input, self.filters as filters is the output channels, kernel size is equal to kernel size. And that's it. Now, oh, that's almost it. Let's kind of see what happens when you apply this. We're going to do for conv in, let's see, for conv, or let's actually do this for I layer in self.cons, which we only have this one layer right now. We're going to do z is equal to layer z, or print z.shape. For I layer in self.cons, oh, enumerate, sorry, enumerate. We get a 2 by 32 by 276 by 505. And just to make this clear, print z.shape. The shape before and the shape after. We can see that our number of channels have gone from 2 to 32, but our height and width dimension have kind of changed here from 278 to 76 and 513 to 505. We don't want that. We want to make sure we pad it so it doesn't change. And there's a couple ways we can do this. We can do padding equals same, I believe. Actually, don't think, yeah. So we could either do that, or we can do what they do in the implementation. We can compute. Maybe when this was implemented, the padding equals same wasn't an option in PyTorch, but this is exactly what PyTorch does when doing padding equals same. Basically, it's the kernel size times dilation minus dilation divided by 2. If we add this much padding in the 1D case, or in the 2D case, it's exactly the same formula, but it's in kernel size will be a tuple of kernel size in the x direction, kernel size in the y direction, dilation in the x direction, dilation in the y direction. As long as you do that, then we'll get the same padding. So this will be padding is equal to get 2D padding kernel size. Right, so the very first one is going to get this specific kernel size. We know this very first convolution has no dilation, so we don't really need to worry about that extra case. This doesn't really change anything. There you go. So the same thing. It doesn't matter. You could have just done padding equals same and gotten the same result. It's up to you. So, okay. So that's our very first convolution that does the projection. So now we're up to 32 channels, 278, 513. Now that we've done that, up for the next part. We need to find our, we're going to essentially analyze this convolution, this image, with different dilations. And that's the main idea, right? So it's kind of resolution in the sense that different convolutions analyze the same piece of data in different ways. So basically deeper layers will have deeper dilation factors. So the way we're going to do this is like this. We're going to do in channels is equal to, and this is the sanity check, filter scale. It doesn't really apply to us, but it's fine. Self.filters and max filters. We want to make sure that whatever we do, we don't exceed max filters ever. And we multiply our input channels. This is going to be the self.filters times the filter scale, whatever you want. But again, because everything for us is set to 1, it doesn't really matter. And so now we're going to do for I dilation in enumerate dilations, our out channels is going to be equal to min. And the way they do it is deeper layers should have deeper channels, more channels essentially, as we increase our based on the filter size. So what they do is basically filter scale to the power I plus 1 times, and outside times self.filters and max filters. So we can see basically filter scale is 2, then it's going to be 2 times self filters, then 4 times, 8 times, so on and so forth. So we just kind of keep increasing it by the scale factor. For us, the scale factor is just set to 1, so there's nothing to do. So I'm just going to go ahead and paste the rest of this in. Basically, we have that. Our convolutions, again, just the norm conv, which the input channels from before, the new output channels that we compute here. We have a kernel size stride, some dilation. So here's one key idea. The dilation is only being applied along the first dimension, which is our time dimension. So the dilation is along the time dimension, but along the frequency dimension, there's no dilation. So we're essentially analyzing every frequency dimension individually, like we're going to get all of them in there. But our time dimension, we want to do different dilations, just kind of analyze our frequency information at different time scales. And that's just a cool little trick. How much that helps, I don't know. Maybe if we change this to something else, maybe it would help. But it wouldn't actually make sense to change the to skip different frequency dimensions, because the frequency dimension is kind of constant. Like if this specific convolution will always have a frequency dimension of 513. This specific short time Fourier transform, because we picked 1024 as the FFT and the window size. So this will always be 513, but this one is variable. Like the length of audio is variable and just depends on what we're processing. So I guess it just makes sense to have multiple views along the time dimension, depending on the length and stuff like that. So okay, so we have our in channels, out channels. After that, we need to do another set of convolutions. So this is again going to be exactly the same thing. So this is going to be the next out channels after the dilations plus 1 for a non-dilated convolution. All of these were dilated convolutions. Let's do one without any dilations. So this is again going to be very simple. It's exactly what we had earlier, with just one small change. Our out channels is going to be len dilations plus 1, because we've already done these many convolutions. Each time we've increased the number of out channels by filter scale, which again is just 1 for us, so this is like doesn't actually matter. So there we go. And then we multiply it by self.filters up to max filters, and then we get our norm conv 2D, and now we get kernel size, but no dilation. So we have our kernel sizes and we're good to go. And the kernel size, as you can see here, is set to 3 by 9. So it's a kernel size of 3 in the time dimension and 9 along the frequency dimension, right? And that's essentially it. So that is our convolutions. Nothing too challenging. Lastly, we need a final convolution. All this convolution is going to do is just put us back to out channels. So we have in channels as 1 and out channels as 1. We're currently at out channels of whatever this value is, up to max filters. So the final convolution, which I'll also just paste right here, is again that norm conv 2D. Everything else is the same. Just we go to out channels now, which is 1 for us. And that's it. And so now what we do is for layer and z, we pass them all through. We're going to z is then self.activation, right? That leaky ReLU activation, apply it. And then what we do is fmap. So we created that variable earlier, fmap.append z. And then that's it. And then z is equal to self.conv post, the final one, c, and then we return z and f map. So there's two things going on here. This convolution, the output has 1 channel, and basically we'll be asking, is it real or fake? We'll see how we do that a little bit later with the standard like hinge loss method for computation for that. So don't worry about that for now. But the other thing we're going to do is a feature mapping loss. Feature mapping is we want 2 things to happen. The discriminator needs to be able to look at real images and fake images and tell us which is real and which is fake. That's based on z. But we also want to make sure that the generator is producing audio, which can then get converted to spectrograms, such that the features extracted by this thing match the true image, the true audio as well. So essentially what's going to happen, you'll see this in just a minute, is that we get feature maps from some data, and these feature maps, just imagine them as multi-scale extracted information. They're basically some kind of latent representation, some features that we've extracted on these spectrograms. And what we do with that, we'll see in just a second. For now, though, this kind of sets it up for the single discriminator, but of course we need multiple. So I'm going to go ahead and paste this right here. This is going to take that config from earlier, so everything's going to be based on that. And there's a couple things that we need to make sure. So I'm going to just keep pasting stuff so we don't need to type any of this in right here. So basically go ahead, check NFFTs, hop lengths, window length. And then we basically have these discriminators at number of filters, in channels, out channels. But the things that change between every single one of the discriminators is the FFT, the window length, and the hop length. Remember up here, right? We have n FFTs, hop lengths, and window lengths. That's all that changes between the different discriminators. They're going to have a different time frequency trade-off, time frequency resolution that they're analyzing on. But other than that, it's all the same. So there we go. And so now that we have that, basically a stack of these discriminators, and how many do we have? We have len. Let's go ahead and actually write the forward method. So the forward method, very simple, def forward self. We're going to pass in real images and or not images, but real audio and generated audio. And then we'll have real outs, gen outs. We'll have our real feature maps and then our gen feature maps. And basically, these outputs will be the final output, the z. So for every single one of our discriminators, we're going to get some z for both the real and the gen. And then for every single one of the discriminators, we're going to have a list of feature maps for the real and the gen. And that's essentially it. So this is going to be a list of tensors, and this is going to be a list of tensors, right? Because each of the feature maps is also internally another list, right? That'll be a little bit more important later. So for discrim in self.discriminators, just loop through. So we're going to do real out, and real feat map is going to be discrim, real. And then our gen out, gen feat map is going to be discrim, gen. And then we'll do real outs dot append, real out, gen out dot append, gen out, real feat maps dot append, real feat map, and then gen feat maps dot append, gen feat map. And there we go. So just go ahead and store them. This is, again, this will be a list of tensors. This will be a list of tensors. So, you know, we'll have to dig in twice to get those values. So then we return real outs, gen outs, real feat maps, gen feat maps. That's it, right? Very, very, very simple. Okay, so now that we have all of that, additionally, right, it's completely up to you. So we've kind of seen the code, so I'm just going to paste in my code itself just to show you an example of what you can do. My code has not just the multiscale, but it also has the multiscale time discriminator and the multi-period discriminator from HiFiGAN. This makes it closer to the what do you call it? To the speaker tokenizer, the speech tokenizer paper, right? So the speech tokenizer paper additionally uses these things. But for now, essentially, we're going to have these set as false because we don't really care about them, just to kind of keep it simple. Oh, I also forgot to write this method. We do have an initialization method to initialize weights, where basically if it's a convolution, use the standard weight initialization for convolution with the mean of 0, standard deviation of 0.01. But that's fine, right? Nothing too important right now. Yeah, so this is the periodic discriminator directly from my HiFiGAN implementation. This is the multi-period discriminator from HiFiGAN, scale discriminator, and multi-scale discriminator. You can see this. I already wrote all this in my HiFiGAN, so I'm not going to do it again. And then my final discriminator is basically just all of these discriminators put together, and I just, it's all the same outputs, but we grab the outputs and feature maps from each of the multiscale, my multiscale time from HiFiGAN, and the multi-period time, again, from HiFiGAN, and store them this way. Again, we won't be using any of these right now, so it's fine. It's just to show you an example of if you come up with some other ideas for discriminators, it's pretty easy to just add them on because they all kind of do the same thing. Okay, so that is our discriminator. It is time to just wrap this all together into our final EnCodec architecture. So let's write modules, new file, EnCodec.py. There's not too much interesting stuff going on here. It's just wrapping everything we've done into one thing. So I'm going to paste the config and then we'll write the model out. There we go. So we have our SeaNet Encoder Decoder. We have a residual vector quantizer. And then we have just all of our standard stuff. So this is going to define, this is going to be elu by default instead of snake. just to make it the same. We have our ratio. So this is again downsample by 320, 8 times 540, 160, 320. We have our activation parameters, just everything we've already seen while implementing, right? Just in one place. And then this is the quantization. We're going to be using 8 codebooks with 1024 embeddings per codebook. And that's it. And each of these codebooks will have a dimensionality of 128. So remember the EnCodec, the final convolution, outputs a 128 channel feature vector, right? So for every single time step, we'll have 128 things. And so this, because codebook dim is set to none, my codebooks will also be 128. If I want it to be less, then I could set that here, and I could change that if I wanted to. And so with that, our EnCodec model, I'm just going to keep pasting because this is just a lot of copy pasting. We have essentially our config, the accelerator if we need it. We have our encoder with all of its stuff. We have the quantizer with all of its stuff. And we have the decoder with all of its stuff, because that's all the EnCodec is. And then just to quickly write out its use case, so it's going to be def is distributed. Again, this distributed is just a sanity check for us, so we can, same chunk of code from before. Here's the first kind of new thing. We need to make sure, of course, different audios, when we pass them in, can have different loudness. So we need to essentially scale the loudness. So we'll write this normalize method, self x, and they do something called RMS, which is root mean square normalization. So we want to make sure that all signals have unit root mean squared error, which is easy. We can do batch size by channels by sequence length is equal to x.shape. And then mono is x. We're going to assume our data is mono. So if we're going to do if channels is greater than 1 for some reason, then we're going to do mono is x.mean dim equals 1, keep dims equals true. So just go ahead and, if we have like dual channel audio, just average those channels together. And our volume is equal to mono.pow 2.mean dim equals 2, keep dim equals true dot square root. So that's root mean squared error, right? So we square it, mean it, take the square root of it. Root mean square, right? So there we go. Volume. And our scale is going to be just a little extra term, 1e minus 8 plus volume, right? Just in case. Volume was 0 for some reason. And so x is going to be x divided by scale, and then we return x and scale. So the reason we're doing this, basically we took this audio and we scaled it down and we divide by scale. And that's the encoder and but if we want to reconstruct, if we want to play back the audio, like the reconstructed audio, we need to unscale it. That's why we're returning the scale here, so we can unscale it later on. To denormalize, it's very simple. To def denormalize, it's going to be self x scale. We're just going to return x time scale. Just undo that normalization. So we have the scale. If we divide by here, just multiply here and we're done. Okay. Up next, def forward self x. So pretty straightforward. So batch size by channels by sequence length is x.shape. That's how our data should come in. So x and scale is going to be self.normalize x. Encoded is going to be self.encoder x. And here is one key thing that we want to keep in mind. In our setup, like we have here, we have up to 8 codebooks. And this is completely fine because we can use all 8 of them. But to make training a little bit more challenging, we know that the more codebooks you have, the easier it is for the model to estimate the original embedding vector. And so we can do something called variable codebook training, where we say that instead of using all 8 every single time, what if in one pass I use only 3 of them, and the next one I use 7 of them, next one I use 4 of them, like just randomly. And that's why in our quantizer down here, we defined an NQ. So I kind of briefly showed this NQ right here. This NQ says that if NQ is none, then it's just going to use all of our codebooks. But if NQ is set to like 4, it can only use the first 4. And that means our quantized out is only an accumulation of the first 4 codebooks rather than all of them. This kind of forces the model to do 2 things. If we always gave it the output of the 8th codebook, the other 7 codebooks before it don't have to work as hard to reconstruct the audio. So this essentially puts pressure on early codebooks to also be good, because they could be the only ones available to do that reconstruction task. And so this is basically called variable bit training, or like multiple codebook training, whatever you want to call it. So we can do num codebooks to use is torch.tensor random.randint 0 to self.num quantizers, and device equals device. And that's it. Or not just device, x.device. So this is going to sample some value between 0 and 8, or 0 and 7 essentially, for how many codebooks do we want. But of course, we need to make sure all the GPUs are doing the same thing. If we do this random sampling, it could give different values on different GPUs if we're in distributed mode. So we're going to do if self.isDistributed, then we're going to do num books codebooks to use. It's going to be accelerate.utils.broadcast num codebooks to use from process equals 0. Just copy that one value over. So whatever GPU 0 says that we should use, all the GPUs should do exactly that. And that's it. And now we pass it through a quantizer. So quantized out. We don't really care about the embeddings here, the indexes, so we can ignore that. And then out losses is going to be self.quantizer encoded num codebooks to use. And then our decoded is going to be self.decoder quantized out, right? So there we go. And now that we have all that, we just need to go ahead and, so again, we normalize the data, pass it through the encoder, quantized it, pass it through the decoder to get our final result. Our decoded will be equal to self.denormalize the decoded with that scale. Right? Just go ahead and denormalize it. And here is that other little extra part that we talked about. Remember when we implemented our convolutions here in our transpose cons. So remember, our encoder is full of our sconv 1Ds. Our transpose cons are made of basically the decoder is made of the transpose convolutions. And we did all this extra work to make sure that we unpadded. There were two types of padding that we added in the encoder, right? We had the padding total, which is based on the configuration of the convolution, and then that little bit of extra padding that we just add on just to make sure that we get full window usage for every single convolution. So that's how we set it up here. But in the transpose convolution, in the decoder, we unpad this padding right here. So the padding total gets removed in the transpose conv, but we don't remove the extra padding because we didn't really store this, and it's kind of hard to basically post compute afterwards of what this should have been. And so instead what we do is we say, okay, let's remove the ones that we definitely know is true, and this little bit of extra padding that we may have added, we can remove it at the end. Well, now is our chance to finally remove it at the end. We are going to do it right here. So our decoded is this, and then finally we're going to do decoded is equal to decoded, and for batch channel up to the sequence length. So whatever the sequence length was the input x, is going to be exactly the sequence length for the output. So we just go ahead and clip off. If there's a couple extra samples here, we go ahead and get rid of them right here. And then we can return, I'll just paste this in, return our encoded, the quantized out, our average of all our losses, the quantizer losses, so these are those commitment losses, and then the decoded, and we are done. And that is one step. Everything else after that is kind of just fine. So we are going to just paste these in and just walk through them real quick. So we have first our tokenization method. So this takes audio and returns the tokens and the scale if we need them. We have so remember in the forward pass, we didn't really keep the indexes. We don't care about them because we just want the final output. But when we tokenize our audio, then this is what we need. We have our tokens and scale. And then when we decode our audio, we pass those indexes to the quantizer, we decode them, and then we go ahead and denormalize them with the scale. We clip off any extra things if we set some kind of max len, and then we make sure that the output is clamped between -1 and 1. Right, because that's the output range of audio. We could have also added a 10H to our model if we wanted to, but this is also fine. And then I also write this quick method here called pass-through, where we just take audio and pass it through and just return the reconstruction back. This will be easy so we can plot our reconstructions later and just listen to them. And so with all of this, hopefully, let's see if this works. We're going to go ahead and do this. Actually, yeah, we don't need to do this. This just checks the normalization. So yeah, this should be fine. Yeah, we're good. Okay, EnCodec is done. So you have our, let's see, we have our conv, we have our discriminator, we have our EnCodec, we have our LSTM, we have our quantizer, and we have our SeaNet, and that's all we had. Now that we've completed the actual model, the discriminator, stuff like that, it's time to start implementing the loss balancer. And so this is the other kind of tricky part for this implementation. So let's go ahead and let me make sure I have all of you open. There we go. All right. So the loss balancer, again, as a quick recap, was essentially that if we have a bunch of different losses, which you can see in our like model architecture here, there's a ton of different losses. If we have so many different losses, then the total loss is the sum of them, of course. But that's not exactly how it works out, because when you do backprop, again, different losses contribute to the overall gradient. And so the total gradient contribution is the sum of those gradient contributions. But more importantly, if different losses have different scales, then the amount of contribution made by each of the losses is kind of dependent on the scale. So this one here is going to be almost 100 times more gradient contribution than the first loss because of the difference in the magnitude. And so this is why we typically multiply by some kind of constants, right? We multiply by some constants to just rescale the gradients. And so the final gradient, the total gradient, will be the sum of the scaled gradient contributions. Unfortunately, this is not as interpretable. So again, it would be easier if the loss was balanced according to the proportion of the overall weights. So what we really want is the ratio. If we have like the ratio of A, B, C being 1 to 1, then the gradient contribution of B should be double that of A and C. That's what we would ideally want. And so we need to essentially rescale our losses to pull this off. This is easier said than done. So we're going to start with the implementation and slowly work our way through it. So we're going to do, I believe all we need are these. So if you don't know what a default dict, so if you do print default dict float is what we're going to be doing. So let's Python, and then we're going to do balancer.py. If we print this out, you can see it's a default dict with class float. If we try to index something from it, something that, I mean, this dictionary obviously doesn't have anything else in it yet, so let's just do apple, whatever. Well, you'll see it'll by default just give a value of 0.0. So anything that doesn't exist in the dictionary is defaulted, that's why default dict, of 0.0. So that's why we're going to be using this, and we'll see why that's important a little bit later. So let's just start with the implementation of the balancer, and hopefully this will make sense. So we're going to do class balancer, and we're going to essentially do it this way. We're going to do def init. We need to provide it a couple things. First, each loss that we're going to get will get some corresponding weight. So those are our weights. We have a total norm of 1. So if we look at right here, this R here is the total norm, and it makes sense to have the total norm just being 1. You could make it more or less, but it doesn't really make a difference. So we're just going to treat R as 1, and we're good to go. That's fine. We're going to have an EMA decay, 0.999, epsilon. Epsilon is 1e negative 12. I'm going to set a max scale of 100 and a min scale of 0.01. And these were not actually in the original implementation, but I added them for stability. We'll see why later. So I'm going to go ahead and copy all of this in for now, just to store that. Of course, we also have the accelerator, right? Because we're going to have to, as you remember, this term, the gradients, won't be from, like the gradient from each loss isn't just dependent on the one GPU, but it's across multiple GPUs. So we have to essentially accumulate the gradient contribution across GPUs. We're going to do that a little bit later as well. So accelerator is equal to none by default is what I'll set it as. There we go. There is another thing here, but we haven't implemented it yet. So we're going to come back to that when we get there. So what we need to write is essentially, whenever we run something, right, like what we're going to have is total loss is going to be like loss 1 plus loss 2 plus loss 3 plus ... And then we're going to do total loss. And of course, when we do this, we're going to multiply them by some constants of loss 1 times A plus loss 2 times B plus loss 3 times C plus ... That's how we typically do losses. But for the loss balancer, and once we do this, once we have the final loss, we do loss dot backward And we're done, right? That basically computes the gradients. So what we need to do is write a new backwards method that basically does everything we saw. It basically does exactly this, but we need to rescale the gradients. And so here is the trick. So let's kind of start from the beginning and we'll slowly work through it. So we're going to do def. We're going to do backward. We're going to write a new backward method, self losses input and retain graph is false. So just to give this an idea, the losses here is not going to be just the loss, but rather a list, right? There's going to be a list of losses, each with basically in a dictionary. So we'll have different losses with some key that's like the name of the loss, and then the value that's the loss itself. And then we have the input. The input is essentially going to be this right here. Basically the thing that produced this specific audio. So if we go back here, the input would be like the weights or whatever of the this final convolution layer. We'll see that in a second as well. And then retain graph equals true that's another flag. We're going to need that as well. We'll see all that come together. So first what we're going to do is create some lists, or dictionaries, norms and grads. And we first need to figure out for every single loss, what is the contribution of a specific loss value with respect to the model output. So the model output is the waveform, right? This model will produce this waveform. And so when we go to compute the loss, this waveform goes forward to compute these loss metrics. So we know that essentially at some point during backpropagation, we're going to have the derivative of this loss here with respect to the waveform, the derivative of this loss here with respect to the waveform, the derivative of these losses with respect, like everything's going to be with respect to this waveform. And then of course it's going to keep chain ruling back through, but all of them have this common tensor, right? The waveform itself. So kind of looking at it more simply, at some point, all of these losses are going to have to compute d loss d waveform, d loss d waveform, d loss d waveform, right? In the backpropagation for the chain rule. And so what we need to do is, what are the gradient contributions? What is exactly, if we call it out, what's DL1 D out? What's DL2 D out? What's DL3 D out? What are the gradient contributions from each of these losses? So let's start with that. So to do this, the input is exactly that. It's basically the waveform. It's the out in our case, the out. What we want is DL1 D out, DL2 D out, DL3 D out, ... So the input is the out, and so let's go ahead and do that. We're going to do for name loss in losses dot items. So like I mentioned, we're going to be passing them in as a dictionary of something like loss 1, and then there'll have some, loss value, and then it'll be loss 2, and it'll have its own loss value, ... Right? So that's how we're going to pass it in. We'll see how we set that up a little bit later when we actually write the training loop. And then what we're going to do is grad, here we go. We're going to do torch.autograd.grad. So torch.autograd.grad lets me manually compute gradients between something. So I want it between the loss and the input. And we're going to do retain graph is true. And we're going to do allow unused to also be true. Okay, so what this is saying is for remember we have a dictionary of losses, so we're going to loop through each loss one at a time and compute what is the derivative of the loss with respect to the input. So again, this is computing what is the DL1 D out, what's DL2 D out, DL3 D out. That's it. And then we're going to retain the graph so we don't lose that information, so we can parse it right now. And then we're also going to do allow unused is true just in case one of these losses are none. Like if these losses don't have any gradients, it's just a check, and we'll see why we do that. When we write the training loop, it just handles an extra case for us. So if this is none, then essentially this will just return none, and then that's it. There's nothing else there. And we'll check that in a second. This is going to return a couple of things. We only need the grad. And so now we have the gradient with respect to the input. So DL, D input. And what we're going to do now is if grad is not none, so that means, it's valid, we're going to do a couple things. the grad of the loss with respect to the input will be in the shape of the input. So dl, the input, is going to be in the shape of the input. And for us, we already know ahead of time that the input has to be in the shape of batch by 1 by L, because it's, there's a batch size number of samples, there's one channel audio, and the audio has some length of L. So what we're going to do is compare or compute the per sample norm of the grads. So our dims is going to be tuple range 1 to grad dot dim. So this is going to give me all the dimensions, basically just dimensions 1 and 2, right? Just grab all of them. Those are my dims. And then norm is going to be grad dot norm dims. Dim equal dims. So this is going to compute the norm along these dimensions on a per sample basis. So for every single sample individually, go ahead and compute the norm along these. This will of course give me some kind of like, basically this will become a batch by nothing. There'll be nothing there. So that gives me my per sample norm. Now what I want to do is get the average norm across all the batch. So we're going to do norm is equal to norm dot mean. This will of course just be, a single number essentially. And then what we're going to do is store norms for this specific name. We're going to store norm. And then our grads for this specific name, we're going to store that grad tensor from earlier. And that's what we're populating in these two things here. For every single loss, we're going to compute based on its name, like the naming scheme is whatever we want. So we'll see that later. For every single loss, go ahead and compute the norm of the loss and then store the gradient as well. And then what we're going to do is count is equal to len grad. So this is what is the per GPU batch size. So len grad. So grad again is the shape of batch by 1 by L. So len of grad is B. So this just tells me how many samples are in every single one of them. So yeah, this will be the same. So yeah, we'll see that in play in just a second. Otherwise, if there is nothing to do, right, then we're going to do norms. Name is just none. And then grads name is also none. That means there was basically this allow unused got actually triggered, and this grad was none. And so we're just going to store none here as our placeholder. Now that we have that, now for the hard part, we need to do the, essentially we need to keep a running track of the norms. So let's give ourselves an idea here. Go back right here. What we computed is this norm, but we don't actually just use the norm directly. So if I pull up the, let me pull it up EnCodec paper real quick here. So they say we introduce a loss balancer in order to stabilize the training. In particular, the varying scales of the gradients coming from the discriminators. We also find that the balancer makes it easy to reason about the different loss weights, yada, yada, yada. And they define the d loss I, dx hat. So basically the output of the model. So derivative of the loss, the ith loss, if there's I of them, with respect to the output of the model. And this is the exponential moving average of GI over the last training batches. So given a set of weights and some reference norm, in our case, the reference norm is just 1, we define this thing right here. We then backpropagate the network. We'll see all this in practice a little bit later. And they use, R of 1, beta is 0.99, so on and so forth. So we can see that the GI here, we do the exponential moving average of GI, not just the norm itself, but we need to compute the EMA. So let's go ahead and work on that part. So this is essentially, they call it in their implementation, so we'll keep it the same. They create something called the averager. So we're going to do def averager. Okay, and we're going to pick some beta. We know the beta is 0.99, but we'll set it to 1.0 for now as a default. And state is none. The state is something that's not in their implementation. We'll see all that in a second. The idea is that if we're, basically the idea is this. If we're tracking EMA, exponential moving averages, over like your batches, and we're training our model, well, let's say we stop training our model and then want to resume training our model. When we resume again, we should load these values again, right? So basically whatever the EMA was up to that point, we need to reload all of that. And that's exactly what this is. This state is something we'll save and checkpoint during training, and then we can always load from there when we pick up from where we left off. So we're gonna do if state is not none, so if we pass in a state, then we're gonna have two things. We're gonna have something called fix. It's gonna be a default dict float state.get, fix or an empty dictionary if it's not there. It's a base case essentially. And then total is going to be again default dict float state.get float state.get total. There we go. Else fix is going to be our default dict float, and total is default dict float. Basically just start from scratch if we don't have anything. Otherwise, load in my fix and total if I actually have something. And there we go. Okay, so what exactly is fix and total? So fix is essentially the numerator, and total is going to be the denominator of an exponential moving average. I don't know, we could call this numerator and denominator here if we want, but I'm just trying to keep it close to the code that they had, even though I already made changes to it. I'm trying to keep it as similar as I can to what they had. And we're going to write this update method, which is going to take some metrics, and these metrics are essentially what we have right here. It's going to be let me scroll down right here. Here we go. Yeah, so these metrics are going to be exactly what we just computed before. It's going to be these norms right here. So those are my metrics. So we're going to be passing in a dictionary of norms, and that's it. And what we need to do is compute a exponential moving average of these norm values. So these metrics are just those dictionary of norms. They'll have some, essentially again, some name and some norm, and then another name like name2, and then like norm2 ... That's what it'll look like. And so we have, so in Python, this is basically a function inside a function. And so as far as this function is concerned, these variables outside are captured via closure. And that means whenever we do any kind of update or change, basically these are going to contain our EMA values. So in the end, our EMA is going to be, the value we want is going to be fixed divided by total. That's what we want. Or actually, no, sorry, the other way around. It's going to be total divided by fix. That's what we're going to be doing. Total divided by fix. So when we do the updates here, we want to make sure that as we're computing stuff, we're referencing this global variable. So that's why we can use non-local total fix. So this makes sure our total and fix refer to the global variables. So we're always constantly updating this global variable every single time, rather than some local copy of that variable. So if that makes sense, basically these variables are captured by closure. If we update it in here, then the local copy that's made in the closure is updated, rather than the global reference that we have up here. It's just like small annoying things. I'm sure there's better ways of doing this too, but this is fine for now. And what we're going to do is for key value, right? So for every name and norm, in metrics.items, we're going to do if value is not none, of course, because remember we have that base case. If we have a none, then there's really nothing for me to do. If value is not none, then what we're going to do is total key is equal to total key times beta plus, make sure it's float, value. So all we're doing is basically every iteration multiply the existing value by beta and then add the new value on. And in the same way, fix key is equal to fix key times beta plus 1. And so the update normalization is going to be the old value times beta plus 1 for the new value, because this is essentially just a counter. This is just a counter. And so what we're going to do now, this is just a counter of our number of elements. And this is the actual like exponential moving average. If beta is 1, for example, let's just take the easy case. If beta is 1, that means total is always going to be total plus the new value, right? So basically total is going to be, so total 0 is going to be equal to total 0. That's how it's going to start. And then total 1 is going to be equal to total 0 plus new 1, and then total 2 is going to be total 1 plus new 2, ... We're going to repeat that. So basically, the total at every iteration is just the old value plus the new value. And then my denominator is going to be the old sum. So initially, it's going to start as 0, and then it becomes 1, and then 2, and then 3, and then 4. So it's just a simple moving average, or just a simple average at that point. If we do total divided by fix, if beta is 1, then it's just essentially just the sum of the total things divided by the number of things we added together. That's a standard average. If beta is not 1, like 0.999, then it essentially becomes an exponential moving average, but it technically has like a bias correction, right? So this is actually kind of how the Atom Optimizer does it, but it's still just EMA. It's a standard EMA update. And then we can return. For every key, we're going to return the total divided by fix key. If total is not none, else none. For, oh, am I missing one? No, we're good. There we go. Oh, I don't like it. Let me just paste this in. I'm missing a bracket somewhere. I don't want to chase it down. So basically, for every single key, we're going to store the total divided by fix. If the total is not none, else it's none. For key total in total dot items. So there we go. List comprehension. I just always miss a bracket somewhere, so it's fine. And that's it. That's all we need to do. The update method, again, is very simply just EMA, exponential moving averages, on these. And this fix and total are what's going to contain those moving averages across the batches. And when we reinitialize training, if we like stop training and we want to resume from where we left off, we load those original values from the EMA and then just keep going. And that's it. That's as simple as that. There we go. So now that we have that, we need to add a couple more methods. We need a def get state, right? So if we need to save the state, we're going to return essentially fix is going to be dict fix. And then our total is going to be dictionary total. And our def load state, we're going to do non-local fix total. And then we're just going to populate our values. So basically like this. So if we want to just directly load the state, we add these methods. And what's cool in Python is we can actually add methods to methods. So in our update, we can do .get state is equal to get state, because technically update is just a class, right? It's just a class, or it's just an object, and we can assign other objects to objects like this. So we can do update.getState. Basically, we're giving this function additional functionality by assigning it this way, just to keep it simple. And then again, update.loadState is equal to load state. And we're going to return the update method. So this averager is just something that returns the method itself. So it returns a method. And so what we can do now is in our balancer right here, balancer, we can do self.averager. So let's call it right here, self.averager is equal to the averager that we just wrote with the EMA decay, whatever you want. And if the beta is 1, as we have it set by default, then essentially it's not really EMA, it's just standard average. What's the average norm across all the batches? But if we have a beta that's a little bit less than 1, then it becomes an exponential moving average. And that's essentially the entire novelty of this. So now that we have all that, we are very, very close to being done with this, which is good. So we have this. So this, if we do so remember, this self.averager is technically a method, right? It returned our averager right here. When you ran it, when you run averager EMA decay, this function returns the method update that has these additional methods like stuck onto it. And so this is a method, which means this self.averager is a method, which means if we run self.averager and we run it on our norms, this will actually trigger this update method and return this stuff back here. So this self.averager gives me my EMA of the norms up till now. Now here's the second problem. I ran this, but this is on a single GPU, right? So I have my average, my EMA essentially, exponential moving average norms per GPU. What we want is not just per GPU, but across all GPUs, right? So to do that, very simple. We need to write one more metric or one more method, def average metrics. And this is going to take a couple of pieces of information. It's going to take metrics as a dictionary. It's going to take count, which we'll set to 1, and then the accelerator is none by default. So all this is going to do is average a dictionary of metrics across all distributed processes, okay? And for the most part, this isn't very hard, but just a little bit of like nuance essentially. So first, if accelerator is none, or accelerator.num processes is equal to 1, then just return metrics. There's nothing to average if there's only one GPU, or we're not even in distributed training, so we don't care. Otherwise, we now need to unpack the dictionary. So what we have are essentially keys and values. It's going to zip, and we're going to do metrics.item. So we're just going to unpack the dictionary so we get a list of keys, our list of values. And here's the key idea. Our metrics are the following. So what we have essentially are something like this. So let's say our values is a list of numbers like v1, v2, v3, something like that. Let's just say that. And we could have more, right? ... And the count, right? The count is something like this. So the count is how many things do we have? So let's go right here. Count was the batch size, right? The len of grad. So whatever the batch size is what we technically need to sum up and then divide by, right? Basically, what was the batch size on the first GPU, batch size on the second GPU, batch size on the third GPU, so on and so forth. We need to get all those B's, add them together. So this count is on this specific GPU. This was my batch size. But the question is, what was the batch size across all of them? And so this is why we're also going to have, that's why we're passing in the count right here. We're also going to have, additionally, the count. So the count is going to be a single number, and we make it a list, right? So what we're going to do is something like this. We're going to do, our tensor is going to be torch.tensor. We're going to have list values plus count, and then dtype is going to be torch.float32, and device is equal to accelerator.device. Okay? And all this is done is essentially create something like this. Basically, we have the metrics from before, v1, v2, v3, whatever they may be, and we have this count that we just kind of stuck on the end. So we just make one tensor that has all these pieces of information in it. Now, what we want to do is sum across processes. So what we really want is this. GPU 0 has its own v0, v1, v, whatever, and it's count 0. And then GPU 1 has its own. And what we want is the sum of all of them. v01 plus v11, v02 plus v12, v03, v13. And then, of course, count 0 and count 1 to get the total count across both GPUs. And so to do this, very simply, we can do tensor is equal to accelerator.reduce. And this is that reduce sum, just, closed out. Reduce, this is that reduce sum from earlier. We're going to do the tensor, and our reduction is going to be sum, just like that. And that'll go ahead and add them together. And then our averaged values, our final average values, is going to be tensor, everything except for the last thing, because the last thing was, our count. And we're going to divide by tensor minus 1, the last thing. And so that's it. So essentially all we've done is averaged by the count. We added everything together and then divide by the count. And that's essentially it. And then once we're done, we can do .cpu, move it to the CPU, and then .toList, right? Don't need it as a tensor anymore. We just made it a list. So now our final list is still like v1, v2, v3. It's a list of our metrics, but they've now been accumulated and averaged across the GPUs. And that's the important part. And we're going to return back our dictionary of zip keys average. So just go put it back exactly how we did, and we're good to go. So our metrics is back to, it's exactly this again. So it was exactly, I deleted it. By the way, the metrics is back to exactly what it was. It's just a dictionary of key value pairs. And now the values are these averaged across GPUs, so global statistics across GPU values. And that's it, right? Nothing too challenging, just little details, and that's all. I keep saying not challenging. There's like this is a long video, guys. There's so much going on in this architecture. Okay, so now that we have the averager done, we can run the average metrics on the averager. Remember, the averager is going to return the dictionary of key value pairs, but that's per GPU. And then we want to average it across count, and then self.accelerator, right? Self.accelerator tells us everything we need. And these will be their average norms. All right, there we go. All that for this. So the average norms are now global average across all the GPUs gradients, and each one is based on the exponential moving average of all the past batches. And that's essentially it. That's the big idea. All right, so now that we have that, we need to get our actual weighting, right? So what we have are the norms. What we've computed is this denominator here with the exponential moving, right? Beta. Up next, we need to compute the total weights and then the ratio. So our total weight is going to be sum self.weights k for k in average norms dot keys. So our weights, this one right here, is also going to be passed in as a dictionary. And one key thing to keep in mind is whatever names I have for the keys for each weight here has to match the names over here for the losses. So if my losses, if I set it up like loss 1 and it comes in as a loss, and then loss 2, which comes in as a loss ... then my weights also have to be called loss 1 and then its weight, and then loss 2 and then its weight. So basically we need to make sure that the names, the keys of our dictionary match across both the weights matrix, or basically our weights values, and the loss values, how we pass them in. So this is just doing that, loop through all the keys, and then grab their corresponding weights right here. And then our ratios is just going to be, and of course sum, this is basically the denominator. So this is the denominator right here, just sum them all together, and then just for every term, divide by that denominator. And that gives us our actual ratios. So K, W, divided by total weights for KW in self.weights.items. That's going to be our ratios. So now we have essentially the ratio of gradient contribution. This means like if we're looking at this one right here, if it's 1 to 2 to 1, then the first one should have 1/4 the contribution. Second one should have 2/4 or 1/2 the contribution. Third one should have 1/4 the contribution. So those are my ratios. Now it's time to init our grad. So we're going to outgrad is going to start out as 0. Of course, we already have grads. Those are these grads right here. So we already have grads, but we essentially will re-weight the grads and add them together. So we're going to do for name average norm in average norm dot items. So for every single one of these norms, we're going to rescale them. So what we're going to do is scale is going to be ratios name. That's going to be what is the ratio for this specific thing times self.total norm, which is default to 1 in our implementation and what they said in the paper, divided by self.epsilon plus average norm. So this makes sure we don't divide by 0, but all we're really doing is the total norm divided by the average norm times the ratio. And that's exactly what we have right here. We have our total norm divided by the average norm, right? Total norm divided by the average norm, and then the ratios, and then the ratio. So let me actually paste this little snippet in because it might make it a little bit clearer of what's going on. So here, I typed this out. Here we go. So basically what we've done is we have 4 different losses, L1 through L4, and each of those losses have a corresponding weight, W1, W2, W3, W4. And of course, each of those losses have their gradient contribution, DL, DL1, DL out, DL2, D out, DL3 out, DL4, D out, so on and so forth. And so what we did is first we computed our norms for each one of them. That was this line right here, compute the norms for each of those losses, compute the norm. After we computed the norm, we get the EMA of the norm, so it stabilizes across batches rather than having it like jitter and change really fast between batches, especially at the beginning of training when the model doesn't know anything. After that, we get our ratios for each one of them, and we make sure that these ratios sum to 1, of course. And then what we do is our current norm is this average. For example, if we have average norm 1, that's what we have right now. Average norm I is the current norm. What we would like it to be is the ratio I times the total norm. We want the effective norm to be based on the ratio, right? So if my weights were 1, 2, 3, 4, then it should be the ratio. The first one should be 1 over 1 plus 2 plus 3 plus 4 of the total norm. The second one should be 2 over 1 plus 2 plus 3 plus 4 over the total norm, so on and so forth. We just want the ratios to match. And so if this is what I want, and this is what I have, then if I multiply by the scale factor of ratio I times total norm divided by the average norm I, if I multiply that by my grad, then that gets me exactly what I need. That's my scale factor that I need to scale by. And so this is exactly what we have right here. Ratio I times total norm divided by the average norm. Is that not exactly what we have here? We have the ratio, we have a total norm, and we have our average norm, right? That's the EMA average norm. And that's it, right? So we're essentially just implementing this very simply. And then we take the grad that we had and just rescale it by that scaling factor. So the norm gets scaled in exactly the same way. So let's go ahead and do that. So we're going to do exactly that. We have our ratios times that total norm, which again is for us just set to 1 because we don't need to scale it past that. So we're going to make sure that we want the effective norm, the total norm of our gradients, to be 1. And this makes sense because we also do clip grad norm, right, when we train our model, but we're essentially forcing the total gradient of the norm to be 1. So there's really no clip grad norm anymore, but that's fine. So that's what it is. And then we divide by the average norm, and that gives us exactly what we need. That's our scale for this one. And so then what we're going to do is, and this is a super important idea, and this actually wasn't in the original implementation, so I'm not exactly sure why, so I added it in just in case. But essentially, what if the scale is super big? Or what if the scale is super small? So just in case of extreme values, and I noticed this happening at the beginning of training. So this instability occurs at the beginning of training. Sometimes I notice that the scale becomes extremely big or small, like in the hundreds of thousands or like in the 1 over hundreds of thousands. So what I've done is we're just going to clip it. We're going to clip them between some reasonable numbers. These numbers seem to work fine for me. We could probably go a little bit higher and a little bit lower on this, but it's fine. So what we're going to do is our scale is fine. The scale is like technically correct, but at the beginning of training, because of potential issues, we're going to just go ahead and do self.min scale, min scale, self.max scale. So all we're doing is just clipping. We're making sure this scale is no bigger than the max scale and no smaller than the min scale, just in case. At the beginning of training, this just seems to help. And if grad's name is not none, so as long as there's actually grads here, we're going to do grad is equal to grad's name times the scale, and we're going to do outgrad plus equals grad. So what we've done is we've rescaled the gradients, and now we're accumulating into this outgrad variable those gradients, and that's all we need to do here. Okay. So yeah, I keep saying there's just like a lot of stuff in this architecture. So I was a little bit hesitant about even making a video on this because it's just so complicated, but that's fine. We are here for fun, so it's no big deal. So if accelerator is none, so if we're not using accelerator, then we can just go ahead and do our input dot backward. So here's another key idea. We have essentially done this. We have gone ahead. Our outgrad is the derivative of the loss, all the different losses with respect to this output, which means this computation right here, where is it? This one right here. All of this has been done. We've accumulated, right? We added on those gradient contributions from the different losses, but we've also rescaled them accordingly. So they're kind of following this ratio as close as possible. And so we've done that. But of course, all we've really done is this. We've done the derivative of all these different losses here with respect to this here. But of course, we need to continue backprop. We need the derivative to keep going to the rest of the architecture, which we haven't done yet. And so what we need to do is manually trigger that here. So if the accelerator is none, so we're not using accelerator, we can do input.backward. So that's basically the waveform.backward. So rather than loss.backward, we're doing the waveform because we already have all the gradients up to waveform. But if we just do input.backward, we need to provide it the outgrad. Basically, what is the upstream gradient? So I'm starting from input. So basically what's the gradient up to input? Well, we've already done that. With the gradient up to here, we've accumulated. And now that we're here, we'll do this thing dot backwards with that upstream gradient so it can compute the rest of the backward pass for us. So input.backward, outgrad. And we're going to do retain graph equals retain graph. It's as simple as that. Otherwise, if we're using the accelerator, it's the same idea. Self.accelerator.backward loss is the input. It's not really the loss, but backprop has to start at the input. The gradient is going to be the outgrad, and retain graph is equal to retain graph. And that will essentially trigger the backward pass for the rest of the model. So again, the key idea is we get some losses. We compute the gradient contribution of each of those losses. We go ahead and do an EMA of the norms of those gradient contributions, and then average those EMAs across all the GPUs. We then go ahead and compute what is the gradient, what is my wanted gradient contribution. Each of these losses should have some ratio of contribution that I'd like it to have. And then what I do is I just loop through all of my losses, all my gradients, and then I just reweight the gradients here by some scale factor that will essentially just reweight the norm of my final gradients, and then I accumulate them into my output grad. And this essentially does the accumulation of D losses with respect to the output. But now that I'm there, I have my upstream gradient, outgrad, so I do input.backwards to continue chain rule, continue backpropagating through the rest of the model. Or if using accelerate, then we can do the accelerate method, and that's also fine. And so all we have left is writing our def state dict self return averager state. It's going to be self.averager.get state, basically the method we wrote earlier, and then def load state self state dict. It's going to be self.averager.load state, just accessing those methods from earlier, state dict averager state. And that's it, right? So that's the loss balancer. Keep saying that's it. There's like a lot of stuff going on here, obviously, but yes. So that's the main idea behind the loss balancer. Okay, now we need to write, here, I need to delete this one so we can start that over. So we need to write a dataset class, of course. So now we're actually getting to the training script. So we're home stretch now. So we're going to do import torch audio. We need from torch.utils.data, import the dataset, and we're going to import warnings, and then we're going to do warnings.filter warnings. Ignore. There's like a warning about like torch codec versus like some other, basically something about reading the audio files that we don't really care about right now because it's just a deprecation warning. So audio dataset. This dataset's very simple. All we're going to do is provide a list of audio paths. So let me just double check that that's actually what we do here. So in our trainer, audio dataset, here we go. Yeah, so we're going to basically pass it a list of audio paths. And based on the audio paths, we're going to go ahead and just load the audios. Very simple like that. So we're going to do class audio dataset, def init, self audio paths, segment length. So here's one thing. We have audio of like variable length, but we are not going to use all the audio every time. We need to just pick some segment length. And so in the paper, they pick 1 second. So I know that my audio's sample rate, which I'll set right here as well, sample rate of like the LibreTTS dataset, for example, is 24,000. And they use 1 second segments. Other papers seem to use more, like 48,000 or 72,000, like 3 second segments. But we're going to stick to the paper. So 1 second segments. And so we just have to store self.segment length gth is equal to segment length. Self.sample rate is sample rate, and then self.audio paths is audio paths. There you go. Def len self return len self.audio paths, and then def get item self index. Very simple. All we're going to do is just load the audio. So I'll just copy this in. I don't want to type this. There's nothing here. So all we're going to do is essentially just, here's the path to the audio, load the audio, If my sample rate of the audio doesn't match the sample rate that I want, then I have to go ahead and resample it. This won't affect us because our audio is 24,000, but that's fine. And then what we're gonna do is if we have non-mono audio, I'm assuming mono, you could also do non, like, you know, binary audio, whatever it's called, but, or basically dual channel audio. We don't have that mono, so if we have dual channel, we're gonna go ahead and average. That doesn't really affect us. We can get the duration of the audio, how many samples we have in the waveform, and then if the length of our audio is longer than the segment length, we're good to go, right? Just go ahead and random sample some segment from start to, you know, start plus segment length from the waveform. If our audio is not long enough, it's shorter, then we're just going to go ahead and take the audio and just pad it with zeros up to there, and that's it. So nothing too challenging. Just there's really not a lot going on in this data set. Very simple. And because we're sampling 24,000 things, each sample we grab is of the same size, and because everything's the same size, we don't need to really write any fancy collate functions or anything like that. Okay, now for the trainer. This trainer is a little bit more, maybe involved is not the right word, but yeah, this is actually my research code, so there's a little bit more like modularity to it, so I'm going to try my best to make it as simple as possible. So we're going to write a trainer. And before we write the trainer, we also will create our config. So new folder, configs, and then I'm going to create a new file in here called config.yaml. And this YAML file will look like this. It has all of our configurations just stored in it. So we have this trainer, that's fine. The run name, so this is for Hugging Face stuff if we want a run name or not. We have the working directory, which I can also go ahead and create workdir. Okay. And there's two ways to do it. We can either pass in a text file with the train test split, and I can actually copy that from my original one. So let's do, here, let me just go here, analysis, NCSA, PyTorch for audio, and Codec. And we have our data here, which is just this train text file. So we can copy this folder and put it right here, just so we have it. Okay. So yeah, we have our data, you know, what training file. So all I've done, just to make this clear, is like I have a path to every single one of the audio files that I want. So you can set it up the same way for your own audio files. So there we go. We have our sampling rate, segment length. When we do the MEL spectrograms, we have how many MELs do we want? They use 80. Actually, I think they use 64 in the paper, which is weird because it's normally 80 for most papers. So I just set it to 80. We have training iterations, warm-up iterations, checkpoint iterations, eval iterations, generations. Every 2,000 iterations, I'd like to generate something so I can listen to it. We have our per GPU batch size, num workers, pin memory, all the standard stuff, our logging related stuff, our optimizer related stuff. This is important, so we'll talk about that in just a second when we actually get there. We have our loss weights, so we can see this is the loss weights that we use, whether or not we want to use the balancer, how many samples we'd like to reconstruct as we're training. We have the config for the generator, so this is basically the EnCodec config, and then we have our discriminators config, but of course, we don't really care about the these two things here because we're not going to be using them. So these are set to false by default, so we don't really care about them. We're only going to stick to the multiscale frequency discriminators. That was what was a part of the paper, right? Everything else is just extras that I added in just out of curiosity. Okay, so let's go ahead and just start working on this trainer. The goal is basically to write a trainer and then do trainer.train, right? So basically that's what we want. So that's how we're going to set it up. I'm going to go ahead and copy all of the imports in just like that from loss. Oh yeah, so we haven't written our losses yet. Yeah, maybe we should actually do that first. Let's write our losses real quick. So new file, loss.py. Let's just go ahead and write them, get them out of the way. Losses are pretty straightforward. There's a couple of losses that we need. We have essentially a MEL spectrogram loss, and we have our generator loss, and we have our discriminator loss. So let's start with the MEL spectrogram loss. Import torch torch.nn as nn, import torch.nn.functional as f, and then from librosa.filters import MEL as librosa MEL function. So this first one, class audio to MEL, is essentially just, we've actually wrote this something very similar for hi-fi GAN. And so it's just a method that's going to take audio and convert it to MEL spectrograms. That's all. So just give them some audio, we'll make some MEL spectrograms, and this is the default configuration, the FFT, hop length, window length, sampling rate, stuff like that. This is different from the other ones. So in our discriminator, we also create spectrograms. So let's kind of look at this again. In the discriminator, we have spectrograms of different sizes, right? So the spectrogram is going to look at, again, different scales of our audio, so different window sizes. We additionally have this MEL spectrogram loss specifically, where we only compare the loss, basically do like mean squared error or whatever, between the input's MEL spectrogram and the generator's MEL spectrogram. So we have a couple of different things going on here. So this one, what we're computing is basically this loss that you see right here. So let's go ahead and do that. We're going to do our window, or super.init, and our window is going to be torch.standard Han window, should be fine. Win length device equals device dot float, and then our MEL basis. So remember, the MEL spectrogram is simply a projection of the original spectrogram. So all we need to do is create that projection matrix, and we can get that with this Labrosa MEL function, basically MEL. It produces a matrix of basically num FFTs by the num MEL channel. So it'd be like a 513, because it's 1024 divided by 2, by 80 matrix right here to go ahead and convert spectrograms to MEL spectrograms, because it's simply just a projection matrix. And then we can do MEL basis is equal to torch.from numpy MEL basis dot CUDA dot float. And that's fine for now. And we're going to do self.register buffer MEL basis. It'll be stored as MEL basis. Self.register buffer window, and store that window as well. And then we can go ahead and store the rest of these variables just so we can access them, right? There we go. And so in our forward method, forward self x, our shape, let's just go and do that, shape is equal to x.shape, and we're going to do if len shape is greater than 2. So if we have more than one channel, then we'll run the analysis per channel, but this doesn't actually apply to the mono audio case. So what we're going to do is x is equal to x.reshape shape 0 times shape 1 by -1. Basically flatten all the other dimensions and then just keep the last one. In our case, it's just 3 dimensions, so this should be fine. And then what we're going to do is our reflect padding. So remember that our MEL spectrogram, we want to have even windows. Basically, we want our MEL spectrogram to cover the entire audio and not just like a part of it. It might kind of miss out on the last couple samples if we don't pad it. So we can just compute that padding. The padding's pretty easy. It's just the window size. It's going to be self.nFFT or window size, whatever, minus self.hop length divided by 2. And if we do our audio is equal to f.pad x, and we're going to just add that little bit of padding on each side, and we'll do reflect padding so we don't add additional frequencies, then that's essentially it, right? So we just add a little bit of padding on each side of the audio, and this makes sure that we have complete windows and there's like no missing samples or anything like that. So keeping it simple. Then we can run our FFT. FFT is very simply just our torch.stft audio, and FFT is equal to self. We could have also used torch audio as FFT. It doesn't really matter. I'm not even going to type this because I don't want to. I will just paste it right here. There you go. So this is our FFT, right? So we did our short time Fourier transform. Now what we're going to do is, of course, this is standard STFT. We need to go ahead and convert it to a MEL spectrogram. So MEL output is going to be, like I mentioned, torch.matmul. The MEL spectrogram is simply just a projection of the original spectrogram. So MEL basis, it's like a log projection, not a linear projection, but that's fine. Torch.sum, torch.pow. Actually, no, technically it is linear projection. But those the weights are created by a, basically like a log law, essentially. So we go ahead. So first of all, we take the FFT. Remember, the FFT is going to come out as, real and imaginary. So they're going to be imaginary numbers. So if we just square it and then add it together along the last dimension. This will essentially go ahead and get the real ones. We could have also just done torch.abs, right? But this is just mean squared, right? So we just, or not mean squared, but we square the corresponding real and imaginary terms, add them together along that dimension, and that will give us essentially the magnitude. So we have the magnitude here. We could have also used torch.abs, and that would have given us the same result. But I'm trying to keep it to the code that they had done here. And then we take this matrix and we map mul it with the MEL basis, basically our projection matrix that projects our spectrogram to a MEL spectrogram. So now we have a MEL spectrogram. But the MEL spectrogram on its own is not as helpful. So what we're going to do is basically convert it to log by converting to decibels, essentially. So spec is going to be torch.log. We ignore the 20 for the decibel computation. And we're going to do torch.clamp and just do MEL output. And min equals 1e minus 5. So we just don't have too big of the values. And there we go. Very simple. So all we do, compute our real values. We're going to torch.abs, project to a MEL spectrogram by mapmulling it with the MEL basis, and then just take its log, and that will give us our log MEL spectrograms that we can actually visualize. And then again, if len shape is greater than 2, then we're going to do log MEL spec is equal to log MEL spec dot reshape shape 0, shape 1, negative 1. So we put these two dimensions here together if there was more than 2 of them. Now we're going to just separate them back out again because we don't want them together. And we can then return log MEL spec. And that's basically it. So that is an audio to MEL. This is basically a simplified version of the same thing we wrote in the hi-fi GAN implementation. So yeah, just keep that in mind, but that's fine. And so let's go ahead and do the generator loss. So def generator loss. All right. So, and actually, should I do the generator loss first? Maybe let's do the discriminator loss first. So let's look here. Our discriminator loss is basically we want to update the discriminator such that we fool the, we can identify what's real and fake. So let's actually do the discriminator loss first just for simplicity. So def discriminator loss, and we're going to pass in logits real and logits fake. All right, we're going to pass in these. And remember when we do this, if we look at our discriminator, that's what these are. Basically the real outs and the gen outs, these are going to be a list of tensors, right? These are a list of tensors. So let's just look at a single example. I know I have all of them in here, but let's just look at the one. Here we go. Our z here is from a single one. And then in the multiscale case, we basically have real outs and gen outs, and it's basically a list of these tensors. The real feature maps and gen feature maps are going to be a list, but each of the inside thing is also a list. So it's going to be a list of tensors, and we'll deal with that later. But for now, all we have is this and this. So basically, the discriminator produces a real outs and a gens outs. And we want it to predict which one is real and which one is fake based on these logits, right? Based on these raw outputs of the model. So to do that, it's relatively straightforward. They use the hinge loss here, as most of these architectures are doing these days. So that's fine. So real logits, logits real, logits fake. Our disk loss will initialize it as 0. And for loss real, or logits real, logits fake, in zip, logits real, logits fake, we're going to do our disk loss is going to be equal to the disk loss plus torch.mean f.relu 1 minus L real. And then we're going to do plus, I'll just put this all on here, plus torch.mean f.relu 1 minus L fake. This is actually the hinge loss. So if you're not familiar with this, I talked about it in one of my previous videos in depth, but let's just kind of briefly discuss it again. We want to minimize this loss. So if I want, what's the minimum that ReLU can be? ReLU is smallest when ReLU is 0. Like the minimum ReLU can be is 0. And if the minimum is 0 for ReLU, that means we know that ReLU can only be 0 if it's less than 0. That means we need 1 minus L real to be less than 0. So we want L real to be greater than 1. If L real is greater than 1, then 1 minus L real will be less than 0, and then f.relu will be 0. In the same way, if we want this to be less than 0, then we want L fake to be less than 1. If L fake is less than 1, then 1 minus, or 1 plus L fake, or I guess not less than 1, but less than -1, sorry, less than -1. If L fake is less than -1, then 1 minus anything less than -1 will also be 0, and then this will be 0. So the hinge loss is essentially incentivizing for the logits of the real images or real audios to be greater than 1, and the logits of the fake ones to be less than -1. So that's why it's called standard hinge loss. It's like the same one they use in support vector machines. And so then the disk loss is going to be disk loss divided by len logits real. Just go ahead and average it up, right? So average however many things we had in here. So remember there, if we have 5 discriminators, because we have multi-scale, so at different scales we have our looking at our discriminator config again, we see we have 1, 2, 3, 4, 5 separate discriminators right here. And so what we've done is we computed, the loss for each one of them individually, and now we just divide by 5 to like average them up across all of them. And there we go. That's our disk loss, and we can return disk loss. So that's our discriminator loss. Nothing too bad. Now for the generator loss. This is a little bit more involved. I promise this is the last annoyingly annoying thing that we need to do. We're going to pass an fmap real, and I'm going to just copy this again. Here we go. So this is going to be a list of tensors. Logits fake is going to be a list of tensors, and then input waves, output waves, sample rate, and nummels. So this says that we have k different discriminators, and each discriminator has L layers each. We can verify this because we remember from right here, in a single discriminator, right? A single discriminator, we loop through, and every single layer we append the output. We store Z from every single one of these post activations in these layers. And so basically this fmap has a list of tensors, and the number of tensors is just the number of layers in that specific discriminator. But then we have multiple discriminators, so we're going to have real feet maps. We're going to append on another list. So if we have 5 discriminators, that means the length of real feet maps is 5, and each list inside this one, so because it's a list of lists, will have however many layers that specific discriminator had. And so in this case, we can go back right here, and that's all it is, right? So there we go. We have our logits fake because we want to make sure that our, and we'll see that in just a second. So let's just actually keep going and we'll see. So first, we have a time domain loss. So if we look right here, we have the loss T. That's the time domain loss between the original audio and the generated audio. So let's go ahead and do that first. Time loss is equal to f.l1 loss, input wave, and the output wave. So this is the input audio that went into the model. This is what was reconstructed on the other end, and we're just doing the L1 loss between them. Now what we have is the frequency domain loss. So here is the main idea. We don't really know, just like before, we don't really know what window hop size combination is good. Like which window size is good to analyze the differences between these. It could be that at the beginning, the model's getting good time domain representations, but the frequency is all over the place. And maybe later on, the frequency domain's good and the time is bad. And how we handle that is dependent on the window, right? Because the larger the window, the better your time, or the larger the window, the more poor your time resolution, but better your frequency resolution, and then vice versa. And so what we're going to do is instead of trying one of them, we're just going to try all of them. So again, the idea is basically from uncertainty principle, larger windows give better frequency resolution and poor time resolution. Small windows are exactly the opposite. So let's just do a bunch of them and add them together. So that's not too much novelty other than that. So frequency loss is 0.0 for I in range 5 to 12. And so 5 to 12 basically means we're going to go from 2 to the power 5 all the way to 2 to the power 11. So we're going to try a bunch of them. So that means we're going to try window sizes from 32 all the way up to 2048. So those are the ranges that we're trying. Our window size is going to be 2 to the power I. Our hop size is kind of up to you. You can either do window size divided by 2 or divided by 4. Either one should work just fine. Typically, I've been seeing 4 being used a lot more in these kinds of architectures than 2. So technically, all you need is half the window size as your hop size for like good reconstruction for overlap add and things like that. But they seem to be doing 4 these days, so we're going to go with 4. And so then our FFT is going to be the audio to mel. It's going to be N FFT. I'm going to paste this in, so I have to type it in. So, we're going to define that audio to mel and then actually do the that's our FFT method. And this FFT method, of course, has a forward function. So our input mel is equal to FFT input wave, and our output mel is going to be FFT our output wave. So all we've done is we've applied a Fourier transform, the short-time Fourier transform, at different time resolutions to the same input and output. And now what we want is the frequency loss. So the frequency loss is equal to the frequency loss plus f dot L1 loss of the input mel and the output mel plus f dot MSE loss of the same thing, the input mel and the output mel. So in their paper, they decided to do both in the frequency loss. They decided to do both the L1 and the L2 loss at the same time. I'm not totally sure why. Like, we could have also probably done Huber and gotten similar results, but it's fine. We're sticking to the paper, so this is no problem. So this is the loss. And basically, again, we start the frequency loss at 0. Try applying Fourier transforms, short-time Fourier transforms, basically the conversion to Mel spectrograms at different time resolutions, so different window sizes, and then compare the L1 and L2 losses of the input audio and the generated output audio. And we, of course, want to minimize this because good generations of audio should be good in both the time domain, so the time domain representation should be similar, but the frequency domain representation should also be similar. Because if both of them are not the same, then something is missing, right? So there we go. That is that loss. Okay, up next, our feature map loss. So this has more to do with, I actually don't know if they show this in the figure. Yeah, I don't think so. But this, they talk about it in the paper, so I'll just show it right here. Multi-band training, discriminator loss, reconstruction, feature, here. We additionally include a relative feature matching loss for the generator, right? So formally, where the mean is computed all dimensions, dk's are the discriminator, L is the number of layers in the discriminator. The discriminators are trained to minimize the hinge loss adversarial function, yada, yada, yada. So yeah, I guess they just briefly give, maybe there's another line in it somewhere about it, but they just say it here. So feature matching loss is essentially the discriminator has gotten very good at identifying what's real and what's fake. I mean, that's essentially what the discriminator should be able to do. And so what we want to make sure we do is that the features extracted for generated, so whatever the features the discriminator extracts for the generated audio, should be similar to the features for the original audio, because this is a good feature extractor. So let's go ahead and do that. We're going to do if fmap real is, and I'll copy this in so I don't have to type this long line. We're just having this toggle here just in case fmap real and fmap fake are none, because I test the model once without any discriminator, so we can hear that. But yeah, so if these things are not none, which they won't be when we train, then k is equal to len logits fake, and L is equal to len fmap fake 0. So remember, k is the number of discriminators, and L is the number of layers inside one of those discriminators, because fmap fake is a list of lists. So our generator loss is 0.0. And this is going to be standard generator loss. So basically, if we look back at our discriminator loss, the goal of the discriminator loss was to discriminate between the two, right? We need to update the discriminator such that we make our reals greater than 1 and our fakes less than -1. But our generator loss should be exactly the opposite. So we're going to do for L fake in logits fake. Generator loss is equal to the generator loss plus torch.mean f.relu 1 minus L fake. That is exactly before we had 1 plus L fake. Now we have 1 minus L fake, because it has to go in the opposite direction. We want our generator to update in the direction that makes L fake move in the same direction that the discriminator makes a thing. So basically we're treating the fake here, as the real because they need to be opposite of each other. So where the discriminator wants L real to be less than 1 and L fake to be greater than -1, we update our generator such that we make L fake also greater than 1. So basically L fake is being treated like the real in this case, because of course the generator is trying to fool the discriminator, right? So it needs to move in the opposite direction. We just add those up, and then we do the generator loss is the generator loss divided by k. Just average them up for everything. And then we have our feature loss. So feature loss is also 0.0, and we're due for f reals, f fakes in zip, f map real, f map fake. So that's the outer list. So looping through our different discriminators, and in each discriminator, we of course have many layers. So for f real, f fake, in zip, f reals, f fakes, right? So now we're looping through those inner lists of this, f fakes, looping through those inner lists. What we're going to do is basically we're going to normalize by mean. And so so what we're going to do is essentially this. We're going to do our feature loss. It's going to be the feature loss plus f dot L1 loss f real f fake. So what we're doing here is essentially we're comparing the feature outputs. Remember, so we have a discriminator and it has a layer 1, and then it has a layer 2, then it has layer 3, ... And each of these layers are good feature extractors. So we want to make sure that the features extracted for real images are similar, or sorry, I keep saying images, but the features extracted for real audios are similar in the features extracted for the fake audios, right? That's all we want. So that's all we're trying to do here. Just trying to make sure that the features extracted are similar. And that's all it is. So you can look at like LPIPs and stuff. They all kind of do exactly this exact same thing, except LPIPs is pre-trained and this is kind of being trained in real time. So that's kind of cool. One problem with this though is some layers, like some of these layers may output values with large magnitudes. If there's large magnitudes, then some layers will dominate the loss and others won't. So just to rescale, they add this extra term on right here, just divide by the mean, absolute mean of the f real, just to divide and just so we can rescale. And so large layers with large magnitudes don't dominate. That's all. Okay. And then our feature loss is equal to feature loss divided by k times L, because you have k discriminators, each with L layers. So there's k things here and then internally L of them here, and that's it. Otherwise, if for some reason we don't pass in anything, that's also fine, and we'll have this as a test case. We just go ahead and initialize, just create losses of 0 as placeholders, right? So we just have something. And then we can go ahead and return this. The naming scheme is important here because when we define our weights a little bit later, we have to use the exact same keys here for the balancer. But that's it, right? That is our entire set of loss functions. So yeah, that's everything we need for the losses. So now let's go ahead and write our trainer. So we've gone ahead, loaded everything in here. We now have this. We also need to write this big, there's always another thing. Okay, 1 second. Let's quickly write these utils. I'm just going to paste these in because there's nothing interesting about them. New file, utils.py. There we go. So this is a quick method. Given some paths to some audios, it will go ahead and load the audios by load them, resample them, make sure it's single channel, add a batch dimension, append, and just store them. And to save audio, same thing. Given some waveforms and some output paths, just go ahead, loop through them one at a time, and then use torch audio save method to just go ahead and save the audios. And that's it. So I'm just gonna, that I don't really need to go into much more depth than that. Okay, now for the trainer. I'm going to go ahead and load all of this stuff. I'm going to copy paste all of this stuff in that is very boilerplate stuff. Okay. Yeah, I can actually copy all of this in. So there is nothing of interest. It seems like a lot. There's nothing going on here. Basically, this EnCodec trainer that we're writing we're going to pass in a generator, a discriminator, and the training configuration. And all we're going to do is basically that training config is that YAML file that we briefly took a look at earlier. It's just this YAML file. So this has all of the training configuration information, that sort of stuff. And so we're just getting that information from the YAML file, and I just set some defaults, reasonable defaults here. So like I mentioned, this code is a little bit more involved than my standard like tutorials, mostly because this is like my actual research code rather than just whatever code, but that's fine. So these are my methods. So there we go. So we have all this here. And just in case we set discriminator to none, because I wanted to test what happens without a discriminator, we print out that we're training without a discriminator. Okay, so now let's write, there's a lot of little not annoying, but just boilerplate code. So we're going to go ahead and just keep this simple. Experiment. Here, I'm just going to paste stuff that is not interesting or to do with the training loop because no one wants to see that. So first of all, the path to the experiment is the working directory and the experiment name. That's how I like doing it. I have a quick method here that can go ahead and identify audio files. So it'll essentially loop through a folder and subfolders, rglob, loop through them and find any file that ends with these extensions or any other ones we could add them in, but these are the only ones I typically work with, so that's fine. Loop through, grab all the audio files, and we now have a path to audio files. This is important in case like we don't have a text. As you remember in my config, we have options. We can either pass in a text file with audio paths in it, or we can just give it a path to an audio directory and then have it kind of identify all the audio files. That's what this would do. After that, we have this new method. So I'll just keep pasting these in as we go. It's not interesting. Load paths from text. If we're doing that, just loop through the line and go ahead and just load all those audio paths in, and we're done. And then we have our write list to text. This is just another helper method if we want to take a list of something and just write it in. So there you go. We have a train test split, right? So take in a list, go ahead and split it by some test percentage. This doesn't really matter as we read it from the self anyway. It's passed in the config, so it's fine. So there we go. If we want to do that, that's train test split. We have our get data sets. This will be the last couple main little things. So very simple. There's nothing really, it looks fancy. It's not fancy. Basically, if we pass in a path to the audio directory, then we have to go ahead and like recursively find all the audio files and do a train test split. If we passed in a path to the text file, then there's nothing to do. Just read the files and we're good to go. In the case that we, just because especially if we are loading audio from a directory and do a random train test split, if we stop training and then resume training, we need to make sure that we are using the same train test split every time. So I go ahead and just cache the train and test files to our working directory. Just make another copy of the train and test. And basically when we resume training, it'll resume training with these files in mind. So the train test splits stay identical. And then we have our train set and test set, just our audio data sets that we've already written earlier. We have a count and a run info. So I'll print. So this is just simple. How many parameters are in the model? So parameters and buffers, because we have those RBQ layers and stuff like that. This is just a simple print to print out the training configuration at the top so I can see what's happening. Okay, that's the boring stuff. So train, self, and then resume is false by default. And we can do if not resume. If we're not resuming, then train set and test set is equal to self dot get datasets, right? Like we had earlier. Else, if we're not doing that, then we need to go ahead and load our cached files. So that's why I went ahead and stored the train.txt, test.txt, and that gives us our data sets now. Okay, so now what we're going to do is our data loaders. I can copy this too. This is just a standard data loader that wraps our data sets. So there you go. We have our train set, test set, and we're done. Okay, so what we're going to do is load some audios for inference. So if we're not resuming, so if not resume, it's of course like watching the losses is fine, but just hearing your model and how good the reconstructions are is probably more helpful than just staring at a loss curve. So we want to make sure we grab some. So we're going to do sampled paths is going to be random.sample test set test set dot audio paths K is self.num samples for reconstruction, however many you want. So I'm going to sample K audio paths from all my audio paths, and specifically from the test set, right? So we can see if it's overfitting or something like that. And then we're going to do self.write list to text. We're just going to store these sampled paths os.path, and I'm going to paste this. I don't want to type all this. So just go ahead and sample some, write them to our path, and then get the path to the saved inputs. I will create some gen inputs essentially. As it's training, we're going to store stuff in here. And then I make that directory so we can store generations in there as we're going. And then what we're going to do is we're going to do for I path and enumerate sampled paths. Here we go. What we want to do is just make a copy for easy access later. So what we're going to do is just create a new folder. So we're going to do for, so basically this gen inputs, for example, is where we're going to store the original audios, like the original input audios. And then as we're training, we're going to store like, after 1,000 iterations, what were the reconstructed audios? After 5,000 iterations, what are the reconstructed audio? So this is where we're just going to save our initial inputs, and we're just going to copy them in. So I can also just paste that in. Just keep it simple. There we go. So let's go ahead, grab the audio files, rename them to like gen I with that extension, whatever they are, and then just copy them from the original file, wherever they're originally stored, to my new directory in my working directory. That's all. Else sampled paths is going to be, again, I have created a file called samples.txt that has the path to exactly those files that I want. And so if I'm resuming, then I can just go ahead and load those files just like that. And our cached audios, we can use that load audio method that we pasted in from our utils, right? So again, utils, we just give it the paths and the sampling rate, and it'll go ahead and load some audios for us. Now for the actual training part. So you can see there's just a lot of like things. So optimizer is equal to torch.optim.atom. And it's going to be P for P and self dot generator dot parameters. If P dot requires grad, and then learning rate is self dot learning rate generator. There we go. So let's go ahead. That's our optimizer. And of course, we have our optimizer for the model. That's the generator. But if we have a discriminator, then we optionally have our disk optimizer. By default, it's going to be set to none. But if self.discriminator is not none, so if we actually have a discriminator, then our disk optimizer will be exactly the same thing. So I'll just copy it in. Same thing, but it'll be on the parameters of the discriminator. We need a scheduler, right? So that's our standard training scheduler. We use cosine because that's what the paper used as well. So the cosine scheduler with a warm-up on the optimizer. And we have how many steps we have scaled up by num processes, and then how many iterations we have scaled up by num processes, because if we have 5 GPUs, then every one is going to like do 5 steps. And so we want to make sure we have enough steps to do everything. So there you go. That's our scheduler. And similarly, we have our scheduler for the for our optimizer, for our main model, but we're also going to have a scheduler for our discriminator, which again, by default will be else. Oh, I need to tab all of you back by 1. There we go. Yeah. So we have our discriminator, and then we have the scheduler for the main model, and then we have the scheduler in the same way for the discriminator, and that's it. After this, we have to do our like prepare for everything. So this is just all of this stuff. Nothing that interesting. So go ahead, just prepare generator, optimizer, scheduler, train loader, test loader, discriminator, disk optimizer, disk scheduler. And so we're going to go ahead, pass it all through my accelerator.prepare, and that gets everything ready here. Now for the important part, remember the weights is going to be equal to, it's going to be our time loss. And we want to make sure the naming is the same. So it's self.time loss lambda, and then we have our frequency loss. It's going to be self.frequency loss lambda. We have our generator loss is going to be self.generator loss lambda, and then finally we have our feature loss, self.feature loss lambda. So these are the weights, and we want to make sure these weights here match, basically the keys here match what we had right here, time frequency generator, because that's what the balancer is going to be doing, right? The balancer needs to make sure that the keys of the weights are the same as the keys of the losses, otherwise it becomes complicated. If self.discriminator is none, then our weights generator loss is going to be 0. So if we're not doing a discriminator, then there's no need to have any weight here. So we're just going to remove them. 0.0 weights, our feature weights, feature loss is also equal to 0.0. So that's going to go ahead. If there's no discriminator, all losses involved with the discriminator should disappear. And so without the discriminator, all we really have is a time loss and the frequency loss, right? And none of the other stuff. If self.use balancer, so if we're using the balancer, then our balancer is equal to the balancer weights equals weights, and accelerator is equal to self.accelerator. We'll leave everything else as the default because that's what the paper used. If we're resuming from checkpoint, this is pretty easy, so I'll just paste this in. The last checkpoint is just going to be whatever the last thing was. So I like I mentioned before, I like saving checkpoints as like checkpoint underscore iteration, right? Like however it may be. So we go ahead and just sort all the checkpoints as long as checkpoint underscore is in it, and then grab the one that has the max value, go ahead and get the path to that, and then we can use accelerator.loadState to load the accelerator stuff. But we additionally, if we're using the balancer, we need to load the balancer as well. So I'm going to be storing some balancer state.bin. Let's go ahead and use torch.load to actually load this bin file. And then I can do balancer.loadState. This is going to trigger, right, these methods right here, balancer.loadState. It'll trigger this method and actually load my running averages into my averager, and we'll be good to go. So there you go. And then completed step is, however many that is. Otherwise, it's just 0 because we're starting from scratch. And now I can go ahead and print my run info, so I can get some print at the top. I can initialize some logs that I can populate as I train. And now we can do our actual training loop. Oh, there's so much going on. While train. I did not think this video would be this long. I thought it'd go way quicker. For waveforms. In train loader. So we're going to loop through. Remember, this thing only returns waveforms, and this is going to be the shape of batch by 1 by, in our case, 24,000, because we want 1 second of audio, so we said our segment length was 24,000. Waveforms is equal to waveforms.to self.accelerator.device. Put on the correct GPU. Optimizer. So let's split this up. We have a generator step. Let's do that first. Optimizer.zeroGrad set to none equals true. And then what we're going to do is if self.discriminator is not none, right? So if we have that, then we're going to do logits real, logits fake. Oh, whoops, I missed a step. So we did that, then we do our output is equal to self.generator waveforms. So yeah, so we go ahead, zero out the gradients of the model, and then go ahead and actually get our output. And this output should be essentially hopefully a good reconstruction of the waveform. And so if we take a quick look at our EnCodec model, which is what we're forwarding through, we just ran the forward method right here, and we get this encoded out quantizer loss, and then the decoded. And so the decoded is my reconstruction. So it's what's on the other end of the model. And so to grab it, so we have essentially, if we are doing this, then we can just go ahead and do this. If the discriminator is not none, into the discriminator, we're going to pass in the waveform and the decoded outputs, right? This is the real, this is the fake. And from that, we'll get the logits real, logits fake, feature map real, feature map fake. Otherwise, all of this stuff is just none because we don't have any kind of discriminator. And then our losses is going to be equal to the generator loss. And I'll just paste this in. So this is the generator loss that we already wrote right here, right? Basically pass in all of this stuff. So that's what we're doing. We're passing in all this stuff. The output decoded is again our reconstruction, the sampling rate, number of mels, that sort of stuff. And now here's the choice. If not, self.use balancer, if we don't want to use the balancer, then our total loss is simply just the weighted sum of the losses. So it'll be the weighted time loss times loss times time loss, weighted frequency loss, frequency loss, so on and so forth. We also additionally have our optimizer quantizer loss. Remember, we still have our commitment loss from earlier. So in our losses, or not in our losses, in our EnCodec model, we return the quantizer loss, which is the commitment loss from our quantizer. And so that piece is still there, and that happens separately. So we're going to do all of this stuff plus the quantizer loss lambda times the output quantizer loss. And then we do backwards, and we're done. Otherwise, we're going to have to actually do something like this. These four losses here are balanced with the loss balancer. So remember, if we go here, all the losses that kind of this thing contributed to, we balance and then backprop. But then the commitment loss actually comes from here, right? It comes from the output of the encoder. So if we go back right here, the commitment loss actually only affects this part right here. It has nothing to do with anything afterwards, which means we need to first do the loss balancer here and then do the commitment loss portion separately. And that's the way they implement it as well. They basically do two different backward passes. So what we do is balancer.backward losses, output decoded. That was the input essentially. And what we're going to do is retain graph as true. The reason we need to retain them here is because we're about to call a second backward pass. And that's going to be this. We're going to accelerate.backward the quantizer loss lambda times the output quantizer loss. So this one is going to basically what's happening is the first one's going to compute the derivative, rescale all the gradients for this specific up to this here, and then the backward will update everything behind that. And then if we don't do retain grad, we need to keep these gradients because we're about to call a second backward pass specifically on this here, which has more to do with our commitment loss. That has to do with the commitment loss. So we need to update that as well. So we have essentially two different backwards. One backwards that goes here, rescales, and then backwards to the rest of them. And the second one that just does this last, this beginning part right here. And so that's why we have two different ones. And if you try to run two backward passes in a row and don't do this and have the retain graph, then PyTorch will throw an error saying like, hey, you're trying to double backwards, and we don't like that. So there we go. So if we're doing the balancer, that's how we're going to do it. Of course, we need to do some gradient clipping. So if self.max grad norm is not none, we can do self.accelerator.clip grad norm self.generator dot parameters self.max grad norm. And actually, now that I think about it, technically the discriminator should have also had a grad norm. That's my bad. It's fine. And now that we have that, we can do optimizer dot step and our scheduler dot step. And this is one of those passes. Of course, we have all these different losses. We'd like to just like visualize them. So I'm just gonna, again, paste this in. If we're training on multiple GPUs, then we need to gather them across the GPUs and average them together. So, the average across the GPUs. If we are not on multiple GPUs, then we just grab them and we're done. And so there you go. That's our accumulated losses. And now what we're going to do is our discriminator step. If self.discriminator is not none, what we're going to do is our disk optimizer dot 0 grad set to none. It's true. Go ahead and zero those out, and let's go ahead and do it. Now, here's a super key idea that I haven't mentioned yet, but you can see right here. Given that the discriminator tends to overpower easily the decoder, we update its weights with a probability of 2/3 and a probability of half at 48 kilohertz. So because we're doing 24 kilohertz, we're going to do 2/3. So this means we're going to random sample, and only every now and then, basically only 2/3 of the time are we going to update the discriminator. That's how they handle it. So we're going to do exactly the same thing. So we're going to do our rand is equal to torch.rand. Size, it's just a single number, so empty. Device equals self.accelerator.device. And then what we need to do is rand is going to be accelerate.utils.broadcast rand from process is 0. So we need to make sure that if we generate random numbers, different GPUs will of course generate different random numbers. We're going to base it on just GPU 0. So we're going to copy that random value to all GPUs. So all GPUs have exactly the same rand value. And then all we need to do is if rand is less than self.diskUpdateProb, which I have stored all the way up here somewhere. Disk update prob, right, set to 0.666, so 2/3. So as long as it's less than that, we're going to update. If it's greater, then we won't update. Then we can do logits real, logits fake, and we're also going to get those feature maps, but we don't really care about that when updating the discriminator. That's just for the generator. Self.discriminator, waveforms, output decoded dot detach, right? We don't need gradients. It's basically treated as a constant, right? That here. So basically we're making sure that these things are similar. That's what a discriminator has to generate or discriminate between. I scrolled up, sorry. There we go. And then our disk loss is going to be the discriminator loss between logits real and logits fake. And then self.accelerator.backward disk loss. And we'll oh yeah, I do clip the discriminator's gradients. We're good. I didn't miss it. It was just later because it's in the discriminator step. Go ahead, clip the gradients if we have to, and then go ahead and actually update the optimizer. Disk optimizer.step. Else, we're going to say disk loss. I'm just going to print it out as skipped. So we'll see that later. And then we can do disk. So regardless of if we update it or not, just to make sure our scheduler is the same, we're going to do disk scheduler.step. Just go ahead and update the scheduler, even if we then do the update, and that's okay, right? Otherwise, like the number of steps is, I don't really know how many steps the model is actually going to take, so let's keep updating and it's fine. And after all of this effort, we have completed one step of training. Everything after this is mostly just logging. So I'm going to just print stuff and walk through it because no one wants to see this. So first, we have our total progress is completed steps by total iterations. We just go ahead and print out like stuff about our training, all the different losses essentially. And yeah, these are just string. I'm just basically making it look nice. That's all. So there's nothing fancy in here. It's just logging. And then after that, we can go ahead and actually perform the log. So if we want to log to weights and biases, store everything in a dictionary, add in the disk learning rate if we're doing a discriminator, and if our disk loss is not just skipped, then go ahead and add that in as well. Log it with accelerate. So there we go. And then of course we have our evaluation loop. So if completed steps percent self.eval iterations is 0, no problem, then we can do self.generator.eval, throw it into evaluation mode, and then we're also going to do self.generator.train, throw it back into training mode afterwards so we don't forget that. And if discriminator is not none, right, then we're also going to do that here. And then later on, we're also going to make sure we put it back into training mode like that. So there we go. And now what we're going to do is just loop through our waveforms. So we're going to do for waveform in waveforms, in TQDM, test loader, disable equals not self.accelerator not self.accelerator dot is main process. Go ahead, loop through our waveforms, and just very simply do with torch dot no grad output is going to be self.generator waveforms, and then we have that same chunk of code from earlier to pass it into the discriminator. So there we go. and then we just compute our losses just like we did earlier. There we go. That's our generator losses. We go ahead and average them up across the GPUs and then store them in a list. So, average our time. The main things we care about in terms of interpretation is really the frequency loss. That's the one you want to keep an eye on when training these models. It gives you the most information of like how good the reconstructions are going to be. So the frequency loss, go ahead and just average them up, store it in a log, and there we go. We can then go ahead after we're done through this loop, go ahead and just average it up across all of the testing data. We can go ahead and print it out, so accelerator.print, print out the validation loss. If we want to log to weights and biases, then we can do that here as well, just log to weights and biases, and then we can reset the log back, right? So once we're done, we reset the log back to empty, and then in the next evaluation, we'll repopulate it again. Lastly, we need to do, of course, like I mentioned, the loss values are fine, and the main loss value you want to keep an eye on is that frequency loss. But listening to audio is a better metric in all ways, so we just need to make sure we do that. So we're going to do if completed, here, I'll just keep pasting. This is nothing interesting. So I'm going to just paste all of this in, and we'll just look through it. Here we go. So if we are in a generation step, then with the main process alone, we need to unwrap the model. Remember, so in Accelerate, if we do DDP, it like wraps the model in the DDP wrapper. We just need to unwrap it so we can access internal methods. And this is why we wrote the dot pass-through method. So in the EnCodec model, we wrote pass-through just to quickly pass an audio in and quickly get its reconstruction back, and that's it. So nothing else. And so we have right here the pass-through, and we essentially just loop through every single audio one at a time and pass them through our thing. So we loop through the cache audios, pass them through, and get our generations. And then we just go ahead and save those generations one at a time in a folder. And every couple iterations will, every maybe 1,000 or 2,000 iterations, we'll go ahead and save these. Lastly, of course, we need to checkpoint the model. Checkpointing is no different than most other checkpointing. It's just now we have our accelerator.saveState that does the heavy lifting for us. I had to turn this off, the safe serialization. So instead of using safe tensors, we're using normal PyTorch bin. I feel like the save state for Accelerate doesn't work for LSTMs for some reason because there's some shared weights. I have not figured that out, but just using bin is fine for now, so I'm going with that. And then we have our, if we're using the balancer, then we can go ahead and grab the balancer state dict and save that as balancer state.bin. So we can also resume the balancer later on. Once we're done. So we've, if completed steps, that means we're done. And at the very, very end, we can go ahead and just save the very final state, and we're done. One more tab. There we go. I believe that is correct. Let's see. Yeah, train. Good. And that's basically it. So that's our trainer, right? So very simple, nothing too crazy. As you can see, there's really not a lot of stuff going on here. The hard part was getting the model, the losses, the balancer. There's a lot of, this has been a crazy video already. So we've covered a ton of stuff. So I would not, if you've honestly made it this far, good for you. And yeah, mostly just about logging and things like that. So nothing of that much interest. I can then go ahead and look at my, yeah, let's just look at the actual model. So I'm just going to back out. EnCodec. I'm going to run accelerate launch runs. Okay, so yeah, just to be clear, we have essentially, I'm gonna close all this out. So we've essentially completed it. There's nothing left to do. All that is left is essentially I'm gonna close you, open you. I wrote this additional run.py, and this run.py basically loads that EnCodec trainer, and then it loads the config file, the training config, generator config. It loads the EnCodec model based on the config. It loads our discriminator based on the config, and then passes it to the EnCodec trainer, and then we can go ahead and train, and we're done, right? So that's all it's doing, and it's running it based on this specific config file, not the Maestro one. That was just something I'm playing with to see if I can get to train it on like piano audio, but that doesn't matter right now. And so yeah, these two are just set to false for now, just for simplicity. And everything else is the same, so nothing else has been changed. all these weights. These weights came directly from the paper, so I haven't changed any of that. We are only update the discriminator every like 0.666 times. These betas came again from the paper. Everything is just from the paper. And in this case, I already again had that data file where I passed it the path to all of my audio files. So yeah, so we have this run.py. If we simply run accelerator launch run.py, this should just initiate EnCodec's training. So let's see. Yeah, so it'll run. It'll start a new run. That's fine. So we get this training configuration at the beginning of number of samples, our segment and sampling rate, the number of model parameters, number of discriminator parameters, and then whether or not we are resuming from checkpoint and our starting iteration. So let's just give this a second. While that happens, I can pull up the... Yeah, so you can see it doing its thing. Make it a little bit wider so it actually fits in one line. And there you go. So you can see every now and then the discriminator is going to get skipped, right? Because we don't train the discriminator every single time. So let's open up weights and biases first, just to see. So we can see this training. It doesn't take too long. I trained it overnight, so it's not the worst thing, but that's fine. So we will stop that so we don't slow things down. What we're going to look at is LibreTTS. Here we go. So I have my training loop right here. Okay, so we can see I trained this for about 160,000. Oh, don't need you. This is their test loss, test frequency loss. This is really the one you want to keep an eye on because this is the most interpretable. Getting the time loss exactly correct is just kind of fine. We see that there's a huge spike here, so something went horribly wrong, but the model seemed to have recovered from it. Otherwise, I would have had to restart from an earlier time step. Here is a better example in the... Oh, here we go. So yeah, here's the frequency loss over time. We can see there's some spikings happening. This is kind of par for the course when training GAN-based models. It's always going to be some kind of instability. But yeah, so we can see it's trained. My frequency loss went down to about 2.7. So just use that as a reference. Forgot to record this part. Of course, this is the most important part. Our entire point of training these EnCodec type models, these audio codec models, isn't really for its ability to reduce the bit rate. I mean, of course, that's an important task that we want our models to be able to do, but rather we want to be able to take continuous audio and convert it to a sequence of discrete codes on which we can train large language models, right? That's our intended purpose for this, training speech large language models, and a lot of them are based on these codec types like Valley and whatever else it may be. And so in this specific scenario, we have to do a little bit of, we just need to actually be able to do this, which I did not show you, so that's what we're going to do right now. So what you see here essentially is just very simple. We have a couple of imports. We have our EnCodec model and the config. We need to be able to load a YAML file because our config file is YAML. Our load audio is the same as before. Just go ahead and load it, resample the audio, and then convert to mono. And then our main is going to be, here's the path to a config file. Here's the path to the weights of the model that I want to load. And then what I'm doing here is I have my list of audio files from my test set, right? From my test set. And all I want to do is go ahead and just pass in my audio and see what the tokens look like. And that's it. So we're going to do, if I print out audio files, we should see, let's just check, if name equals main. We're going to run the main method. And we should see a list, right? A huge list of our audio paths. Let's just grab the first one. So we're going to do path to audio is going to be our audio files, 0. Just gonna grab one of them just so we can do it. We also need to make sure we can load our model, so we can load that right here. So yeah, that's fine. So our config is going to be our load YAML path to config. And so again, this is just loading our standard config file that we had before, just basically that YAML file. It has all of our models configuration in it. So all we really care about is not the whole config, but specifically the generator config. So there we go. We now have our generators set up, and we can then do our model is equal to the, or actually we're going to do our EnCodec config is going to be the EnCodec config that we had from earlier, EnCodec config. We're going to load this specific config into it. So now we have our actual config file. This is that, dictionary, essentially, our data class that we created for our model. And then we can do our model alone is going to be the EnCodec model with this specific EnCodec config. Of course, we need to actually load the weights of the model. So state dict is going to be torch.load path to weights, which I've been stored right here in the bin file. And we can then do our model.load state dict, and that will go ahead and actually load the weights of this specific model that I've trained. So now what we're going to do is basically just take the audio that we have, load it, and then pass it into our setup. So we're going to do here, I'm going to actually get rid of this and put it right here, just for, you'll see why in a second. So our audio is going to be equal to load audio. We have our path to audio, and the sampling rate we can find in the config. So config, training config, and then the sampling rate. So we stored this in the config file, so we can grab it from there. Sampling rate. If we print out the audio, we should see a nice little waveform. Looks like there is no such file or directory. Yeah, of course. So basically we need to make sure we strip any extra white space off. Or I guess we need to do path to audio, strip any extra white space off. That's what we forgot. There we go. So now we have our waveform. There's just an extra, the new line character essentially was in there. So there we go. Now we have our path to audio. Now that we have that, we can go ahead and pass it into our model. So we're going to do first our model itself. Model is equal to, we're going to throw it into evaluation mode. So that's fine. And then we can do our with torch.noGrad. We're going to do tokens. Scale is equal to model.tokenize audio. And so now if we print out our tokens, we should see some tokens that have been processed. And so we can see these are the tokens we have. And if we print out the tokens.shape, we should have num codebook. So let's see here. We have 8 by 1 by 974. So basically what we have is 8. This is the number of codebooks. 1, which is the batch dimension. We only have one sample here. And then 974 is the sequence length, right? So basically the original audio got downsampled to 974. These are the sequences of tokens that we would like to train our future LLMs on. Of course, we don't have just one sequence of tokens, we have multiple sequences. And so to deal with that, there's a couple of tricks we're going to have to do and a couple of, papers that we can take inspiration from. But that's basically it. We have all of these tokens, and this is the discrete set that we would like to train LLMs on in the future. And let's go ahead and just listen to some of the results, right? Just to get an idea. So let's make sure the audio is working. Yeah, desktop audio is on. So we should be able to just listen to some stuff. So again, this model was trained for about 200,000-ish, a little bit less steps. So let's look here. So we have in our workdir, I have, let's go back to EnCodec. We're going to look at the working directory, and we're going to first look at the libretts. Here we go. And so what we have are, not this one, local, here we go. So in this libretts, we have my original inputs. So let's find that file. So these are checkpoints. We have our gen inputs. So let's just listen to one of them.
Well, said he, extending his hand to Monte Cristo, I suppose you have come to sympathize with me, for indeed misfortune has taken possession of...
Okay, so that's what the audio sounds like. Let's play its corresponding. So 2,000 iterations in. That's pretty bad, right? So let's maybe try 10,000 iterations in.
Well, said he, extending his hand to Monte Cristo, I suppose you have come to sympathize with me.
Not bad, right? So it's starting to sound like it. Let's look at it 200,000 steps in.
Well, said he, extending his hand to Monte Cristo, I suppose you have come to sympathize with me, for indeed misfortune has taken possession of...
Okay, so you can hear there's a little bit of roboticness, but that's not so far away from the original.
Well, said he, extending his hand to Monte Cristo, I suppose you have come to sympathize with me, for indeed misfortune...
Let's try another one. Let's listen to maybe this one.
But this undertaking, by reason of the great number and force of the London militia.
Okay, let's now listen to the last one.
But this undertaking, by reason of the great number and force of the London militia, was...
So that's a good reconstruction, right? I'm pretty happy with that. So the input and the reconstructions are very similar to each other. And that's basically what we want, right? Listening to it, so if we listen to the same file, let's listen maybe 30,000 in.
But this undertaking, by reason of the great number and force of the London militia, was thought...
So it's pretty good, but you can hear a little bit of that there. A little bit of like tinniness, roboticness, and that
But
disappears
this undertaking,
here.
by reason of the great number and force of the London militia, was thought by many to be a
Good. So yeah, that's basically the main takeaway here. I believe I have a couple of things I wanted to show based on this. So let's see what we have. In my sample, I have also done a couple things like this. So let's see. Visualizations, worked. I don't actually remember. Yeah, okay, we'll look at all that in a second. Let's just listen to the samples. So here is the original English sample.
Whatever you all prefer, said Elsie.
Okay, and here's my reconstruction.
Whatever you all prefer, said Elsie.
Pretty good, right? They're pretty similar. Now, a question I asked was, well, this data, this model, was just trained on English only. How does it transfer to other languages? So I grabbed a random French audio and a random, Chinese audio, and I tried the reconstruction just to see it. So let's listen to French first.
Comment faire en sorte de relier physiquement et socialement des populations réparties sur tout son territoire, parfois isolées dans des villages situés au fin fond de vallées très...
Okay, that's pretty good, right? And let's listen to now the reconstruction.
Comment faire en sorte de relier physiquement et socialement des populations réparties sur tout son territoire, parfois isolées dans des villages situés au fin fond de vallées très enclavées.
That's surprisingly close, right? Like, despite this model never being trained on French, that's a pretty good reconstruction. I'd be happy with that, which means we could easily fine-tune this on French just to improve it. Let's try Chinese.
我们平时能够遇见其他 stranger 的机会其实不是很多，所以其实这样的一个
Okay, let's listen to reconstruction.
我们平时能够遇见其他 stranger 的机会其实不是很多，所以其实这样的
This one is meaningfully worse. And this makes sense, right? If you think about like the distance or the difference between languages, French is closer to English than Chinese is, right? So this is kind of in line with what we would think. Another thing that I was curious to see, and this is important, is when we train these models, right? Let's go back to here. We have all of these code books, and what we do is we add all the codes together, the quantized, to get our estimate. But the question is, how many do we need? I trained 8 of them, but what if we only use 1 of them, or 2 of them, or however many? So what I've done here is, here's a sample again.
Whatever you all prefer, said Elsie.
Okay. What happens if I just use the 0th code, nothing else? So basically, we don't use codebooks 1 through 7. We only use we don't use codebooks 1 through 8, or 2 through 8. We only use codebook number 1. So the very first
Whatever
codebook.
you all prefer, said Elsie.
So listen to that again. Here's the original.
Whatever you all prefer, said Elsie. Whatever you all prefer, said Elsie.
So the first codebook is obviously capturing the semantic information, because it's capturing we can understand exactly what it is, what the person is saying. It just doesn't sound like the original. Let's listen again.
Whatever you all prefer, said Elsie.
There's the original.
Whatever you all prefer, said Elsie.
So it's the same words, just it doesn't sound like the person. Let's see what happens when we add in the first codebook.
Whatever you all prefer, said Elsie.
That's better. What if we add up to 4 of them?
Whatever you all prefer, said Elsie.
Okay, and then when we add all of them, of course.
Whatever you all prefer, said Elsie.
So we can see that the semantic information is captured in the first one, but acoustic detail, timbre, things like that. All like the personal acoustic information, your own voice features are better captured in deeper residual layers. So that's kind of cool to see. I thought I had an example of okay, so I guess I don't have it. I don't remember where I kept it anymore. I thought I had an example where I inferenced, so let's see, workdir, maestro. Oh yeah, this was kind of fun. I kind of trained it on piano, but this did not go well. I need to figure it out so you can see. So yeah, that's trained on piano, but it's very under optimized. I'm still working on it just for fun. So you can see it can be trained on non-speech, or it can be trained on anything. I believe, yeah, this is fine, and this is also fine. Okay, maybe I don't have it. So yeah, I trained an example, which I can't find anymore, of the what happens if we don't use any discriminator. And basically the audio sounds like garbage. Like without the discriminator, the audio does not sound good at all. So that shows that just the time loss and our frequency loss is not enough. That discriminator loss really helps with the audio quality. To wrap this up, let's go ahead and look at the last couple things, just some figures, right, for interest. So we can see that this is all fine, this is all fine, this is all fine. Yeah, this is all fine. Okay, so we can train the model. So here's what the spectrograms look like. So what I did is here's the original spectrogram, MEL spectrogram, for one of the audios. And then every couple iterations, I just grabbed the corresponding spectrogram. And you can see at the beginning, 2000 iterations in, we start to get some form of that frequency information coming in. But the more we train, the better those representations become, right? Like basically the detail of the spectrogram starts to appear. And we can see a couple of interesting things going on. Like, for example, in this original spectrogram, we can see there's actually some high frequency noise. That's what this stuff is here. We can see that high frequency noise has been slightly diminished here. So, because of course, true data doesn't have noise, and this model ends up kind of removing some of that information. But yeah, so this after 100,000 steps, 200,000 steps, it's hard to exactly perceive differences just based on the spectrograms alone. Just listening to them, you can hear a slight improvement by training for longer. Additionally, an important question, of course, is codebook utilization. I have 8 codebooks, each codebook having 1024 codes in them. Well, how many of them are actually being used? And so I kind of just plotted a bar of them, and you can see that the very first codebook is pretty utilized. Everything after that is relatively utilized, but it starts to die off. And this shows that either A, for this specific problem, maybe I don't need 8 codebooks. Maybe I only need 6 of them or 4 of them. Like I just don't need as many. Or I need to essentially incentivize the model for better codebook utilization. And this is exactly, so some other papers have found that the EMA update methods don't actually promote codebook utilization as well. And so those papers use the standard commitment loss rather than EMA updates. This is the Descript audio codec. So this is a very, very similar, it's based on the RVQGAN paper, but they use the, let me find it, commitment. Our model can be trained using the original VQAVA codebook and commitment loss without KMeans initializations or random restarts. And that's fine. Commitment loss, let me see, what would it be called? EMA? Proposed with EMA. So yeah, they find here that basically the entropy, like, codebook, the EnCodec seems to have worse entropy, worse utilization than this one here. That's basically it. They essentially find that using EMA, it suffers from codebook underutilization. That's all. So that's exactly what I wanted to mention, right? They find better. So maybe I'll add it to the package later to actually include that. So we don't use EMA and just use standard codebook commitment loss. And again, I tested the out-of-domain sample just to see how it works on audio it's never seen before, like French and Chinese. So we are listening to that. And we also listened to how many codebooks do we need. So this is the original audio. And then here's codebook just 0. And we can see that, like, if we zoom in here, really zoom in here. Look at these. Here, what you have is your main, like, frequency, and you kind of have harmonics. And the harmonics of your voice is kind of what determines a lot of your, like, the sound and timbre and things like that. What you see here is some of those harmonics seem to be missing. We have some of them here, some of them are missing here. And as we add additional code vectors, we get better and better representations. Like those small details essentially seem to be appearing. And that's basically it, right? So this is a codec. This was a very long video, way longer than I thought it was going to be. That is the entire EnCodec architecture. Like I mentioned, after training this, you can go back and train additional transformers on those codes directly to further drop the bit rate. So our bit rate is 6 kilobits per second. So going back to here, right here, and then right here, we had 8 codes per sample because we had 8 codebooks. We had 75 samples per second because we downsampled by a factor of 320 from 24,000 down to 75. And because each codebook had 1024 codes in it, there are 10 bits each. So that puts us at 6 kilobits per second, way lower than the 384 kilobits the raw audio would have been. And that's basically it. Now we can further drop this down, and a lot of modern architectures are basically about this. How do we reduce this, continue reducing it more and more? And doing entropy coding with arithmetic, basically arithmetic coding, like Huffman coding and things like that is a trick to do bit packing, to keep more frequent codes, give them less bits, less frequent codes, give them more bits, and so you get a better representation. To do that, you need probabilities to do arithmetic coding, and what's better to generate probabilities than a transformer, right? And that's basically it. So yeah, this was a long one. If you made it this far, good for you. It's very impressive. This is actually a very challenging architecture. As you can see, there's just a lot of pieces going on. I would highly recommend, if you have done this, then going back and starting to come up with your own ideas is definitely the way, because audio codecs, we kind of talked about it, like its importance is for reducing the dimensionality, the size that audio takes in our systems, in network systems or storage systems, whatever they may be. But of course, a lot of these speech large language models are trained directly on these indexes. They're essentially, these models are being treated like speech tokenizers. And that's what we'll be working on in the future, hopefully, to train our own speech tokenizer to generate audio. Because if I can generate these token sequences here, I can pass them to the decoder to actually generate audio, which would be awesome. So that's it for this one, and I will see y'all in the next one.